Okay, so welcome back. So we're going to start by doing some review, and we're going to talk about test sets, training sets, validation sets, and OOB. Something we haven't covered yet, but we will cover in more detail later, is also cross-validation, but I'm going to talk about that as well. Right? So we have a data set with a bunch of rows in it, and we've got some dependent variable. And so what's the difference between like machine learning and kind of pretty much any other kind of work? The difference is that in machine learning, the thing we care about is the generalization accuracy or the generalization error, whereas in like pretty much everything else, all we care about is how well we kind of map to the observations, full stop. And so this thing about generalization is the key unique piece of machine learning. And so if we want to know whether we're doing a good job of machine learning, we need to know whether we're doing a good job of generalizing. If we don't know that, we know nothing, right? Yeah.
By generalizing, do you mean like scaling? Being able to scale larger data sets?
No, I don't mean scaling at all. So scaling is an important thing in many, many areas. It's like, okay, we've got something that works on my computer with 10,000 items. I now need to make it work on 10,000 items per second or something. So scaling is important, but not just for machine learning, for just about everything we put in production. Generalization is where I say, okay, here is a model that can predict cats from dogs. I've looked at 5 pictures of cats, 5 pictures of dogs, and I've built a model that is perfect. And then I look at a different set of 5 cats and dogs, and it gets them all wrong. So in that case, what it learnt was not the difference between a cat and a dog, but it learnt what those 5 exact cats look like and those 5 exact dogs look like. Or I've built a model of predicting grocery sales for a particular product. So for toilet rolls in New Jersey last month. And then I go and put it into production, and it scales great. In other words, it has a great latency. I don't have a high CPU load, but it fails to predict anything well other than toilet rolls in New Jersey. And it also turns out it only did it well for last month, not the next month. So these are all generalization failures. So the most common way that people check for the ability to generalize is to create a random sample. So they'll grab a few rows at random and pull it out into a test set. And then they'll build all of their models on the rest of the rows. And then when they're finished, they'll check the accuracy they got on there. So the rest of the rows are called the training set. Everything else we could call the training set. And so at the end of their modeling process on the training set, they got an accuracy of 99% at predicting cats from dogs. At the very end, they check it against a test set to make sure that the model really does generalize. Now, the problem is, what if it doesn't, right? So, okay, well, I could go back and change some hyperparameters, do some data augmentation, whatever else, try to create a more generalizable model. And then I'll go back again after doing all that and check, and it's still no good. Right? And I'll keep doing this again and again until eventually, after 50 attempts, it does generalize. But does it really generalize? Because maybe all I've done is accidentally found this one which happens to work just for that test set, because I've tried 50 different things, right? And so if I've got something which is like right coincidentally 0.05% of the time, then I'm very likely to accidentally get a good result. So what we generally do is we put aside a second data set. I've got a couple more of these and put these aside into a validation set. Validation set. right? And then everything that's not in the validation or test is now training. And so what we do is we train a model, check it against the validation to see if it generalizes, do that a few times, and then when we finally got something where we're like, okay, we think this generalizes successfully based on the validation set, and then at the end of the project, we check it against the test set. Yeah.
So basically, by making this two-layer test set validation set, if it gets one right, the other one wrong, you kind of double-checking your errors, kind of like.
It's checking that we haven't overfit to the validation set. So if we're using the validation set again and again, then we could end up not coming up with a generalizable set of hyperparameters, but a set of hyperparameters that just so happen to work on the training set and the validation set. So if we try 50 different models against the validation set, and then at the end of all that, we then check that against the test set, and it still generalizes well, then we're kind of going to say, okay, that's good. We've actually come up with a generalizable model. If it doesn't, then that's going to say, okay, we've actually now overfit to the validation set. At which point you're kind of in trouble, right? Because you don't have anything left behind, right? So the idea is to use effective techniques during the modeling so that doesn't happen, right? But if it's going to happen, you want to find out about it. Like you need that test set to be there, because otherwise when you put it in production and then it turns out that it doesn't generalize, that would be a really bad outcome, right? You end up with less people clicking on your ads or selling less of your products or providing car insurance to very risky vehicles or whatever.
Just to make sure, do you need to ever check if the validation set and the test set is coherent, or you just keep test set away?
So if you've done what I've just done here, which is to randomly sample, there's no particular reason to check as long as they're big enough, right? But we're going to come back to your question in a different context in just a moment. Now, another trick we've learned for random forests is a way of not needing a validation set. And the way that we learned was to instead use the OOB error, or the OOB score. And so this idea was to say, well, every time we train a tree in a random forest, there's a bunch of observations that are held out anyway, because that's how we get some of the randomness. And so let's calculate our score for each tree based on those held out samples, and therefore the forest by averaging the trees that each row was not part of training. Okay. And so the OOB score gives us something which is pretty similar to the validation score. But on average, it's a little less good. Can anybody either remember or figure out why on average it's a little less good? Quite a subtle one. Can I give it to Chenshi?
I'm not sure, but is it because you are you are doing every kind of pre-processing on your test set, and so the OOB score is reflecting the performance on testing set?
No, so the OOB score is not using the test set at all. The OOB score is using the held out rows in the training set for each tree.
So I mean, you are basically testing each tree on some data from the training set.
Yes.
So you have the potential of overfitting the training set.
It shouldn't cause overfitting because each one is looking at a held out sample, so it's not an overfitting issue. It's quite a subtle issue. Ernest, do you want to have a try?
Aren't the samples from OOB bootstrap samples?
They are.
And so then you're never going to, on average, they only grab 63% of the chance.
So on average, the OOB is 1 minus 63%. Yeah.
Exactly, yeah.
And so what's the issue?
So then if you're not...
So why would the score be lower than the validation score?
Then that implies that you're leaving sort of like a black hole in the data, that there's like data points you're never going to sample and they're not going to be represented by the model.
No, that's not true though, because each tree is looking at a different set, right? So the OOB, so like we've got like, I don't know, dozens of models, right? And in each one, there's a different set of rows, which happen to be held out, right? And so when we calculate the OOB score for like, let's say row 3, we say, okay, row 3 is in this tree, and that's it. And so we calculate the prediction on that tree and for that tree, and we'd average those two predictions. And so with enough trees, each one has a 40 or so percent chance that the row is in that tree. So if you have 50 trees, it's almost certain that every row is going to be mentioned somewhere. Did you have an idea, Karim?
With validation set, we can use the whole forest to make the predictions, but here we cannot use the whole forest, so we cannot exactly see.
Exactly. So every row is going to be using a subset of the trees to make its prediction. And with less trees, we know we get a less accurate prediction. So that's a subtle one, right? And if you didn't get it, have a think during the week until you understand why this is, because it's a really interesting test of your understanding of random forests, of why is OOB score on average less good than your validation score? They're both using random held out subsets. Anyway, it's generally close enough, right? So why have a validation set at all when you're using a random forest? If it's a randomly chosen validation set, it's not strictly speaking necessary, but you've got 4 levels of things to test, right? So you could test on the OOB. When that's working well, you can test on the validation set, when hopefully by the time you check against the test set, there's going to be no surprises. So that'd be one good reason. Then what Kaggle do, the way they do this is kind of clever. What Kaggle do is they split the test set into 2 pieces, a public and a private. And they don't tell you which is which. So you submit your predictions to Kaggle, and then a random 30% of those are used to tell you the leaderboard score. But then, at the end of the competition, that gets thrown away, and they use the other 70% to calculate your real score. So what that's doing is that you're making sure that you're not continually using that feedback from the leaderboard to figure out some set of hyperparameters that happens to do well on the public, but actually doesn't generalize. Okay, so it's a great test. This is one of the reasons why it's good practice to use Kaggle, because at the end of a competition, at some point this will happen to you, and you'll drop 100 places on the leaderboard the last day of the competition when they use the private test set, and it's oh, okay, that's what it feels like to overfit. And it's much better to practice and get that sense there than it is to do it in a company where there's hundreds of millions of dollars on the line. Okay, so this is the easiest possible situation where you're able to use a random sample for your validation set. Why might I not be able to use a random sample for my validation set? I'm going to pass it to Taylor.
In the case of something where we're forecasting, we can't randomly sample because we need to maintain the temporal ordering.
Go on. Why is that?
Because it doesn't make sense. So in the case of an ARMA model, I can't use I can't pull out random rows because I'm thinking that there's a certain dependency, or I'm trying to model a certain dependency that relies on a specific lag term. And if I randomly sample those things, then that lag term isn't there for me to use. Okay,
so it could be a technical modeling issue that I'm using a model that relies on yesterday, the day before, and the day before that. And if I've randomly removed some things I don't have yesterday, and my model might just fail. Okay, that's true, but there's a more fundamental issue. Do you want to pass it to Tyler? It's a really good point. Although, in general, we're going to try to build models that are more resilient than that.
Particularly with, temporal order. We expect things that are close by in time to be related to things close to them. Mm-hmm. So if we destroy the order, if we destroy the order, we really aren't going to be able to use that this time is close to this other time.
I don't think that's true, because we can pull out a random sample for our validation set and still keep everything nicely ordered.
Well, so we would like to predict things in the future, which we would require as much data close to the end of our.
Okay, that's true. I mean, we could be like limiting the amount of data that we have by taking some of it out. But my claim is stronger. My claim is that by using a random validation set, we could get totally the wrong idea about our model. Karam, do you want to have a try?
So if our data is imbalanced, for example, we can, if we are randomly sampling it, we can only have one class in our validation set. So our fitted model maybe.
That's true as well. So
different.
maybe you're trying to predict in a medical situation who's going to die of lung cancer, and that's only 1 out of 100 people, and we pick out a validation set that we accidentally have nobody that died of lung cancer. That's also true. These are all good niche examples, but none of them quite say, like, why could the validation set just be plain wrong? Like, give you a totally inaccurate idea of whether this is going to generalize. And so let's talk about, and the closest is what Tyler was saying about time, closeness in time. The important thing to remember is when you build a model, you always have a systematic error, which is that you're going to use the model at a later time than the time that you built it, right? Like, you're going to put it into production, by which time the world is different to the world that you're in now. And even when you're building the model, you're using data which is older than today anyway, right? So there's some lag between the data that you're building it on and the data that it's going to actually be used on in real life. And a lot of the time, if not most of the time, that matters, right? So if we're doing stuff in like predicting who's going to buy toilet paper in New Jersey, and it takes us 2 weeks to put it in production, and we did it using data from the last couple of years, then by that time, things may look very different, right? And particularly, our validation set, if we randomly sampled it, right, and it was like from a 4-year period, then the vast majority of that data is going to be over a year old, right? And it may be that the toilet buying habits of folks in New Jersey may have dramatically shifted. Maybe they've got a terrible recession there now and they can't afford high quality toilet paper anymore. Or maybe their paper making industry has gone through the roof and suddenly, they're buying lots more toilet paper because it's so cheap or whatever, right? So the world changes, and therefore if you use a random sample for your validation set, then you're actually checking how good are you at predicting things that are totally obsolete now. Right? How good are you at predicting things that happened 4 years ago? That's not interesting. Okay? So what we want to do in practice, anytime there's some temporal piece, is to instead say, assuming that we've ordered it by time, right? So this is old, and this is new. That's our validation set. Okay? Or if we, I suppose actually do it properly, that's our validation set, that's our test set. Make sense? Right? So here's our training set, and we use that, and we try and build a model that still works on stuff that's later in time than anything the model was built on. And so we're not just testing generalization in some kind of abstract sense, but in a very specific time sense, which is it generalizes to the future. Could you pass it to Suraj, please?
So when we are, as you said,
could you lift it up?
As you said, there is some temporal ordering in the data. So in that case, is it wise to take the entire old data for training, or only a few recent data set?
For validation, test, or training?
No, I'm talking about training.
Training. Yeah, that's a whole other question, right? So how do you get the validation set to be good? So I build a random forest on all the training data. It looks good on the training data. It looks good on the OOB, right? And this is actually a really good reason to have OOB. If it looks good on the OOB, then it means you're not overfitting in a statistical sense. Right? Like it's working well on a random sample. But then it looks bad on the validation set. So what happened? Well, what happened was that you somehow failed to predict the future. You only predicted the past. And so Suraj had an idea about how we could fix that. Would be, okay, well, maybe we should just train. So like maybe we shouldn't use the whole training set. We should try a recent period only. And now, on the downside, we're now using less data, so we can create less rich models. On the upside, it's more up-to-date data. And this is something you have to play around with. Most machine learning functions have the ability to provide a weight that is given to each row. So, for example, with a random forest, rather than bootstrapping at random, you could have a weight on every row and randomly pick that row with some probability, right? And we could say, here's our probability. We could pick a curve that looks like that. So the most recent rows have a higher probability of being selected. That can work really well. Yeah, it's something that you have to try, and if you don't have a validation set that represents the future compared to what you're training on, you have no way to know which of your techniques are working. How do you make the compromise between amount of data versus recency of data? So what I tend to do is when I have this kind of temporal issue, which is probably most of the time, once I have something that's working well on the validation set, I wouldn't then go and just use that model on the test set, because the thing that I've trained on is now the test set is much more in the future compared to the training set. So I would then replicate building that model again, but this time I would combine the training and validation sets together, okay, and retrain the model. And at that point, you've got no way to test against a validation set, so you have to make sure you have a reproducible script or notebook that does exactly the same steps in exactly the same ways. Because if you get something wrong, then you're going to find on the test set that you've got a problem. So what I do in practice is I need to know, is my validation set a truly representative of the test set? So what I do is I build 5 models on the training set. I build 5 models on the training set, and I try to have them kind of vary in how good I think they are, right? And then I score them, my 5 models, on the validation set, right? And then I also score them on the test set, right? So I'm not cheating, so I'm not using any feedback from the test set to change my hyperparameters. I'm only using it for this one thing, which is to check my validation set. So I get my 5 scores from the test set. And then I check that they fall in a line. Okay? And if they don't, then you're not going to get good enough feedback from the validation set. So keep doing that process until you're getting a line. And that can be quite tricky, right? Sometimes the test set, trying to create something that's as similar to the real world outcome as possible, it's difficult, right? And when you're kind of in the real world, the same is true of creating the test set. Like the test set has to be as close to production as possible. So what's the actual mix of customers that are going to be using this? How much time is there actually going to be between when you build the model and when you put it in production? How often are you going to be able to refresh the model? These are all the things to think about when you build that test set. Okay. Yeah, first.
So you want to say that first make 5 models on the training data,
yeah,
and then till you get a straight line relationship, change your validation and test set?
You can't really change the test set generally. So this is assuming that the test set's given. Change the validation set. So if you started with a random sample validation set and then it's all over the place and you realize, oh, I should have picked the last 2 months, and then you pick the last 2 months and it's still all over the place and you realize, oh, I should have picked it so that's also from the 1st of the month to the 15th of the month, and keep going until changing your validation set until you found a validation set which is indicative of your test set results.
So the 5 models, you would start maybe just the random data and then average and like just make it better or
Yeah, I
worse?
mean, maybe exactly, maybe kind of 5 like not terrible ones, but you want some variety, and you also particularly want some variety in like how well they might generalize through time. So one that was trained on the whole training set, one that was trained on the last 2 weeks, one that was trained on the last 6 weeks, one which used lots and lots of columns and might overfit a bit more. Yeah. So you kind of want to get a sense of like, oh, if my validation set fails to generalize temporally, I'd want to see that. If it fails to generalize statistically, I'd want to see that.
Sorry, can you explain in a bit more detail what you mean by change your validation set so it indicates the test set? Like, what does that look like?
So let's take the groceries competition where we're trying to predict the next 2 weeks of grocery sales. So possible validation sets that Terence and I played with was a random sample, the last month of data, the last 2 weeks of data, and the other one we tried was same day range, 1 month earlier. So the test set in this competition was the 1st to the 15th of August. Sorry, the 15th, maybe the 15th to the 30th of August. So we tried like a random sample is 4 years. We tried the 15th of July to the 15th of August. We tried the 1st of August to the 15th of August. And we tried the 15th of July to the 30th of July. And so there were 4 different validation sets we tried. And so with random, our kind of results were all over the place. With last month, they were like not bad, but not great. The last 2 weeks, there was a couple that didn't look good, but on the whole, they were good. And same day range of the month earlier, they got a basically perfect line.
So that's the part I'm talking about right there. What exactly are you comparing it to from the test set? I just got confused what you're creating that graph off of.
So for each of those, so I build 5 models, right? So there might be like, just predict the average, do some kind of simple group mean of the whole data set, do some group mean of the last month of the data set, build a random forest of the whole thing, build a random forest from the last 2 weeks. On each of those, I calculate the validation score, and then I retrain the model on the whole training set and calculate the same thing on the test set. And so each of these points now tells me how well did it go in the validation set, how well did it go in the test set. And so if the validation set is useful, we would say every time the validation set improves, the test set score should also improve.
Yeah, so you just said retrain. Do you mean retrain the model on training and validation set?
Yeah, that was the step I was talking about here. So once I've got the validation score based on just the training set, I would then retrain it on the train and validation and check against test.
Right, just to make sure.
Somebody else?
So just to clarify, by test set you mean submitting it to Kaggle and then checking the score?
If it's Kaggle, then your test set is Kaggle's leaderboard.
Okay.
In the real world, the test set is this third data set that you put aside, and it's that third data set that having it reflect real world production differences is the most important step in a machine learning project. Why is it the most important step? Because if you screw up everything else, but you don't screw up that, you'll know you've screwed up, right? Like if you've got a good test set, then you'll know you screwed up because you screwed up something else and you tested it and it didn't work out. And it's like, okay, you're not going to destroy the company, right? If you screwed up creating the test set, that would be awful, right? Because then you don't know if you've made a mistake, right? You try to build a model, you test it on the test set, it looks good, but the test set was not indicative of real world environment. So you don't actually know if you're going to destroy the company, right? Now, hopefully you've got ways to put things into production gradually so you won't actually destroy the company, but you'll at least destroy your reputation at work, right? It's like, oh, Jeremy tried to put this thing into production, and in the first week, the cohort we tried it on, their sales halved, and we're never going to give Jeremy a machine learning job again, right? But if Jeremy had used a proper test set, then like he would have known, this is like half as good as my validation set said it would be, I'll keep trying, right? And now I'm not going to get in any trouble. I was actually like, oh, Jeremy's awesome. He identifies ahead of time when there's going to be a generalization problem. Okay. So this is something that kind of everybody talks about a little bit in machine learning classes, but often it kind of stops at the point where you learn that there's a thing in sklearn called make test train split, and it returns these things, and off you go, right? But the fact that or here's the cross-validation function, right? So the fact that these things always give you random samples tells you that much, if not most of the time, you shouldn't be using them. The fact that random forest gives you an OOB for free, it's useful, but it only tells you that this generalizes in a statistical sense, not in a practical sense, right? So then finally, there's cross-validation, right? Which outside of class, you guys have been talking about a lot, which makes me feel somebody's been overemphasizing the value of this technique. So I'll explain what cross-validation is, and then I'll explain why you probably shouldn't be using it most of the time. So cross-validation says, let's not just pull out one validation set, but let's pull out 5, say. So let's assume that we're going to randomly shuffle the data first, right? This is critical, right? We first randomly shuffle the data. And then we're going to split it into 5 groups. And then for model number 1, we'll call this the validation set. And we'll call this the training set. Okay? And we'll train, and we'll check against the validation, and we'll get some RMSE, R squared, whatever. And then we'll throw that away. And we'll call this the validation set. And we'll call this the training set. And we'll get another score. Okay? We'll do that 5 times. And then we'll take the average. Okay, so that's a cross-validation average accuracy. So who can tell me a benefit of using cross-validation over the kind of standard validation set I talked about before? Could you pass it to Feng?
If you have a small data set, then cross-validation will make use of the data you have.
Yeah, you can use all of the data. You don't have to put anything aside. And you kind of get a little benefit as well in that, you've now got 5 models that you could ensemble together, each one which used 80% of the data. So, sometimes that ensembling can be helpful. Feng, could you tell me, what could be some reasons that you wouldn't use cross-validation?
We have enough data, so we not want the validation set to be included in the model training process to pollute the model.
Okay, yeah, I'm not sure that cross-validation is necessarily polluting the model. What would be a key downside of cross-validation?
But for deep learning, if you have learned the pictures and the neural network will know the picture, and it's more likely to predict it left and right. So, I guess
sure, but if we put aside some data each time in the cross-validation, can you pass that to Suraj? I'm not so worried about. I don't think there's one of these validation sets is more statistically accurate. Yes, Suraj.
If I'm not mistaken, will we be overfitting the data? If you're trying to...
I think that's what Feng was worried about. I don't see why that would happen. Each time we're fitting a model, just behind you. Each time we're fitting a model, we are absolutely holding out 20% of the sample, right? So yes, the 5 models between them have seen all of the data, but it's kind of like a random forest. In fact, it's a lot like a random forest. Each model has only been trained on a subset of the data. Yes, Nishan.
Say if it is like a large data set, like it will take a lot of time.
Oh, yes, exactly. Right? So we have to fit 5 models rather than 1. So here's a key downside. Number 1 is time. And so if we're doing deep learning and it takes a day to run, suddenly it now takes 5 days, or we need 5 GPUs. Okay, what about my earlier issues about validation sets? Do you want to pass it over there? What's your name? Jose.
Yes. So if you had like temporal data, wouldn't you be, like by shuffling, wouldn't you be breaking that relation?
Well, we could unshuffle it afterwards. We could reorder it. Like we could shuffle, get the training set out, and then sort it by time. Presumably there's a date column there, so I don't think it's going to stop us from building a model. Did you have Ernest?
With cross-validation, you're building 5 even validation sets, and if there is some sort of structure that you're trying to capture in your validation set to mirror your test set, you're essentially just throwing that a chance to construct that yourself.
Right. I think you're going to say that. I think you said the same thing as I'm going to say, which is that our earlier concerns about why random validation sets are a problem are entirely relevant here. All these validation sets are random. So if a random validation set is not appropriate for your problem, most likely because, for example, of temporal issues, then none of these 5 validation sets are any good. They're all random, right? And so if you have temporal data like we did here, there's no way to do cross-validation really, or like probably no good way to do cross-validation. I mean, you want to have your validation set be as close to the test set as possible, and so you can't do that by randomly sampling different things. So, so as Feng said, you may well not need to do cross-validation because most of the time in the real world, we don't really have that little data, right? Unless your data is based on some very, very expensive labeling process or some experiments that cost a lot to run or whatever. But nowadays, data scientists are not very often doing that kind of work. Some are, in which case this is an issue, but most of us aren't. So we probably don't need to. As Nishan said, if we do it, it's going to take a whole lot of time, right? And then as Ernest said, even if we did do it, and we took up all that time, it might give us totally the wrong answer because random validation sets are inappropriate for our problem. Okay? So I'm not going to be spending much time on cross-validation because I think it's an interesting tool to have. It's easy to use. sklearn has a cross-validation thing you can go ahead and use. But it's not that often that it's going to be an important part of your toolbox, in my opinion. It'll come up sometimes. Okay, so that is validation sets. So then the other thing we started talking about last week and got a little bit stuck on because I screwed it up was tree interpretation. So I'm actually going to cover that again without the error and dig into it in a bit more detail. So can anybody tell me what tree interpreter does and how it does it? Anybody remember? It's a difficult one to explain. I don't think I did a good job of explaining it, so don't worry if you don't do a great job. But does anybody want to have a go at explaining it? No? Okay, that's fine. So let's start with the output of tree interpreter. So if we look at a single model, a single tree, in other words, here is a single tree. Okay. And so to remind us, the top of a tree is before there's been any split at all. So 10.189 is the average log price of all of the options in our training set. So I'm going to go ahead and draw right here. 10.189 is the average of all. Okay. And then if I go coupler system less than or equal to 0.5, then I get 10.345. Okay, so for this subset of 16,800, coupler is less than or equal to 0.5, the average is 10.345. And then of the people with a coupler system less than or equal to 0.5, we then take the subset where enclosure is less than or equal to 2, and the average there of log sale price is 9.955. So here's 9.955. Okay? And then final step in our tree is model ID, just for this group with no coupler system, with enclosure less than or equal to 2. Then let's just take model ID less than or equal to 4573. And that gives us 10.226. Okay? So then we can say, all right, starting with 10.189, average for everybody in our training set for this particular tree's subsample of 20,000. Adding in the coupler decision for coupler less than or equal to 0.5 increased our prediction by 0.156. So if we predicted with a naive model of just the mean, it would have been 10.189. Adding in just the coupler decision would have changed it to 10.345. So this variable is responsible for a 0.156 increase in our prediction. From that, the enclosure decision was responsible for a minus 0.395 decrease. The model ID was responsible for a 0.276 increase, until eventually that was our final decision. That was our prediction for this auction of this particular sale price. So we can draw that as what's called a waterfall plot, right? And waterfall plots are one of the most useful plots I know about. And weirdly enough, there's nothing in Python to do them. And this is one of these things where there's this disconnect between like the world of like management consulting and business, where everybody uses waterfall plots all the time, and like academia, who have no idea what these things are. But like every time like you're looking at, say, here is last year's sales for Apple, and then there was a change in that iPhones increased by this amount, Macs decreased by that amount, and iPads increased by that amount. Every time you have a starting point in a number of changes and a finishing point, waterfall charts are pretty much always the best way to show it. So here, our prediction for price based on everything, 10.189. There was an increase, blue means increase, of 0.156 for coupler, decrease of 0.395 for enclosure, increase model ID of 0.276. So increase, decrease, increase to get to our final 10.266. So you see how a waterfall chart works? So with Excel 2016, it's built in. You just click Insert Waterfall Chart, and there it is. If you want to be a hero, create a waterfall chart package for Matplotlib, put it on pip, and everybody will love you for it. There are some like really crappy gists and manual notebooks and stuff around. These are actually super easy to build. Like you basically do a stacked column plot where the bottom of this is like all white, right? Like you can kind of do it, but if you can wrap that up all and put the data, the points in the right spots and color them nicely, that would be totally awesome. I think you've all got the skills to do it, and would make, be a terrific thing for your portfolio. So there's an idea. Could make an interesting Kaggle kernel even. Like, here's how to build a waterfall plot from scratch. And by the way, I've put this up on pip. You can all use it. So in general, therefore, obviously, going from the all and then going through each change, then the sum of all of those is going to be equal to the final prediction. So that's how we could say, if we were just doing a decision tree, then, you're coming along and saying, like, how come this particular auction was this particular price? And it's like, well, or your prediction for it, and like, oh, it's because of these three things had these three impacts, right? So for a random forest, we could do that across all of the trees, right? So every time we see coupler, we add up that change. Every time we see enclosure, we add up that change. Every time we see model, we add up that change, okay? And so then we combine them all together, we get what tree interpreter does. Right? So you could go into the source code for tree interpreter, right? It's not at all complex logic, or you could build it yourself, right? And you can see how it does exactly this. So when you go tree interpreter.predict with a random forest model for some specific auction, so I've got a specific row here, this is my 0 index row, it tells you, okay, this is the prediction, the same as the random forest prediction. Bias, this is going to be always the same, it's the average sale price for everybody for each of the random samples in the tree. And then contributions is the average of, the total of all the contributions for each time we see that specific column appear in a tree. Right? So last time I made the mistake of not sorting this correctly. So this time np.argsort is a super handy function. It sorts, it doesn't actually sort contribution 0. It just tells you where each item would move to if it were sorted. So now by passing IDXS to each one of the column, the level, contribution, I can then print out all those in the right order. So I can see here, here's my column, here's the level, and the contribution. So the fact that it's a small version of this piece of industrial equipment meant that it was less expensive. Right? But the fact it was made pretty recently meant that it was more expensive. The fact that it's pretty old, however, made that it was less expensive. Right? So this is not going to really help you much at all with like a Kaggle style situation where you just need predictions. But it's going to help you a lot in a production environment or even pre-production. Right? So like something which any good manager should do if you say, here's a machine learning model I think we should use, is they should go away and grab a few examples of actual customers or actual auctions or whatever and check whether your model looks intuitive, right? And if it says like, my prediction is that, lots and lots of people are going to really enjoy this crappy movie, and it's like, wow, that was a really crappy movie, then they're going to come back to you and say like, explain why your model's telling me that I'm going to like this movie because I hate that movie. And then you can go back and you say, well, it's because you like this movie and because you're this age range and you're this gender. On average, actually, people like you did like that movie. Okay, yeah.
What's the second element of each tuple?
This is saying for this particular row, it was a mini. And it was 11 years old.
Got it.
And it was a hydraulic excavator track, 3 to 4 metric tons.
Yeah, got it. Thank you.
So it's just feeding back and telling you. Because this is actually what it was. It was these numbers. So I just went back to the original data to actually pull out the descriptive versions of each one. Okay. So if we sum up all the contributions together and then add them to the bias, then that would be the same as adding up those 3 things, adding it to this, and as we know from our waterfall chart, that gives us our final prediction. This is a almost totally unknown technique, and this particular library is almost totally unknown as well. So like it's a great opportunity to, show something that a lot of people, like it's totally critical in my opinion, but rarely known. So that's kind of the end of the random forest interpretation piece. And hopefully you've now seen enough that when somebody says, we can't use modern machine learning techniques because they're black boxes that aren't interpretable, you have enough information to say, you're full of shit, right? Like, they're extremely interpretable, and the stuff that we've just done, trying to do that with a linear model, good luck to you. Even where you can do something similar with a linear model, trying to do it so that it's not giving you totally the wrong answer, and you had no idea it was the wrong answer, is going to be a real challenge. So, the last step we're going to do before we try and build our own random forest is deal with this tricky issue of extrapolation. So in this case, if we look at our tree, let's look at the accuracy of our most recent trees. We still have, a big difference between our validation score and our training score. Actually, in this case, it's not too bad. The difference between the OOB and the validation is actually pretty close. So if there was a big difference between validation and OOB, like I'd be very worried about that we've dealt with the temporal side of things correctly. Let's just have a look at, I think our most recent model. Here it was. Yeah, so there's a tiny difference, right? And so on Kaggle, at least, you kind of need that last decimal place. In the real world, I'd probably stop here. But quite often you'll see there's a big difference between your validation score and your OOB score. And I want to show you how you would deal with that. Particularly because actually we know that the OOB should be a little worse because it's using less trees. So it gives me a sense that we should be able to do a little bit better. And so the way we should be able to do a little bit better is by handling the time component a little bit better. Here's the problem with random forests when it comes to extrapolation. When you've got a data set that's like, got 4 years of sales data in it, and you create your tree, right? And it says like, oh, if it's in some particular store and it's some particular item and it is on special, here's the average price, right? It actually tells us the average price, over the whole training set, which could be pretty old, right? And so when you then want to step forward to like, well, what's going to be the price next month? It's never seen next month, and whereas with a kind of a linear model, it can find a relationship between time and price, where even though we only had this much data, when you then go and predict something in the future, it can extrapolate that. But a random forest can't do that. There's no way, if you think about it, for a tree to be able to say, well, next month it would be higher still. So there's a few ways to deal with this, and we'll talk about it over the next couple of lessons. But one simple way is just to try to avoid using time variables as predictors if there's something else we could use that's going to give us a better, a kind of a stronger relationship that's actually going to work in the future. So in this case, what I wanted to do was to, first of all, figure out what's the difference between our validation set and our training set. Like if I understand the difference between our validation set and our training set, then that tells me what are the predictors which have a strong temporal component, and therefore they may be irrelevant by the time I get to the future time period. So I do something really interesting, which is I create a random forest where my dependent variable is it in the validation set? Right? So I've gone back and I've got my whole data frame with the training and validation all together. And I've created a new column called isValid, which I've set to 1. And then for all of the stuff in the training set, I set it to 0. Right? So I've got a new column which is just, is this in the validation set or not? And then I'm going to use that as my dependent variable and build a random forest. So this is a random forest not to predict price, to predict is this in the validation set or not. And so if your variables were not time dependent, then it shouldn't be possible to figure out if something's in the validation set or not. This is a great trick in Kaggle, right? Because in Kaggle, they often won't tell you whether the test set is a random sample or not. So you could put the test set and the training set together, create a new column called isTest, and see if you can predict it. If you can, you don't have a random sample, which means you have to come and figure out how to create a validation set from it, right? And so in this case, I can see I don't have a random sample because my validation set can be predicted with a 0.9999 R squared. And so then if I look at feature importance, the top thing is sales ID. And so this is really interesting. It tells us very clearly sales ID is not a random identifier, but probably it's something that's just set consecutively as time goes on. We just increase the sales ID. Sale elapsed, that was the number of days since the first date in our data set, so not surprisingly, that also is a good predictor. Interestingly, machine ID, clearly each machine is being labeled with some consecutive identifier as well. And then there's a big, don't just look at the order, look at the value. So 0.7, 0.1, 0.07, 0.002. Okay, stop, right? These top three are hundreds of times more important than the rest, right? So let's next grab those top three, right? And we can then have a look at their values, both in the training set and in the validation set. And so we can see, for example, sales ID on average is, I've divided by 1,000, on average is 1.8 million in the training set and 5.8 million in the validation set, right? So you can see, just confirm, like, okay, they're very different. So let's drop them. Okay, so after I drop them, let's now see if I can predict whether something's in the validation set. I still can with 0.98 R squared. So once you remove some things, then other things can come to the front, and it now turns out, okay, that's not surprisingly. Age, things that are old are, more likely, I guess, to be in the validation set because they've, earlier on in the training set, they can't be old yet. Year made, same reason. So then we can try removing those as well. And so once let's see, where do we go here? Yeah, so what we can try doing is we can then say, all right, let's take the sales ID, so that's machine ID from the first one, the age, year made, sale day of year from the second one, and say, okay, these are all time-dependent features. So I still want them in my random forest if they're important, right? But if they're not important, then taking them out, there are some other non-time dependent variables that work just as well. That would be better, right? Because now I'm going to have a model that generalizes over time better. So here I'm just going to go ahead and go through each one of those features and drop each one at a time. Okay, retrain a new random forest and print out the score. Okay, so before we do any of that, our score was 0.88 for our validation versus 0.89 OOB. And you can see here, when I remove sales ID, my score goes up. And this is like what we're hoping for. We've removed a time-dependent variable. There were other variables that could find similar relationships without the time dependency. So removing it caused our validation to go up. Our OOB didn't go up, right? Because this is genuinely, statistically, a useful predictor, right? But it's a time-dependent one, and we have a time-dependent validation set. So this is really subtle, but it can be really important, right? It's trying to find the things that give you a generalizable time across time prediction, and here's how you can see it. So it's like, okay, we should remove sales ID for sure, right? But sale elapsed didn't get better. Okay, so we don't want that. Machine ID did get better. Went from 888 to 893. Right? So it's actually quite a bit better. Age got a bit better. Year made got worse. Sale day of year got a bit better. Okay, so now we can say, all right, let's get rid of the three where we know that getting rid of it actually made it better. Okay, and as a result, look at this. We're now up to 915. Okay, so we've got rid of three time-dependent things, and now, as expected, our validation is better than our OOB. Okay, so that was a super successful approach there, right? And so now we can check the feature importance. And let's go ahead and say, all right, that was pretty damn good. Let's now leave it for a while. So give it 160 trees, let it churn on it, and see how that goes. Okay, And so, as you can see, like we did all of our interpretation, all of our fine tuning, basically with smaller models, subsets, and at the end we ran the whole thing. It actually still only took 16 seconds. And so we've now got an RMSE of 0.21. Okay, so now we can check that against Kaggle. Again, unfortunately this older competition we're not allowed to enter anymore to see how we would have gone, so the best we can do is check whether it looks like we would have done well based on our validation set. So it should be in the right area, and yeah, based on that we would have come first. Okay, so I think this is an interesting series of steps, right? So you can go through the same series of steps in your Kaggle projects, and more importantly, your real-world projects. So one of the challenges is once you leave this learning environment, suddenly you're surrounded by people who they never have enough time. They always want you to be in a hurry. They're always telling you, do this and then do that. You need to find the time to step away, right, and go back, because this is a genuine real-world modeling process you can use. And it gives, when I say it gives world-class results, I mean it, right? Like this guy who won this, Listigos, sadly he's passed away, but he is the top Kaggle competitor of all time. Like he won, I believe, like dozens of competitions. So if we can get a score even within cooey of him, then we are doing really, really well. Okay, so let's take a 5-minute break, and we're going to come back and build our own random forest. I just wanted to clarify something quickly. Very good point during the break was going back to the change in R squared between here and here is not just due to the fact that we removed these three predictors. We also went reset RF samples, right? So to actually see the impact of just removing, we need to compare it to the final step earlier. So it's actually compared to 907. So removing those three things took us from 907 to 915. Okay, so I mean, and in the end, of course, what matters is our final model. But yeah, just to clarify. Okay. So some of you have asked me about writing your own random forests from scratch. I don't know if any of you have given it a try yet. My original plan here was to do it in real time, and then as I started to do it, I realized that that would have kind of been boring for you because I screw things up all the time. So instead, we might do more of like a walk through the code together. Just as an aside, this reminds me, talking about the exam, actually somebody asked on the forum about like what can you expect on the exam. The basic plan is to make it the exam be very similar to these notebooks. So it'll probably be a notebook that you have to, get a data set, create a model, train it, feature importance, whatever, right? And the plan is that it'll be open book, open internet. You can use whatever resources you like. So basically, if you're entering Kaggle competitions, the exam should be very straightforward. I also expect that there will be some pieces about like, here's a partially completed random forest or something, finish writing this step here, or here's a random forest, implement feature importance, or implement one of the things we've talked about. So it'll be, the exam will be much like what we do in class and what you're expected to be doing during the week. There won't be any define this or tell me the difference between this word and that word or whatever. There's not going to be any rote learning. It'll be entirely like, are you an effective machine learning practitioner? I.e., can you use the algorithms? Can you create an effective validation set? And can you create parts of the algorithm, implement them from scratch? So it'll be all about writing code, basically. So if you're not comfortable writing code to practice machine learning, then you should be practicing that all the time. If you are comfortable, you should be practicing that all the time also. Whatever you're doing, write code to implement to do machine learning. Okay. So I kind of have a particular way of writing code. And I'm not going to claim it's the only way of writing code, but it might be a little bit different to what you're used to, and hopefully you'll find it at least interesting. Implementing random forest algorithms is actually quite tricky, not because the code's tricky. Like, generally speaking, most random forest algorithms are pretty conceptually easy. Generally speaking, academic papers and books have a knack of making them look difficult, but they're not difficult conceptually. What's difficult is getting all the details right and knowing when you're right. And so, in other words, we need a good way of doing testing. So if we're going to re-implement something that already exists, so like say we wanted to create a random forest in some different framework, different language, different operating system, I would always start with something that does exist, right? So in this case, we're just going to do it as a learning exercise, writing a random forest in Python. So for testing, I'm going to compare it to an existing random forest implementation. Okay, so that's like critical. Anytime you're doing anything involving like non-trivial amounts of code in machine learning, knowing whether you've got it right or wrong is kind of the hardest bit. I always assume that I've screwed everything up at every step. And so I'm thinking like, okay, assuming that I screwed it up, how do I figure out that I screwed it up, right? And then much to my surprise, from time to time, I actually get something right, and then I can move on. Okay, but most of the time I get it wrong. So unfortunately with machine learning, there's a lot of ways you can get things wrong that don't give you an error. They just make your result like slightly less good. And so that's what you want to pick up. So given that I want to kind of compare it to an existing implementation, I'm going to use our existing data set, our existing validation set, and then to simplify things, I'm just going to use 2 columns to start with. So let's go ahead and start writing a random forest. So my way of writing nearly all code is top-down, just like my teaching. And so by top-down, I start by assuming that everything I want already exists, right? So in other words, the first thing I want to do, I'm going to call this a tree ensemble, right? So to create a random forest, the first question I have is, what do I need to pass in, right? What do I need to initialize my random forest? So I'm going to need some independent variables, some dependent variable, pick how many trees I want. I'm going to use the sample size parameter from the start here. So how big do you want each sample to be? And then maybe some optional parameter of what's the smallest leaf size. Okay. For testing, it's nice to use a constant random seed, so we'll get the same result each time. So this is just how you set a random seed. Okay. Maybe it's worth mentioning this for those of you that aren't familiar with it. Random number generators on computers aren't random at all. They're actually called pseudo-random number generators. And what they do is, given some initial starting point, in this case 42, a pseudo-random number generator is a mathematical function that generates a deterministic, always the same, sequence of numbers, such that those numbers are designed to be as uncorrelated with the previous number as possible, okay? And as unpredictable as possible. And as uncorrelated as possible with something with a different random seed. So the second number in the sequence starting with 42 should be very different to the second number starting with 41. And generally they involve kind of like taking, using big prime numbers and taking mods and stuff like that. It's kind of an interesting area of math. If you want real random numbers, the only way to do that is you can actually buy hardware called a hardware random number generator that will have inside them like a little bit of some radioactive substance and like something that detects how many things it's spitting out, or there'll be some hardware thing.
Getting current system time, is it a valid random number generation process?
So that would be maybe for a random seed, right? So this thing of like, what do we start the function with? So one of the really interesting areas is like in your computer, if you don't set the random seed, what is it set to? And yeah, quite often people use the current time for security. Like obviously we use a lot of random number stuff for security stuff. Like if you're generating an SSH key, it needs to be random. It turns out, like, people can figure out roughly when you created a key. Like, they could look at, like, oh, ID RSA has a timestamp, and they could try, all of the different nanoseconds starting points for a random number generator around that timestamp and figure out your key. So in practice, a lot of, like, really random, high randomness requiring applications actually have a step that say, please move your mouse and type random stuff at the keyboard for a while. And so it like gets you to be a source. It's called entropy, to be a source of entropy. Other approaches is they'll look at like, the hash of some of your log files or, stuff like that. It's a really, really fun area. So in our case, our purpose actually is to remove randomness. So we're saying, okay, generate a series of pseudo-random numbers starting with 42. So it always should be the same. So if you haven't done much stuff in Python OO, this is a basically standard idiom, at least, I write it this way, most people don't, but if you pass in like 1, 2, 3, 4, 5 things that you're going to want to keep inside this object, then you basically have to say self.x equals x, self.y equals y, self.sample equals sample, right? And so we can assign to a tuple from a tuple, so again, this is like my way of coding. Most people think this is horrible, but I prefer to be able to see everything at once. And so I know in my code, anytime I see something that looks like this, it's always all of the stuff in the method being set. If I did it a different way, then half the codes now come off the bottom of the page and you can't see it. So, all right. So that was the first thing I thought about was like, okay, to create a random forest, what information do you need? Then I'm going to need to store that information inside my object. And so then I need to create some trees, right? A random forest is something that has some trees. So I basically figured, okay, list comprehension to create a list of trees. How many trees do we have? Well, we've got n trees. That's what we asked for. So range n trees gives me the numbers from 0 up to n trees at -1. Okay. So if I create a list comprehension that loops through that range, calling create tree each time, I now have n trees. And now, so to write that, I didn't have to think at all. Like, that's all, like, obvious. And so I've kind of delayed the thinking to the point where it's like, well, wait, we don't have something to create a tree. Okay, no worries. But let's pretend we did. If we did, we've now created a random forest. Okay, we'd still need to, like, do a few things on top of that. For example, once we have it, we would need a predict function. So, okay, well, let's write a predict function. How do you predict in a random forest? Can somebody tell me, either based on their own understanding or based on this line of code, what would be like your 1 or 2 sentence answer? How do you make a prediction in a random forest? Pastor Spencer?
You would want to, over every tree for your, like the row that you're trying to predict on, average the values that each tree would produce for that.
Exactly,
that
good. And so, that's a summary of what this says, right? So for a particular row, right, or maybe this is a number of rows, go through each tree, calculate its prediction. So here is a list comprehension that is calculating the prediction for every tree for x. I don't know if x is one row or multiple rows, it doesn't matter, right? As long as tree.predict works on it. And then once you've got a list of things, a cool trick to know is you can pass numpy.mean, a regular non-numpy list, okay? And it'll take the mean. You just need to tell it axis equals 0, means average it across the lists, okay? So this is going to return the average of .predict for each tree. And so I find list comprehensions allow me to write the code in the way that my brain works. Like, you could take the words Spencer said and like translate them into this code, or you could take this code and translate them into words like the one Spencer said, right? And so when I write code, I want it to be as much like that as possible, right? I want it to be readable. And so hopefully you'll find, like when you look at the fast AI code and you're trying to understand, well, how did Jeremy do X? I try to write things in a way that you can read it and like kind of turn it into English in your head.
So if I see correctly, that predict method is recursive?
No, it's calling tree.predict, and we haven't written a tree yet. So self.trees is going to contain a tree object. So this is tree ensemble.predict, and inside the trees is a tree, not a tree ensemble. So this is calling tree.predict, not tree ensemble.predict. Good question. Okay. So we've nearly finished writing our random forest, haven't we? All we need to do now is write create tree, right? So based on this code here, or on your own understanding of how we create trees in a random forest, can somebody tell me, let's take a few seconds, have a read, have a think, and then I'm going to try and come up with a way of saying, how do you create a tree in a random forest? Okay, who wants to tell me? Anybody else? Okay, Tyler's got close to the mic.
You take you're essentially taking a random sample of the original data, and then you're just constructing a tree however that happens.
So construct a decision tree, like a non-random tree, from a random sample of the data. Okay, so again, like, we've delayed any actual thought process here. We've basically said, okay, we could pick some random IDs. This is a good trick to know. If you call np.random.permutation passing in an int, it'll give you back a randomly shuffled sequence from 0 to that int, right? And so then if you grab the first :n items of that, that's now a random subsample. So this is not doing bootstrapping. We're not doing sampling with replacement here, which I think is fine. You know, for my random forest, I'm deciding that it's going to be something where we do subsampling, not bootstrapping. Okay, so here's a good line of code to know how to write, because it comes up all the time. Like I find in machine learning, most algorithms I use are somewhat random, and so often I need some kind of random sample. Can you pass that, Tyler or Chenshi?
Won't that give you one extra? Because you said it'll go from 0 to length.
No. So this will give you, if len self.y is of size n, this will give you n. A sequence of length n, so 0 to n minus 1.
Okay.
And then from that, I'm picking out :self.sample size, so the first sample size IDs.
I have a comment on bootstrapping. I think this method is better because we have chance of giving more weights to each observation, or am I thinking wrong?
No, I mean, I think for bootstrapping, we could also give weights.
I mean, weighing single observations more than they are, like, without wanting that weight. Because when bootstrapping with replacement, we can have a single observation and duplicates of it in the same tree, which will give...
It does feel weird, but I think... I'm not sure that the actual theory or empirical results backs up our intuition that it's worse. It would be interesting to look back at that, actually. Personally, I prefer this because I feel like most of the time we have more data than we want to put in a tree at once. I feel like back when Bryman created random forests, it was 1999, it was kind of a very different world, you know, where we pretty much always wanted to use all the data we had. But nowadays, I would say that's generally not what we want. We normally have too much data. And so what people tend to do is they'll like fire up a Spark cluster and they'll run it on hundreds of machines, when it makes no sense, because if they had just used a subsample each time, they could have done it on one machine. And like the overhead of like Spark is a huge amount of I/O overhead. Like I know you guys are doing distributed computing now. If you've looked at some of the benchmarks, yeah, exactly. So if you do something on a single machine, it can often be hundreds of times faster because you don't have all this I/O overhead. It also tends to be easier to write the algorithms, like you can use like sklearn, easier to visualize, cheaper, so forth. So like I almost always avoid distributed computing, and I have my whole life. Like even 25 years ago when I was starting in machine learning, I still didn't use clusters, because I always feel like whatever I could do with a cluster now, I could do with a single machine in 5 years' time. So why don't I just focus on always being as good as possible with the single machine, and that's going to be more interactive and more iterative and work for me. So, okay, so again, we've like delayed thinking to the point where we have to write decision tree. And so hopefully you get an idea that this top-down approach, the goal is going to be that we're going to keep delaying thinking so long that we delay it forever. Like eventually we've somehow written the whole thing without actually having to think, right? And that's kind of what I need, because I'm kind of slow, right? So this is why I write code this way. And notice, like, you never have to design anything. You just say, hey, what if somebody already gave me the exact API I needed? How would I use it? Okay, and then okay, to implement that next stage, what would be the exact API I would need to implement that? Right? You keep going down until eventually you're like, oh, that already exists. Okay, so this assumes we've got a class called decision tree, so we're going to have to create that. So a decision tree is something, so we already know what we're going to have to pass it, because we just passed it, right? So we're passing in a random sample of x's, a random sample of y's, indexes is actually, so we know that down the track, so I've got to plan a tiny bit. We know that a decision tree is going to contain decision trees, which themselves contain decision trees. And so as we go down the decision tree, there's going to be some subset of the original data that we've kind of got. And so I'm going to pass in the indexes of the data that we're actually going to use here. Okay, so initially it's the entire random sample, right? So I've got the whole, I've got the whole range, and I turn that into an array. So that's 0, the indexes from 0 to the size of the sample. And then we'll just pass down the min leaf size. So everything that we got for constructing the random forest, we're going to pass down to the decision tree, except of course num trees, which is irrelevant for the decision tree. So again, now that we know that's the information we need, we can go ahead and store it inside this object. So I'm pretty likely to need to know how many rows we have in this tree, which I generally call n. How many columns do I have, which I generally call C. So the number of rows is just equal to the number of indexes we were given, and the number of columns is just like however many columns there are in our independent variables. So then we're going to need this value here. We need to know for this tree, what's its prediction, right? So the prediction for this tree is the mean of our dependent variable for those indexes, which are inside this part of the tree, right? So at the very top of the tree, it contains all the indexes, right? I'm assuming that by the time we've got to this point, remember, we've already done the random sampling, right? So when we're talking about indexes, we're not talking about the random sampling to create the tree. We're assuming this tree now has some random sample. Inside decision tree, this is one of the nice things, right? Inside decision tree, the whole random sampling thing's gone, right? That was done by the random forest, right? So at this point, we're building something that's just a plain old decision tree. It's not in any way a random sampling anything. It's just a plain old decision tree, right? So the indexes is literally like which subset of the data have we got to so far in this tree. And so at the top of the decision tree, it's all the data, right? So it's all of the indexes, okay? So all of the indexes, so this is therefore all of the dependent variable that are in this part of the tree, and so this is the value, mean of that. Does that make sense? Anybody got any questions about that? So, yes, can you pass it to Chen-Shi?
Actually, just to let you know that a large portion of us don't have a OOP experience.
Okay,
Yeah,
sure.
just to let you
So, so a quick OOP primer would be helpful. Great. Yeah. Okay. Who has done object-oriented programming in some programming language? Okay. So you've all used actually lots of object-oriented programming in terms of using existing classes, right? So every time we've created a random forest, we've called the random forest's constructor, and it's returned an object, and then we've called methods and attributes on that object. So fit is a method. You can tell because it's got parentheses after it, right? Or else, yeah, OLB score is a property or an attribute, doesn't have parentheses after it. Okay, so inside an object there are kind of two kinds of things. They're the functions that you can call. So you have object dot function parenthesis arguments, or there are the properties or attributes you can grab, which is object dot and then just the attribute name with no parentheses. So when and then the other thing that we do with objects is we create them. Okay, we pass in the name of the class and it returns us the object, and you have to tell it all of the parameters necessary to get constructed. So let's just copy this code. And see how we're going to go ahead and build this. So the first step is we're not going to go m equals random forest regressor. We're going to go m equals tree ensemble. We're creating a class called tree ensemble. And we're going to pass in various bits of information. Okay. So maybe we'll have 10 trees, sample size of 1,000, maybe a min leaf of 3, right? And you can always choose to name your arguments or not. So when you've got quite a few, it's kind of nice to name them so that just so we can see what each one means. It's always optional, right? So we're going to try and create a class that we can use like this. And then I'm not sure we're going to bother with .fit because we've passed in the x and the y. Right, like in scikit-learn, they use an approach where first of all you construct something without telling it what data to use, and then you pass in the data. We're doing these two steps at once. We're actually passing in the data, right? And so then after that, we're going to be going m dot, so we're going to go preds equals m dot predict, passing in maybe some validation set. Okay, so that's the API we're kind of creating here. So this thing here is called a constructor. Something that creates an object is called a constructor. And Python, there's a lot of ugly, hideous things about Python, one of which is it uses these special magic method names. Underscore, underscore, init, underscore, underscore is a special magic method that's called when you try to construct a class. So when I call tree ensemble, parenthesis, it actually calls tree ensemble dot, people say dunder init. I kind of hate it, but anyway, dunder init. Double underscore init, double underscore, dunder init. So that's why we've got this method called dunder init. Okay, so when I call tree ensemble, it's going to call this method. Another hideously ugly thing about Python's OO is that there's this special thing where if you have a class, and to create a class, you just write class in the name of the class. All of its methods automatically get sent one extra parameter, one extra argument. which is the first argument. And you can call it anything you like. If you call it anything other than self, everybody will hate you and you're a bad person. Okay? So call it anything you like, as long as it's self. Okay. So that's why you always see this. And in fact, I can immediately see here, I have a bug. Anybody see the bug in my predict function? I should have self, right? I always do it, right? So anytime you try and call a method on your own class and you get something saying you passed in 2 parameters and it was only expecting 1, you forgot self. Okay? So this is a really dumb way to add OOP to a programming language, but the older languages like Python often did this because they kind of needed to, they started out not being OO and then they kind of added OO in a way that was hideously ugly. So Perl, which predates Python by a little bit, kind of, I think, really came up with this approach, and unfortunately other languages of that era stuck with it. So you have to add in this magic self. So the magic self now, when you're inside this class, you can now pretend as if any property name you like exists. So I can now pretend there's something called self.x. I can read from it, I can write to it, right? But if I read from it and I haven't yet written to it, I'll get an error. So the stuff that's passed to the constructor gets thrown away by default. Like there's nothing that says you need to, this class needs to remember what these things are. But anything that we stick inside self is remembered for all time. You know, as long as this object exists, you can access it, it's remembered. So now that I've gone, in fact, let's do this, right? So let's create the tree ensemble class. And let's now instantiate it. Okay. Of course, we haven't got x. We need to call x train, y train. Okay, decision tree is not defined. So let's create a really minimal decision tree. There we go. Okay, so here is enough to actually instantiate our tree ensemble. Okay, so we've defined the init for it. We've defined the init for decision tree. We need decision trees init to be defined because inside our ensemble init, it called self.createTree, and then self.createTree called the decision tree constructor, and then decision tree constructor basically does nothing at all other than save some information, right? So at this point, we can now go m dot, oh, sorry. Okay, and if I press tab at this point, can anybody tell me what I would expect to see? Pass it to Taylor. Chenshi, could you pass that to Taylor?
We would see a drop down of all available methods for that class.
Okay, which would be?
In this case, so if M is a tree ensemble, we would have create tree and predict.
Okay. Anything else?
What? Oh yeah, and as well as Ernest whispered, the variables.
As well, yeah. So the variable could mean a lot of things. We'll say the attributes. Yes. So the things that we put inside self. So if I hit tab, right there they are. Right, as Taylor said, there's create tree, there's predict, and then there's everything else we put inside self. Right. So if I look at m dot min leaf, if I hit shift enter, what will I see? Yeah, the number that I just put there, I put min leaf is 3, so that went up here to min leaf. This here is a default argument, so it says if I don't pass anything, it'll be 5, but I did pass something, right? So it's 3. Self.min leaf here is going to be equal to min leaf here. Okay? So something which, because of this rather annoying way of doing OO, it does mean that it's very easy to accidentally forget to do that, right? So if I don't assign it to self.minleaf, right, then I get an error. And so here, tree ensemble doesn't have a minleaf, right? So how do I create that attribute? I just put something in it. Okay, so if you want to, if you don't know what a value of it should be yet, but you kind of need to be able to refer to it, you can always go self.minleaf equals none, right? So at least it's something you can read, check for noneness, and not have an error. Okay. Great. Now, interestingly, I was able to instantiate tree ensemble, even though predict refers to a method of decision tree that doesn't exist. And this is actually something very nice about the dynamic nature of Python, is that because it's not like compiling it, it's not checking anything unless you're using it, right? So we can go ahead and create decision_d.predict later, and then our instantiated object will magically start working, right? It doesn't actually look up that method's details until you use it. And so it really helps with top-down programming. Okay, so when you're inside a class definition, in other words, you're at that indentation level, indented one in, so these are all class definitions. Any function that you create, unless you do some special things that we're not going to talk about yet, is automatically a method of that class. And so every method of that class magically gets a self passed to it. So we could call, since we've got a tree ensemble, we could call m.createTree, and we don't put anything inside those parentheses because the magic self will be passed. And the magic self will be whatever m is. Okay, so m.createTree returns a decision tree, just like we asked it to, right? So m.createTree.idxs will give us the self.idxs inside the decision tree. Okay, which is set to np.arrange range self.sample size. Okay. Why, as data scientists, do we care about object-oriented programming? Because a lot of the stuff you use is going to require you to implement stuff with OOP. For example, every single PyTorch model of any kind is created with OOP. It's the only way to create PyTorch models. Good news is what you see here is the entirety of what you need to know. So this is all you need to know. You need to know to create something called init, to assign the things that are passed to init to something called self, and then to stick the word self after each of your methods. Okay? And so the nice thing is, like now, to think as an OOP programmer is to realize you don't now have to pass around x, y, sample size, and min leaf to every function that uses them. By assigning them to attributes of self, they're now available like magic. Right? So this is why OOP is super handy. If you're particularly, I started trying to create a decision tree initially without using OOP and try to keep track of what that decision tree was meant to know about. It was very difficult, whereas with OOP, you can just say inside the decision tree, self.indexes equals this, and everything just works. Okay, that's great. So we're out of time. I think that's great timing because there's an introduction to OOP, but this week, next class, I'm going to assume that you can use it, right? So you should create some classes, instantiate some classes, look at their methods and properties, have them call each other and so forth until you feel comfortable with them. And maybe for those of you that haven't done OOP before and find some other useful resources, you could pop them onto the wiki thread so that other people know what you find useful. Great. Thanks, everybody. So we've looked at a lot of different random forest interpretation techniques. And a question that's come up a little bit on the forums is what are these for, really? How do these help me get a better score on Kaggle? And my answer's kind of been they don't necessarily. And so I want to talk more about why do we do machine learning? What's the point? And to answer this question, I'm going to put this PowerPoint in the GitHub repo so you can have a look. I want to show you something really important, which is examples of how people have used machine learning, mainly in business, because that's where most of you are probably going to end up after this, is working for some company. I'm going to show you applications of machine learning which are either based on things that I've been personally involved in myself or know of people who are doing them directly. So none of these are going to be like hypotheticals. These are all actual things that people are doing and I've got direct or secondhand knowledge of. I'm going to split them into two groups, horizontal and vertical. So in business, horizontal means something that you do like across different kinds of business, whereas vertical means it's something that you do within a business or within a supply chain or within a process. So in other words, an example of horizontal applications is everything involving marketing. So like every company pretty much has to try to sell more products to its customers, and so therefore does marketing. And so each of these boxes are examples of some of the things that people are using machine learning for in marketing. So let's take an example, right? Let's take churn. Okay, so churn refers to a model which attempts to predict who's going to leave. Right? So I've done some churn modeling fairly recently in telecommunications. And so we're trying to figure out for this big cell phone company which customers are going to leave. That is not of itself that interesting. Like building a highly predictive model that says Jeremy Howard is almost certainly going to leave next month is probably not that helpful, because like if I'm almost certainly going to leave next month, there's probably nothing you can do about it, right? It's too late. It's going to cost you too much to keep me. Right? So in order to understand, like, well, why would we do churn modeling? I've got a little framework that you might find helpful. So if you Google for Jeremy Howard data products, I think I've mentioned this thing before. There's a paper you can find, Designing Great Data Products, that I wrote with a couple of colleagues a few years ago. And in it, I describe my experience of actually turning machine learning models into like stuff that makes money, right? And the basic trick is this thing I call the drivetrain approach, which is these 4 steps. The starting point to actually turn a machine learning project into something that's actually useful is to know, what am I trying to achieve? And that doesn't mean like I'm trying to achieve a high area under the ROC curve, or I'm trying to achieve a large difference between classes. No, it would be I'm trying to sell more books, or I'm trying to reduce the number of customers that leave next month, or I'm trying to detect lung cancer earlier. Right? These are objectives. So the objective is something that absolutely directly is the thing that the company or the organization actually wants. No company or organization lives in order to create a more accurate predictive model. Right? There's some reason. Right? So that's your objective. Now that's obviously the most important thing. If you don't know the purpose of what you're modeling for, then you can't possibly do a good job of it. And hopefully people are starting to, pick that up in out there in the world of data science. But interestingly, what very few people are talking about, but it's just as important, is the next thing, which is levers. A lever is a thing that the organization can do to actually drive the objective. So let's take the example of churn modeling, right? What is a lever that an organization could use to reduce the number of customers that are leaving?
They could take a closer look at the model and do some of this random forest interpretation and see some of the causes that are causing people to leave and potentially change those issues in the company.
Okay, so that's a data scientist's answer. But I want you to go to the next level. What are the things? The levers are the things they can do. Do you want to pass it behind you? What are the things that they can do?
Just outreach, like calling or sending emails.
They could call someone and say, like, are you happy? Anything we could do? Okay.
They can provide incentives to increase engagement with the product.
Yeah, so they could like give them a free pen or something if they, buy $20 worth of product next month. Yep. You are going to do that as well? Okay, so you guys are the giving out carrots rather than the handing out sticks. Do you want to send it over in a couple of goes?
Actually change the price of the product or the subscription, or
yeah, you could give them a special. All right. So these are levers, right? And so whenever you're working as a data scientist, keep coming back and thinking, what are we trying to achieve? We being the organization, and how are we trying to achieve it? Being like, what are the actual things we can do to make that objective happen? So building a model is never ever a lever. Okay, but it could help you with the lever. So then the next step is, what data does the organization have that could possibly help them to set that lever to achieve that objective, right? And so this is not what data did they give you when you started the project, right? But like think about it from a first principles point of view. Okay, I'm working for a telecommunications company. They gave me some certain set of data, but I'm sure they must know where their customers live, how many phone calls they made last month, how many times they called customer service, whatever. And so have a think about okay, if we're trying to decide who should we reduce give a special offer to proactively, then we want to figure out what information do we have that might help us to identify who's going to react well or badly to that. Perhaps more interestingly would be, what if we were doing a fraud algorithm, right? And so we're trying to figure out who's going to not pay for the phone that they take out of the store. They're on some 12-month payment plan. We never see them again. Now, in that case, the data we have available, it doesn't matter what's in the database. What matters is what's the data that we can get when the customer is in the shop, right? So there's often constraints around the data that we can actually use. So we need to know, what am I trying to achieve? What can this organization actually do specifically to change that outcome? And at the point that that decision is being made, what data do they have or could they collect, right? And so then the way I put that all together is with a model. And this is not a model in the sense of a predictive model, but it's a model in the sense of a simulation model. So one of the main examples I give in this paper is one I spent many years building, which is if an insurance company changes their prices, how does that impact their profitability, right? And so generally your simulation model contains a number of predictive models. So I had, for example, a predictive model called an elasticity model that said for a specific customer, if we charge them a specific price for a specific product, what's the probability that they would say yes, both when it's new business and then a year later, what's the probability that they'd renew? And then there's another predictive model, which is what's the probability that they're going to make a claim and how much is that claim going to be, right? And so you can combine these models together then to say, all right, if we changed our pricing by reducing it by 10% for everybody between 18 and 25, and we can run it through these models that combine together into a simulation, then the overall impact on our market share in 10 years' time is X, and our cost is Y, and our profit is Z, and so forth, right? So in practice, most of the time, you really are going to care more about kind of the results of that simulation than you do about the predictive model directly. But most people are not doing this effectively at the moment. So for example, when I go to Amazon, right, I read all of Douglas Adams's books, right? And so having read all of Douglas Adams's books, the next time I went to Amazon, they said, would you like to buy the collected works of Douglas Adams? This is after I had bought every one of his books. So like from a machine learning point of view, some data scientist had said, oh, people that buy one of Douglas Adams's books often go on to buy the collected works, right? But recommending to me that I buy the collected works of Douglas Adams isn't smart, right? And it's actually not smart at a number of levels. Like, not only is it unlikely I'm going to buy a box set of something of which I have every one individually, but furthermore, it's not going to change my buying behavior. Like, I already know about Douglas Adams. I already know I like him. So taking up your valuable web space to tell me, hey, maybe you should buy more of the author who you're already familiar with and have bought lots of times, isn't actually going to change my behavior, right? So what if instead of creating a predictive model, Amazon had built an optimization model that said, like, that could simulate and said, if we show Jeremy this ad, how likely is he then to go on to buy this book? And if I don't show him this ad, how likely is he to go on to buy this book? And so that's the counterfactual, right? The counterfactual is what would have happened otherwise. And then you can take the difference and say, okay, what should we recommend him that is going to maximally change his behavior? So maximally result in more books. And so you'd probably say like, oh, he's never bought any Terry Pratchett books. He probably doesn't know about Terry Pratchett, but like lots of people that liked Douglas Adams did turn out to like Terry Pratchett, so let's like introduce him to a new author, right? So it's the difference between a predictive model on the one hand versus an optimization model on the other hand. So the two tend to go hand in hand, right? The optimization model basically is saying, well, first of all, you have a simulation model, right? The simulation model is saying, in a world where we put Terry Pratchett's book on the front page of Amazon for Jeremy Howard, this is what would have happened. He would have bought it with a 94% probability, right? And so that then tells us with this lever of like, what do I put on my homepage for Jeremy today? We say, okay, of all the different settings of that lever, the put Terry Pratchett on the homepage has the highest simulated outcome, right? And then that's the thing which maximizes our profit from Jeremy's visit to Amazon.com today, okay? So generally speaking, your predictive models kind of feed in to this simulation model, but you've kind of got to think about like, how do they all work together? So for example, let's go back to churn, right? So I'd turn out that Jeremy Howard is very likely to leave his cell phone company next month. What are we going to do about it? Oh, let's call him, right? And I can tell you, if my cell phone company calls me right now and says, just calling to say we love you, I'd be like, I'm canceling right now. like that would be a terrible idea. So again, you would want a simulation model that says like, what's the probability that Jeremy is going to change his behavior as a result of calling him right now, right? So one of the levers I have is call him. On the other hand, if I like got a piece of mail tomorrow that said like, for each month you stay with us, we're going to give you $100,000. Okay, then that's going to definitely change my behavior, right? But then feeding that into the simulation model, it turns out that overall that would be an unprofitable choice to make. So do you see how all this fits in together, right? So when we look at something like churn, we want to be thinking like, what are the levers we can pull, right? And so what are the kind of models that we could build with what kinds of data to help us pull those levers better to achieve our objectives? And so when you think about it that way, you realize that the vast majority of these applications are not largely about a predictive model at all. They're about interpretation. They're about understanding what happens if, right? So if we kind of take the the intersection between, on the one hand, here are all the levers that we could pull, like here are all the things we can do, and then here are all of the features from our random forest feature importance that turn out to be strong drivers of the outcome. And so then the intersection of those is, here are the levers we could pull that actually matter, right? Because if you can't change the thing, then it's not very interesting. And if it's not actually a significant driver, it's not very interesting, right? So we can actually use our random forest feature importance to tell us what can we actually do to make a difference. And then we can use the partial dependence to actually build this kind of simulation model to say like, okay, well, if we did change that, what would happen, right? So, you know, there are examples, lots and lots of these vertical examples. And so what I want you to kind of think about as you think about the machine learning problems you're working on is like, why does somebody care about this, right? And like, what would a good answer to them look like? And how could you, you know, how could you actually positively impact this business? So if you're creating like a Kaggle kernel, you know, try to think about from the point of view of the competition organizer. Like, what would they want to know? And how can you give them that information? So something like fraud detection, on the other hand, you probably just basically want to know who's fraudulent, right? So you probably do just care about the predictive model. But then you do have to think carefully about the data availability here. So it's like, okay, but we need to know who's fraudulent at the point that we're about to deliver them a product. Right? So it's no point like looking at data that's available like a month later, for instance. So you've kind of got this key issue of thinking about, you know, the actual operational constraints that you're working under. You know, lots of interesting applications in human resources, but like employee churn, it's another kind of churn model. We're finding out that Jeremy Howard's sick of lecturing, he's going to leave tomorrow, what are you going to do about it? Well, knowing that wouldn't actually be helpful. It'd be too late, right? You would actually want a model that said, what kinds of people, you know, are leaving USF? And it turns out that like, oh, everybody that goes to the downstairs cafe leaves USF, you know, I guess their food is awful, or, you know, whatever, right? Or everybody that we're paying less than $500,000 a year is leaving USF, you know, because they can't afford basic housing in San Francisco. So like you could use your employee churn model, not so much to say like which employees hate us, but why do employees leave, right? And so again, it's really the interpretation there that matters. You know, lead prioritization is a really interesting one, right? Like this is one where a lot of companies, yes, Dina, can you pass that over there?
Yeah, so I was just wondering, so like for the churn thing, you suggested so one way is like pay an employee like 1 million a year or something. But then it sounds like there are two predictors that you need to predict for. I mean, one the churn and one you need to optimize for like your profit thing. So how does it work in that?
Yeah, exactly. So this is what this like simulation model is all about. So it's a great question. So like you kind of figure out this objective we're trying to maximize, which is like company profitability. You can kind of create like a pretty simple like Excel model or something that says like here's the revenues and here's the costs, and the cost is equal to the, you know, number of people we employ multiplied by their salaries, blah, 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 right? And so inside that kind of Excel model, there are certain cells, there are certain inputs where you're like, oh, that thing's kind of stochastic, you know, or that thing is kind of uncertain, but we could predict it with a model. And so that's kind of what I do then, is I then say, okay, we need a predictive model for how likely somebody is to stay if we change their salary, how likely they are to leave, you know, with their current salary, how likely they are to leave next year if I increase their salary now, blah, blah, blah. So you kind of build a bunch of these models, and then you combine them together with simple business logic, and then you can optimize that. You can then say, okay, if I, you know, pay Jeremy Howard $500,000, that's probably a really good idea, you know, and if I pay him less, then, you know, it's probably not, or whatever. Like you can figure out the overall impact. And so it's really shocking to me how few people do this. Like most people in industry measure their models using like AUC or RMSE or whatever, which is never actually what you want. Yes, can you pass it over here?
I wanted to stress a point that you made before. In my experience, a lot of the problem was to define the problem, right? So you are in a company, you're talking to somebody that doesn't have like this mentality that you have. They don't know that you have to have X and Y and so on. So you have to try to get that out of them. You know, what exactly do you want? And try to go through a few iterations of understanding what they want, and then you know the data, you know what the data is, you know actually where you can measure, which is often know what they want, so you have to kind of get a proxy for what they want. And then, so a lot of what you do is not that much of like, well, some people do actually just work on really good models for, you know, but a lot of people also just work on this kind of how do you put this as a, you know, classification, regression, or some other type of modeling. That's actually kind of the most interesting, I think, and also kind of what you have to do well, I think.
Yeah, the best people do both. You know, the best people understand the technical model building deeply, but also understand the kind of strategic context deeply. And so this is one way to think about it. And as I say, like, you know, I actually think, you know, there aren't many articles I wrote in 2012 I'm still recommending, but this one I think is still equally valid today. So yeah, so like another great example is lead prioritization, right? So like a lot of companies, like every one of these boxes I'm showing, you can generally find a company or many companies whose sole job in life is to build models of that thing, right? So there are lots of companies that sell lead prioritization systems. But again, like the question is, how would we use that information, right? So if it's like, oh, our best lead is Jeremy, you know, he's our highest probability of buying. Does that mean I should send a salesperson out to Jeremy or I shouldn't? Like if he's highly probable to buy, why waste my time with him? You know? So like, again, it's like you really want some kind of simulation that says like, what's the likely change in Jeremy's behavior if I send my best salesperson, Yanette, out to go and like encourage him to sign. Okay. So yeah, I think this is like, there are many, many opportunities for data scientists in the world today to move beyond predictive modeling to actually bringing it all together, you know, with the kind of stuff that Dina was talking about in her question. So, as well as these horizontal applications that basically apply to like every company, there's a whole bunch of applications that are specific to like every part of the world, right? So for those of you that end up in healthcare, some of you will become experts in one or more of these areas, like readmission risk. Okay, so what's the probability that this patient is going to come back to the hospital? And readmission is, depending on the details of the jurisdiction and so forth, it can be a disaster for hospitals when somebody is readmitted, right? So if you find out that this patient has a high probability of readmission, what do you do about it? Well, again, the predictive model is helpful of itself, right? It rather suggests like we just shouldn't send them home yet because they're going to come back. But wouldn't it be nice if we had the tree interpreter and it said to us the reason that they're at high risk is because we don't have a recent EKG for them, and without a recent EKG, we can't have a high confidence about their, you know, cardiac health. In which case, it wouldn't be like, well, let's keep them in the hospital for 2 weeks. It'll be like, let's give them an EKG. Okay? So there's this interaction between interpretation and predictive accuracy. Okay?
So correct me if I'm wrong, but what I'm understanding you saying is that the predictive models are a really great starting point, but in order to actually like answer these questions, we really need to focus on the interpretability of these models.
Yeah, I think so. And more specifically, I'm saying like we just learned a whole raft of random forest interpretation techniques, and so I'm kind of trying to justify like, well, why, right? And so the reason why is because actually, maybe I'd say most of the time, the interpretation is the thing we care about. And like, you can create a chart, you know, or a table without machine learning. And indeed, that's how most of the world works, right? Most managers like build all kinds of tables and charts without any machine learning behind them. But they often make terrible decisions because like, they don't know the feature importance of the objective they're interested in. So the table they create is of things that actually are the least important things anyway. Or they just do a univariate chart rather than a partial dependence plot, so they don't actually realize that the relationship they thought they're looking at is due entirely to something else, right? So, you know, I'm kind of arguing for data scientists getting like much more deeply involved in strategy and in trying to use machine learning to really help, you know, help a business with all of its objectives, right? You know, there are companies like dunnhumby is a huge company that does nothing but retail applications with machine learning. And so like, I believe there's like a dunnhumby product you can buy which will help you figure out like, if I put my new store in this location versus that location, how much, you know, how many people are going to shop there. Or if I put like, you know, my diapers in this part of the shop versus that part of the shop, how's that going to impact, you know, purchasing behavior or whatever, right? So I think it's also good to realize that like the subset of machine learning applications you tend to hear about, you know, in the tech press or whatever is this massively biased tiny subset of stuff which kind of Google and Facebook do. Whereas the vast majority of stuff that actually makes the world go round is, you know, these kinds of applications that actually help people make things, buy things, sell things, build things, so forth.
So about tree interpretation, the way we looked at the tree was we manually checked which feature could cause was more important for particular observation. But for businesses, they would have huge amount of data and they want this interpretation for a lot of observations. So how do they automate it?
I don't think the automation's at all difficult. Like you can run any of these algorithms like looping through the rows or doing them in parallel. It's all just code. Am I misunderstanding your question?
Is it like they set a threshold that if some feature is above, like for different people will have different behavior?
So yeah, okay, I get it. It's a good question. The important thing, this is a really important issue actually, is the vast majority of machine learning models don't automate anything. They're designed to provide information to humans, right? So for example, if you're a point of sales, you know, customer service phone operator for an insurance company, and your customer asks you, why is my renewal $500 more expensive than last time? Then hopefully, you know, the insurance company provides in your terminal a little screen that shows the result of the tree interpreter or whatever, and so that you can jump there and tell the customer like, okay, well, here's last year, you're in this different zip code, which, you know, is less, has lower amounts of car theft, and this year also you've actually changed your vehicle to a more expensive one or whatever, right? So it's not so much about thresholds and automation, but about, you know, making these model outputs available to the decision makers in an organization, whether they be at the top strategic level of like, you know, are we going to shut down this whole product or not, all the way to the operational level of like that individual discussion with a customer. So like another example is like aircraft scheduling and gate management. Like there's lots of companies that do that, right? And basically what happens is that the people, you know, there are people in out of the airport whose job it is to basically tell each aircraft what gate to go to figure out when to close the doors, stuff like that. And so the idea is, you know, you're giving them software which has the information they need to make good decisions. So the machine learning models end up embedded in that software to kind of say like, okay, that plane that's currently coming in from Miami, there's a 48% chance that it's going to be over 5 minutes late. And if it does, then this is going to be the knock-on impact through the rest of the terminal, for instance. Okay, so that's kind of how these things tend to fit together. So there's so many of these, right? There's lots and lots. And so it's not like, I don't expect you to like remember all these applications, but what I do want you to do is to like spend some time like thinking about them. Like sit down with one of your friends and like talk about a few examples of like, okay, how would we go about like doing failure analysis in manufacturing? I don't know, like, you know, who would be doing that? Why would be they doing it? What kind of models might they use? What kind of data might they use? Like start to like kind of practice this and get a sense. So, because then as you're like interviewing, and then when you're at the workplace and you're talking to managers, you want to be like straight away able to kind of recognize that the person you're talking to, what do they try to achieve? What are the levers that they have to pull, right? What is the data they have available to pull those levers to achieve that thing? And therefore, how could we build models to help them do that? And what kind of predictions would they have to be making, right? And so then you can have this really thoughtful, empathetic conversation with those people, kind of saying like, hey, you know, in order to reduce the number of customers that are leaving, you know, I guess you're trying to figure out like, you know, who should you be providing better pricing to or whatever, and so forth.
So what I'm noticing, like from your beautiful little chart above, is that like a lot of this, to me at least, still seems like the primary purpose is like at least base level, like is predictive power. And so I guess my thing is like for explanatory problems, like a lot of the ones that people are faced with like in social sciences, is that something machine learning can be used for or is used for, or is that not really the realm that it is?
Yeah, it's a great question. And I've had a lot of conversations about this with people in social sciences. And currently, machine learning is not well applied in like economics or psychology or whatever on the whole. But I'm convinced it can be for the exact reasons we're talking about. So if you're trying to figure out like, if you're trying to do some kind of behavioral economics and you're trying to understand like why some people behave differently to other people, you know, a random forest with a feature importance plot would be a great way to start. Or like more interestingly, if you're trying to do some kind of sociology experiment or analysis based on a large social network data set where you have an observational study, you really want to try and pull out all of the sources of kind of exogenous variables, you know, all the stuff that's going on outside. And so if you use a partial dependence plot with a random forest, that happens automatically. So I actually gave a talk at MIT a couple of years ago for the first conference on digital experimentation, which was really talking about like, how do we experiment in, you know, things like social networks and kind of these digital environments. And yeah, economists all do things with like, you know, classic statistical tests. But the group of yeah. So, but anyway, in this case, the economists I talked to were absolutely fascinated by this, and they actually asked me to give a introduction to machine learning session at MIT to these various faculty and graduate folks in the economics department. And so, and some of those folks have gone on to be, you know, write some pretty famous books and stuff, and so hopefully it's been useful. So, like, it's definitely early days, but it's a big opportunity. But as Yannette says, it's, you know, there's plenty of skepticism still out there. All right. Huh? Well, the skepticism comes from unfamiliarity, basically, with like this totally different approach. So, like, if you've spent 20 years studying econometrics and somebody comes along and says, here's a totally different approach to all the all the stuff that econometricians do, naturally your first reaction will be like, prove it, So that's fair enough. But I think it's, over time, the next generation of people who are growing up with machine learning, some of them will move into the social sciences. They'll make huge impacts that nobody's ever managed to make before, and people will start going, wow. Just like happened in computer vision, right? When, computer vision spent a long time of people saying like, hey, maybe you should use deep learning for computer vision, and everybody in computer vision is like, prove it. We have decades of work on amazing feature detectors for computer vision. And then finally in 2012, Hinton and Krajewski came along and said, okay, our model's like twice as good as yours. And, we've only just started on this. And everybody was like, oh, okay, that's pretty convincing. And nowadays, every computer vision researcher basically uses deep learning. So I think that time will come in this area too. Okay, I think what we might do then is take a break, and we're going to come back and talk about these random forest interpretation techniques and do a bit of a review. So let's come back at 2 o'clock. So let's have a go at talking about these different random forest interpretation methods, having talked about like why they're important. So let's now remind ourselves like what they are. So I'm going to let you folks have a go. So let's start with confidence based on tree variance. So can one of you tell me one or more of the following things about confidence based on tree variance? What does it tell us? Why would we be interested in that? And how is it calculated? This is going back a ways because it was the first one we looked at. Even if you're not sure, or you only know a little piece of it, give us your piece and we'll build on it together.
Yeah, I think I got a piece of it. It's getting the variance of our predictions from random forests.
That's true. That's the how. Can you be more specific? So what is it, the variance of?
I think it's, if I'm remembering correctly, I think it's just the overall prediction.
The variance of the predictions of the trees, yes. So normally the prediction is just the average. This is the variance of the trees.
And so it kind of just gives you an idea of how much your prediction is going to vary. So if maybe you want to minimize variance, maybe that's your goal for whatever reason that could be.
That's not so much the reason. So I like your calculation description. Let's see if somebody else can tell us how you might use that. It's okay if you're not sure. Yeah, have a start.
So I remember that we talked about kind of the independence of the trees, and so maybe something about if the variance of the trees is high or low, then
No, not so much that. That's an interesting question, but it's not what we're going to see here. Do you want to pass it back behind you? So to remind you, just to fill in a detail here, what we generally do here is we take just one row, like one observation often, and like find out how confident we are about that, like how much variance there are in the trees for that. Or we can do it as we did here for different groups.
According to me, the idea is like for each row, we calculate the standard deviation that we get from the random forest model, and then maybe group according to different variables or predictors and see for which particular predictor the standard deviation is high, and then go deep down as why it is happening. Maybe it is because a particular category of that variable has very less number of observations.
Yeah, that's great. So that would be one approach. Is kind of what we've done here is to say, like, is there any groups that have where we're very unconfident? Something that I think is even more important would be when you're using this like operationally, right? Let's say you're doing a credit decisioning algorithm. So we're trying to say like, okay, is Jeremy a good risk or a bad risk? Should we loan him $1 million? And the random forest says, I think he's a good risk, but I'm not at all confident. In which case we might say, okay, maybe I shouldn't give him $1 million. Whereas if the random forest said, I think he's a good risk, I am very sure of that, then we're much more comfortable giving him $1 million, right? And I'm a very good risk, so feel free to give me $1 million, right? I checked the random forest before, a different notebook, not in the repo. So like this is like, it's quite hard for me to give you folks direct experience with this kind of like single observation interpretation stuff, because it's really like the kind of stuff that you actually need to be putting out to the front line. Do you know what I mean? Like it's not something which you can really use so much in a kind of Kaggle context, but it's more like, okay, if you're actually putting out some algorithm which is making like big decisions that could cost a lot of money, you probably don't so much care about the average prediction of the random forest, but maybe you actually care about like the average minus a couple of standard deviations. You know, like what's the kind of worst case prediction? And so, as Shikha mentioned, it's like maybe there's a whole group that we're kind of unconfident about. So yeah, so that's confidence based on tree variance. All right. Who wants to have a go at answering feature importance? What is it? Why is it interesting? How do we calculate it? Or any subset thereof? Dina.
I think it's like it's basically to find out which features are important for your model. So you take each feature and you like randomly sample all the values in the feature and you see how the predictions are. If it's very different, it means that that feature was actually important. Else, if it's fine to take any random values for that feature, it means that probably it's not very important.
Okay, that was terrific. There's this. That was all exactly right. There was some details that maybe were skimmed over a little bit. I wonder if anybody else wants to jump into like a more detailed description of how it's calculated. Because I know this morning some people were not quite sure. Is there anybody who's like not quite sure, maybe who wants to like have a go? Or want to just put it next to you there? Let's see. How exactly do we calculate feature importance for a particular feature?
So I think after you're done building the random forest model, you take each column and randomly shuffle it and generate a prediction and check the validation score. If it gets pretty bad for after shuffling one of the columns, that means that column was important. So that has higher importance. I'm not exactly sure how we quantify the feature importance.
Okay, great. Dina, do you know how we quantify the feature importance? That was a great description.
I think we take the difference in the R-square.
Or score of some sort, exactly. Yeah, so let's say we've got our dependent variable, which is price, right? And there's a bunch of independent variables, including year made, right? And so we basically, we use the whole lot to build a random forest, right? And then that gives us our predictions, right? And so then we can, let's call this y, right? And so then we can compare that to get, I don't know, whatever, R squared, RMSE, whatever you're interested in, right, from the model. Now, the key thing here is I don't want to have to retrain my whole random forest. That's kind of slow and boring, right? So using the existing random forest, how can I figure out how important year made was, right? And so the suggestion was, let's randomly shuffle the whole column, right? So now that column is totally useless. It's got the same mean, same distribution, everything about it is the same, but there's no connection at all between particular people, actual year made, and what's now in that column. I've randomly shuffled it, okay? And so now I put that new version through with the same random forest, so there's no retraining done, okay, to get some new y hat, I call it y hat ym, right? And then I can compare that to my actuals to get like an RMSE ym, right? And so now I can start to create a little table. So now I can create a little table where I've basically got like the original here, RMSE, and then I've got with year made scrambled. So this one had an RMSE of like 3, this one had an RMSE of like 2, enclosure, scrambling that had a RMSE of like 2.5, right? And so then I just take these differences. So I'd say year made, the importance is 1. 3 minus 2. The enclosure is 0.5, 3 minus 2.5, and so forth, right? So how much worse did my model get after I shuffled that variable? Does anybody have any questions about that? Can you pass that to Danielle, please?
I assume you just chose those numbers randomly, but my question, I guess, is, do all of them theoretically come out a perfect model to start out with? Like, will all the importances sum to 1, or is that not?
No.
They're just...
Honestly, I've never actually looked at what the units are, so I'm actually not quite sure.
Okay.
Sorry. We can check it out during the week. If somebody's interested, have a look at the this sklearn code and see exactly what those units of measure are, because I've never bothered to check. Although I don't check like the units of measure specifically, what I do check is the relative importance. And so like, here's an example. So rather than just saying like, what are the top 10? Yesterday, one of the practicum students asked me about a feature importance where they said like, oh, I think these 3 are important. And I pointed out that the top one was 1,000 times more important than the second one. Right? So like, look at the relative numbers here. And so in that case, it's like, no, don't look at the top 3. Look at the one that's 1,000 times more important and ignore all the rest. Right? And so this is where sometimes the kind of your natural tendency to want to be like precise and careful, you need to override that and be very practical. It's like, okay, this thing's 1,000 times more important. Don't spend any time on anything else. Right? So then you can go and talk to the manager of your project and say like, okay, this thing's 1,000 times more important. And then they might say, oh, that was a mistake. It shouldn't have been in there. We don't actually have that information at the decision time. Or, for whatever reason, we can't actually use that variable. And so then you could remove it and have a look. Or they might say, gosh, I had no idea that like that was by far more important than everything else put together. So let's forget this random forest thing and just focus on like understanding how we can better collect that one variable and better use that one variable. So that's like something which comes up quite a lot. And actually another place that came up just yesterday, again, another practicum student asked me, hey, I'm doing this medical diagnostics project, and my R squared is 0.95 for a disease which I was told is very hard to diagnose. Is this random forest a genius or is something going wrong? And I said, like, remember, the second thing you do after you build a random forest is to do feature importance. So do feature importance, and what you'll probably find is that the top column is something that shouldn't be there. And so that's what happened. He came back to me half an hour later. He said, yeah, I did the feature importance. You were right. The top column was basically something that was another encoding of the dependent variable. I've removed it. And now my R squared is negative 0.1, so that's an improvement. Okay. The other thing I like to look at is this chart, right? Is to basically say, like, where do kind of things flatten off in terms of like which ones should I be really focusing on. So that's the most important one. Right? And so when I did credit scoring in telecommunications, I found there were 9 variables that basically predicted very accurately who was going to end up paying for their phone and who wasn't. And like apart from ending up with a model that saved them $3 billion a year in fraud and credit costs, it also let them basically rejig their process so that they focused on collecting those 9 variables much better. All right. Who wants to do partial dependence? This is an interesting one. Very important, but in some ways kind of tricky to think about.
I'll go ahead and try.
Yeah, please do.
So from my understanding of what partial dependence is that there's not always necessarily like a relationship between strictly the dependent variable and this independent variable that necessarily like is showing importance, but rather an interaction between two variables that are working together.
Something like this, right?
Yeah.
Where we're like, oh, that's weird. Like you'd expect this to be kind of flat and there's a weird pokey bit.
Yeah. Mm-hmm. And so this example, what we found was that it's not necessarily year made or when the sale was elapsed, but it's actually the age of the model. And so that is easier to just like to tell a company, well, obviously your younger models are going to sell for more, and it's less about when the year was made.
Yeah, exactly. So let's come back to how we calculate this in a moment. But the first thing to realize is that the vast majority of the time, post your course here, when somebody shows you a chart, it'll be like a univariate chart. They'll just like grab the data from the database and they'll plot X against Y, and then managers have a tendency to want to like make a decision, right? So it'd be like, oh, there's this like drop off here, so we should like stop dealing in equipment made between 1990 and 1995 or whatever, right? And this is like a big problem because like real world data has lots of these interactions going on. So like, maybe there was a recession going on around the time that those things are being sold, or maybe around that time people were buying more of a different type of equipment or whatever, right? So generally what we actually want to know is, all other things being equal, what's the relationship between year made and sale price, right? Because like if you think about the drivetrain approach idea of like the levers, you really want a model that says, if I change this lever, how will it change my objective? Okay? And so it's by pulling them apart using partial dependence that you can say, okay, actually, this is the relationship between year made and sale price, all other things being equal. Right? So how do we calculate that?
So for the variable year made, for example, you're going to train, you keep every other variable constant, and then you're going to pass every single value of the year made and then train the model after that. So for every model, you're going to have the light blue for the values of it, and the median is going to be the yellow line up there.
Good. Okay. So let's try and draw that. So by leave everything else constant, what she means is leave them at whatever they are in the data set. So just like when we did feature importance, right, we're going to leave the rest of the data set as it is, and we're going to do partial dependence plot for year made. All right, so we've got all of these other rows of data that we'll just leave as they are. And so instead of randomly shuffling year made, instead what we're going to do is replace every single value with exactly the same thing, 1960. Okay? And just like before, we now pass that through our existing random forest, which we have not retrained or changed in any way, to get back out a set of predictions. Why 1960? Okay, and so then we can plot that on a chart. Year made against partial dependence, 1960, here. Okay, then we can do it for 1961, 2, 3, 4, 5, and so forth, right? And so we can do that for on average for all of them, or we could do it just for one of them, right? And so when we do it for just one of them, and we change its year made and pass that single thing through our model, that gives us one of these blue lines. Right? So each one of these blue lines is a single row as we change its year made from 1960 up till 2008. And so then we can just take the median of all of those blue lines to say, you know, on average, what's the relationship between year made and price, all other things being equal. So why is it that this works? Why is it that this process tells us the relationship between year made and price, all other things being equal? Well, maybe it's good to think about like a really simplified approach. A really simplified approach would say, what's the average auction? You know, what's the average sale date? What's the most common type of machine we sell? Which location do we mostly sell things? And like we could come up with a single row that represents the average auction. And then we could say, okay, let's run that row through the random forest, but replace its year made with 1960. And then do it again with 1961, and then do it again with 1962. And we could like plot, you know, those on our little chart, right? And that would give us a version of the relationship between year made and sale price, all other things being equal, right? But what if, like, tractors looked like that, and backhoe loaders looked like that, right? Then taking the average one would hide the fact that there are these totally different relationships, right? So instead, we basically say, okay, our data tells us what kinds of things we tend to sell and who we tend to sell them to and when we tend to sell them, so let's use that, right? So then we actually find out, like, for every blue line, like, here are actual examples of these relationships, right? And so then what we can do is, as well as plotting the median, is we can do a cluster analysis to find out, like, a few different shapes, right? And so we may find, in this case, they all look like pretty much this different versions of the same thing with different slopes. So my main takeaway from this would be that the relationship between sale price and year is basically a straight line, right? And remember, this was log of sale price, right? So this is actually showing us an exponential. And so this is where I would then like bring in the domain expertise, which is like, okay, things depreciate over time by a constant ratio. So therefore, I would expect older stuff, year made, to have this exponential shape. So this is where, like I kind of mentioned, like at the very start of my machine learning project, I generally try to avoid using as much domain expertise as I can and let the data do the talking, right? So like one of the questions I got this morning was like, oh, if there's like a sale ID, a model ID, I should throw those away, right? Because they're just IDs. It's like, no, right? Don't assume anything about your data, right? Leave them in, and if they turn out to be super important predictors, you want to find out, you know, why is that? Okay, but then now I'm at the other end of my project, right? I've done my feature importance. I've pulled out the stuff which is like, you know, from that dendrogram, you know, the kind of redundant features. I'm looking at the partial dependence, and now I'm thinking like, okay, is this shape what I expected? Okay, so even better, before you plot this, first of all think, what shape would I expect this to be? Because it's always easy to justify to yourself after the fact, oh, I knew it would look like this. Right? So what shape do you expect? And then is it that shape? So in this case, I'd be like, yeah, this is what I would expect. Okay. Where else? This is definitely not what I'd expect. So the partial dependence plot has really pulled out the underlying truth. Okay. So does anybody have any questions about like why we use partial dependence or how we calculate it? Who's got the? Oh, you've got it.
So say you found, say 20 features that you think are important. Are you gonna measure the partial dependence for every single one of them? So is there a limit on that?
If there are 20 features that are important, then I will do the partial dependence for all of them. where important means like it's a lever I can actually pull. It's like the magnitude of its size is like not much smaller than the other 19. Like, based on all of these things, it's like, yeah, it's a feature I ought to care about. Then I will want to know how it's related. It's pretty unusual to have that many features that are important both operationally and from a modeling point of view, in my experience.
Sorry, one follow-up.
Sure.
How do you define important, actually, now I think about it?
So important means it's a lever, so it's something I can change. And it's like, kind of at the spiky end of this tail. Or, maybe it's not a lever directly, like maybe it's like zip code, and I can't actually tell my customers where to live, but I could like focus my new marketing attention on a different zip code,
Would it make sense to do pairwise shuffling for every combination of two features and hold everything else constant, like in feature importance, to see interactions and compare scores?
So you wouldn't do that so much for partial dependence. I think your question is really getting to the question of could we do that for feature importance? Right. So I think interaction feature importance is a very important and interesting question. But doing it by randomly shuffling every pair of columns, if you've got 100 columns, sounds computationally intensive, possibly infeasible. So what I'm going to do is, after we talk about tree interpreter, I'll talk about an interesting but largely unexplored approach that will probably work. Okay, who wants to do tree interpreter? All right, over here, Prince. Can you pass that over here to Prince?
I was thinking this to be more like feature importance, but feature importance is for complete random forest model, and this tree interpreter is for feature importance for particular observation. So if that, let's say it's about hospital readmission. So if a patient A1 is going to be readmitted to a hospital, which feature for that particular patient is going to impact, and how can we change that? And it is calculated starting from the prediction of mean, then seeing how each feature is changing the behavior of that particular patient.
Okay. I'm smiling because that was one of the best examples of technical communication I've heard in a long time. So it's really good to think about like why was that effective, right? So what Prince did there was he used as specific an example as possible. Right? So humans are much less good at understanding abstractions, right? So if you kind of say, oh, it takes some kind of feature and then there's an observation in that feature where it's like, no, it's a hospital readmission. Okay, and so we take a specific example. The other thing he did, which was very effective, was to kind of take an analogy to something we already understand. So we already understand the idea of feature importance across all of the rows in a data set. So now we're going to do it for a single row. Okay, so like, one of the things I was really hoping we would learn from this experience is how to become effective technical communicators. So that was a really great role model from Prince of like using all of the tricks we have at our disposal for effective technical communication. So hopefully you found that a useful explanation. I don't have a hell of a lot to add to that other than to show you, what that looks like. So with the tree interpreter, we picked out a row, okay? And so remember when we talked about the confidence intervals at the very start, the confidence based on tree variance, we mainly said like you'd probably mainly use that for a row. So this would also be for a row. So it's like, okay, why is this patient likely to be readmitted? Okay, so here is all of the information we have about that patient. or in this case, this auction. Right? Why is this auction so expensive? So then we call treeinterpreter.predict, and we get back the prediction of the price, right? The bias, which is the root of the tree. So this is just the average price for everybody. So this is always going to be the same. And then the contributions, which is how important is each of these things, right? And so the way we calculated that was to say, okay, at the very start, the average price was 10, right? And then we split on enclosure, right? And for those with this enclosure, the average was 9.5. And then we split on year made, I don't know, less than 1990. And for those with that year made, the average price was 9.7. Right, and then we split on the number of hours on the meter, and for with this branch we got 9.4. Right, and so we then have a particular auction which we pass it through the tree, and it just so happens that it takes this path. Right, so one row can only have one path through the tree. Right, and so we ended up at this point. Okay, so then we can create a little table, right? And so as we go through, we start at the top, and we start with 10, right? That's our bias. And when we said enclosure resulted in a change from 10 to 9.5, minus 0.5. Year made changed it from 9.5 to 9.7, so plus 0.2. Right, and then meter changed it from 9.7 down to 9.4, which is minus 0.3. And then if we add all that together, 10 minus a half is 9.5, plus 0.2 is 9.7, minus 0.3 is 9.4. Lo and behold, that's that number, which takes us to our Excel spreadsheet. Where's Chris, who did our waterfall? There you are. All right, so last week we had to use Excel for this because there isn't a good Python library for doing waterfall charts. And so we got our starting point, this is the bias, and then we had each of our contributions, and we ended up with our total. The world is now a better place because Chris has created a Python waterfall chart module for us and put it on pip. So never again will we have to use Excel for this. And I wanted to point out that waterfall charts have been very important in business communications at least as long as I've been in business. So that's about 25 years. Python is a couple of decades old, a little bit less. Maybe a couple of decades old. But, despite that, no one in the Python world ever got to the point where they actually thought, I'm going to make a waterfall chart. So they didn't exist until 2 days ago. Which is to say, the world is full of stuff which ought to exist and doesn't necessarily take a hell of a lot of time to build. Chris, how long did it take you to build the first Python waterfall chart?
So a disclaimer is that the code existed.
Well, there was a gist of it, yeah.
But it wasn't in a function.
Yeah.
And I had it.
Yeah.
So,
about 8 hours. Okay, so, a hefty time amount, but not unreasonable. And now, forevermore, people, when they want the Python waterfall chart, will end up at Chris's GitHub repo and hopefully find lots of other USF contributors who have made it even better. So in order for you to help improve Chris's Python waterfall, you need to know how to do that, right? And so you're going to need to submit a pull request. Life becomes very easy for submitting pull requests if you use something called Hub. So if you go to github/hub, That will send you over here. And what they suggest you do is that you alias get to hub, because it turns out that hub actually is a strict superset of get. But what it lets you do is you can go get fork, get push, get pull request, and you've now sent Chris a pull request. Without hub, this is actually a pain and requires like going to the website and filling in forms and stuff, right? So this gives you no reason not to do pull requests. And I mention this because like when you're interviewing for a job or whatever, I can promise you that the person you're talking to will check your GitHub. And if they see you have a history of submitting thoughtful pull requests that are accepted to interesting libraries, that looks great, right? It looks great because it shows you're somebody who actually contributes. It also shows that if they're being accepted, that you know how to create code that fits with people's coding standards, has appropriate documentation, passes their tests and coverage, and so forth, right? So when people look at you and they say, oh, here's somebody with a history of successfully contributing accepted pull requests to open source libraries, that's a great part of your portfolio, okay? And you can specifically refer to it, right? So either I'm the person who built Python waterfall, here is my repo, or I'm the person who contributed currency number formatting to Python waterfall, here's my pull request. Anytime you see something that doesn't work right in any open source software you use is not a problem. It's a great opportunity, right? Because you can fix it and send in the pull request. So yeah, give it a go. It actually feels great the first time you have a pull request accepted. And of course, one big opportunity is the FastAI library. Thank you. Who was the person here, the person who added all the docs to FastAI structured? In the other class, okay. So thanks to one of our students, we now have doc strings for most of the FastAI.structured library, and that again came via a pull request. So thank you. Okay. Does anybody have any questions about how to calculate any of these random forest interpretation methods, or why we might want to use any of these random forest interpretation methods? Because towards the end of the week, you're going to need to be able to build all of these yourself from scratch. One over there. Can you pass that, please? That's right.
Just looking at the tree interpreter, I noticed that some of the values are NaNs. How I get why you would keep them in the tree, but how can an NaN have a feature importance?
Okay, let me pass it back to you. Why not? So, in other words, how is NaN handled in pandas and therefore in the tree?
Set to some default value.
Does anybody remember how pandas, notice these are all in categorical variables. How does pandas handle NaNs in categorical variables, and how does FastAI deal with them? Can somebody pass it to the person who's talking?
-1 for pandas?
Yeah, pandas sets them to -1 category code.
Yeah.
And do you happen to remember what we then do? Doesn't matter really. We add 1 to all of the category codes, so it ends up being 0. So in other words, we have a category with, remember, by the time it hits the random forest, it's just a number, and it's just the number 0, right? And we map it back to the descriptions back here. So the question really is, why shouldn't the random forest be able to split on 0? It's just another number. So it could be NaN, high, medium, or low, 0, 1, 2, 3, 4. And so, missing values are one of these things that are generally taught really badly. Like often people get taught like, here are some ways to remove columns with missing values, or remove rows with missing values, or to replace missing values. That's like never what we want, because missingness is very, very, very often interesting. And so we actually learnt that from our feature importance that coupler system NaN is like one of the most important features. And so for some reason, well, I could guess, right? coupler system NAN presumably means this is a kind of industrial equipment that doesn't have a coupler system. Now, I don't know what kind that is, but apparently it's a more expensive kind. Does that make sense?
Yeah.
Okay. So, yeah, I did this competition for university grant research success, where by far the most important predictors were whether or not some of the fields were null. And it turned out that this was data leakage, that these fields only got filled in most of the time after a research grant was accepted, right? So, it allowed me to win that Kaggle competition, but didn't actually help the university very much. Okay, great. So let's talk about extrapolation. And I am going to do something risky and dangerous, which is we're going to do some live coding. And the reason we're going to do some live coding is I want to explore extrapolation together with you, and I kind of also want to help give you a feel of, like how you might go about like writing code quickly in this notebook environment, right? And this is the kind of stuff that you're going to need to be able to do, in the real world and in the exam, is kind of quickly create the kind of code that we're going to talk about. So I really like creating synthetic data sets. Anytime I'm trying to like investigate the behavior of something, because if I have a synthetic data set, I know how it should behave. Which reminds me, before we do this, I promised that we would talk about interaction importance, and I just about forgot. Tree interpreter tells us the contributions for a particular row based on the difference in the tree. We could calculate that for every row in our data set and add them up, right? And that would tell us feature importance. It would tell us feature importance in a different way, right? One way of doing feature importance is by shuffling the columns one at a time. Another way is by doing tree interpreter for every row and adding them up. Neither is more right than the others. They're actually both quite widely used. So there's this kind of type 1 and type 2 feature importance. So we could try to expand this a little bit to do not just single variable feature importance, but interaction feature importance. Now here's the thing. What I'm going to describe is very easy to describe. It was described by Bryman right back when random forests were first invented, and it is part of the commercial software product from Salford Systems, who have the trademark on random forests. But it is not part of any open source library I'm aware of. And I've never seen an academic paper that actually studies it closely. So what I'm going to describe here is a huge opportunity. But it's also like there's lots and lots of details that kind of need to be fleshed out. But here's the basic idea. This particular difference here, right, is not just because of year made, but because of a combination of year made and enclosure. Right? The fact that this is 9.7 is because enclosure was in this branch and year made was in this branch. So in other words, we could say the contribution of enclosure interacted with year made is minus 0.3. Yeah? And so what about that difference? Well, that's an interaction of year made and hours on the meter. So year made interacted with, I'm using star here not to mean times, but to mean interacted with. It's a kind of a common way of doing things, like R's formulas do it this way as well. Year made by interacted with meter has a contribution of minus 0.1. Perhaps we could also say from here to here that this also shows an interaction between meter and enclosure, like with one thing in between them. So maybe we could say meter by enclosure equals, and then what should it be? Should it be minus 0.6? I mean, in some ways that kind of seems unfair because we're also including like the impact of year made, right? So maybe it should be minus 0.6. Maybe we should add back this 0.2, right? And these are like details that I actually don't know the answer to, right? Like how should we best kind of assign a contribution to each pair of variables in this path, right? But clearly, conceptually, we can, right? The pairs of variables in that path all represent interactions, right? Yes, Chris, could you pass that to Chris, please?
Why don't you force them to be next to each other in the tree?
I mean, I'm not going to say it's the wrong approach. I don't think it's the right approach, though, because it feels like this path here, meter and enclosure are interacting. So it seems like not recognizing that contribution is throwing away information. But I'm not sure, I had one of my staff at Kaggle actually do some R&D on this a few years ago, and they actually found, and I wasn't close enough to know how they dealt with these details, but they got it working pretty well. But unfortunately, it never saw the light of day as a software product. But like, this is something which, maybe a group of you could get together and build, I mean, do some Googling to check, but I really don't think that there are any interaction feature importance parts of any open source library. Can you pass that back?
Wouldn't this exclude interactions, though, between variables that don't matter until they interact? So say your row never chooses to split down that path, but that variable interacting with another one becomes your most important split.
I don't think that happens, right? Because if there's an interaction that's important only because it's an interaction and not on a univariate basis, it will appear sometimes, assuming that you set max features to less than 1. Okay. And so therefore it will appear in some path.
What is meant by interaction here? Is it multiplication, ratio, addition?
Interaction means appears on the same path through a tree. Like an interaction, in this case the tree, there's an interaction between enclosure and year made because we branch on enclosure and then we branch on year made. So to get to here, we have to have some specific value of enclosure and some specific value of year made.
Sorry, my brain's kind of working on this right now. What if you went down the middle leaves between the two things you were trying to observe, and you could just sort of and you would also take into account what the final measure is. So, I mean, if we extend the tree downwards, you'd have many measures, both of like the two things you're trying to look at and also the in-between steps. There seems to be a way to like average information out in between them.
There could be. So I think what we should do is talk about this on the forum. I think this is fascinating, and I hope we build something great. But I need to do my live coding. So that was a great discussion. Keep thinking about it. And do some experiments. And so to experiment with that, you almost certainly want to create a synthetic data set first, right? It's like y equals x1 plus x2 plus x1 times x2 or something, like something where that there's this interaction effect and there isn't that interaction effect, and then you want to make sure that the feature importance you get at the end is what you expected, right? And so probably the first step would be to do single variable feature importance using the tree interpreter style approach. And one nice thing about this is like it doesn't really matter how much data you have. Like all you have to do to calculate feature importance is just like slide through the tree, right? So you should be able to write in a way that's actually pretty fast. And so even writing it in pure Python might be fast enough, depending on your tree size. Okay, so we're going to talk about extrapolation. And so the first thing I want to do is create a synthetic data set that has a simple linear relationship. We're going to pretend it's like a time series, right? So we need to basically create some x values. So the easiest way to kind of create some synthetic data of this type is to use linspace, which just creates some evenly spaced data, right, between start and stop, with by default 50 observations. So if we just do that, right, there it is. Okay. And so then we're going to create a dependent variable. And so let's assume there's just a linear relationship between x and y, and let's add a little bit of randomness to it, right? So uniform random between low and high. So we could like add somewhere between like minus 0.2 and 0.2, say, okay? And so the next thing we need is a shape, right? Which is basically what dimensions do you want these random numbers to be? And obviously we want them to be the same shape as x's shape. So we can just say x dot shape. Okay? So in other words, that's x dot shape. Remember, when you see something in parentheses with a comma, that's a tuple with just one thing in it. Okay, so this is of shape 50, and so we've added 50 random numbers, and so now we could plot those. Okay, so shift tab, x comma y. All right, so there's our data. Okay, so like for when you're both working as a data scientist or for doing your exams in this course, you need to be able to like quickly whip up a data set like that, throw it up on a plot without thinking too much, okay? And like, as you can see, you don't have to really remember much, if anything. You just have to know how to like hit shift tab to check the names of the parameters. You know, everything in the exam will be open book, open internet, so you can always like Google for something to try and find linspace if you forgot what it's called. All right, so let's assume that's our data, right? And so we're now going to build a random forest model. And what I want to do is build a random forest model that kind of acts as if this is a time series. So I'm going to take this as a training set, right? I'm going to take this as our validation or test set, just like we did in, you know, groceries or bulldozers or whatever. Okay. So we can use exactly the same kind of code that we used in split vals, right? So we can basically say x train, comma, x val equals x up to 40, comma, x from 40. Okay, so that just splits it into the first 40 versus the last 10, right? And so we can do the same thing for y. And there we go. Okay, so the next thing to do is we want to create a random forest. Okay, and fit it. And that's going to require x's and y's. All right, now that's actually going to give an error. And the reason why is that it expects x to be a matrix, not a vector, because it expects x to have a number of columns of data, right? So it's important to know that a matrix with one column is not the same thing as a vector, right? So if I try to run this, right? Expected 2D array got 1D array instead. So we need to convert our 2D array into a 1D array. So remember I said x.shape is 50, right? So x has one axis. So here's the important nomenclature. X's rank is 1. The rank of a variable is equal to the length of its shape. How many axes does it have? So a vector we can think of as an array of rank 1. A matrix is an array of rank 2. I very rarely use words like vector and matrix because they're kind of meaningless specific examples of something more general, which is they're all n-dimensional tensors, right? Or n-dimensional arrays. Okay, so an n-dimensional array, we can say it's a tensor of rank n. They basically mean kind of the same thing. Physicists get crazy when you say that, because to a physicist, a tensor has quite a specific meaning, but in machine learning, we generally use it in the same way. Okay, so how do we turn an array, a one-dimensional array into a two-dimensional array? There's a couple of ways we can do it, but basically we slice it, right? So colon means give me everything in that axis, right? Colon comma none means give me everything in the first axis, which is the only axis we have, and then none is a special indexer, which means add a unit axis here. So let me show you. That is of shape 50, 1. So it's of rank 2. Right? It has two axes. One of them is a very boring axis, right? It's a length 1 axis. So let's move this over here. There's 1, 50. Okay? And then to remind you, the original is just 50. Right? So you can see I can put none as a special indexer to introduce a new unit axis there. Okay, so this thing has 1 row and 50 columns. This thing has 50 rows and 1 column. So that's what we want, right? We want 50 rows and 1 column. This kind of playing around with ranks and dimensions is going to become increasingly important in this course and in the deep learning course, right? So spend a lot of time slicing with none, slicing with other things, try to create 3-dimensional, 4-dimensional tensors and so forth. I'll show you a trick. I'll show you 2 tricks. The first is you never ever need to write comma colon. It's always assumed. So if I delete that, this is exactly the same thing. Okay? And you'll see that in code all the time, so you need to recognize it. The second trick is this is adding an axis in the second dimension, right? Or I guess the index 1 dimension. What if I always want to put it in the last dimension, right? And often our tensors change dimensions without us looking, because you went from a 1-channel image to a 3-channel image, or you went from a single image to a mini batch of images. Suddenly you get new dimensions appearing. So to make things general, I would say this, ... means as many dimensions as you need to fill this up. Okay? And so in this case, it's exactly the same thing, but I would always try to write it that way because it means it's going to continue to work as I get, higher dimensional tensors. All right. So in this case, I want 50 rows and 1 column. So I'll call that, say, x1. Okay. So let's now use that here. And so this is now a 2D array. And so I can create my random forest. Okay. So then I could plot that. And this is where you're going to have to turn your brains on, because the folks this morning got this very quickly, which was super impressive. I'm going to plot y train against m.predict x train. Okay, before I hit go, what is this going to look like? Yeah, it should basically be the same, right? Our predictions hopefully are the same as the actuals. So this should fall on a line. But there's some randomness, so it won't quite. I should have used scatter plot. Okay? Right, so that's cool. Right, that was the easy one. Let's now do the hard one. The fun one. What's that going to look like? Okay. So I'm going to say no, but nice try. You know, it's like, hey, we're extrapolating to the validation. That's what I'd like it to look like, but that's not what it is going to look like. Think about what trees do, and think about the fact that we have a validation set here and a training set here. So think about a forest is just a bunch of trees. So the first tree is going to, okay, Melissa's going to have a go. Can you pass that to Melissa?
Will it start grouping the dots?
Yeah, that's what it does. Okay, but you know, let's think about how it groups the dots. So, yeah, Tim.
I'm guessing since all the new data is actually outside of the original scope, it's all going to be basically the same. It's like one huge group.
Yeah, right. So, like we make it like forget the forest. Let's create one tree, right? So we're probably going to split somewhere around here first, and then we're going to probably split somewhere around here. And then we're going to split somewhere around here and somewhere around here, right? And so our final split is here, right? So our prediction, when we say, okay, let's take this one. And so it's going to put that through the forest, right? And end up predicting this average. It can't predict anything higher than that, because there is nothing higher than that to average, right? So this is really important to realize. A random forest is not magic, right? It's just returning the average of nearby observations, where nearby is kind of in this like tree space. So let's run it. Let's see if Tim's right. But holy shit, that's awful, right? And like, if you don't know how random forests work, then this is going to totally screw you, right? If you think that it's actually going to be able to extrapolate to any kind of data it hasn't seen before, like particularly like future time periods, it's just not. Like, it just can't. It's just averaging stuff it's already seen. That's all it can do. Okay? So we're going to be talking about like how to avoid this problem. We talked a little bit in the last lesson about trying to avoid it by just like avoiding unnecessary time-dependent variables where we can, right? But in the end, if you really have a time series that looks like this, we actually have to deal with a problem, right? So one way we could deal with the problem would be use like a neural net, right? Use something that actually has a function or shape that can actually like fit something, that actually fits something like this, right? And so then it'll extrapolate nicely. Another approach would be to use all the time series techniques you guys are learning about in the morning class to fit some kind of time series, right? And then detrend it, right? And so then you'll end up with detrended dots, and then use the random forest to predict those, right? And that's particularly cool, right? Because if you're, like, imagine that your random forest was actually trying to predict data that, like, I don't know, maybe it was two different states. And so the blue ones, you know, are down here, and the red ones are up here, right? Now, if you tried to use a random forest, it's going to do a pretty crappy job, because, like, time is going to seem much more important. So it's basically still going to, like, split like this, and then it's going to split like this. And then finally, once it kind of gets down to this piece, it'll be like, oh, okay, now I can see the difference between the states, right? So in other words, like when you've got this big time piece going on, you're not going to see the other relationships in the random forest until every tree deals with time. So one way to fix this would be with a gradient boosting machine, GBM, right? And what a GBM does is it creates a little tree, right, and runs everything through that first little tree, which could be like the time tree, and then it calculates the residuals, and then the next little tree just predicts the residuals. So it'd be kind of like detrending it, right? So GBMs handle this. GBMs still can't extrapolate to the future, but at least they can deal with time-dependent data more conveniently, right? So we're going to be talking about this quite a lot more over the next couple of weeks, right? And in the end, the solution is going to be just use neural nets, right? But for now, using some kind of time series analysis, detrend it, and then use a random forest on that isn't a bad technique at all. And if you're playing around with something like the Ecuador groceries competition, that would be a really good thing to fiddle around with. All right, see you next time. Welcome back. We're going to be talking today about random forests. We're going to finish building our own random forest from scratch. But before we do, I wanted to tackle a few things that have come up during the week, a few questions that I've had. And I want to start with kind of the position of random forests in general. So we spent about half of this course doing random forests, and then after today, the second half of this course will be neural networks, broadly defined. This is because these two represent like the two key classes of techniques which cover nearly everything that you're likely to need to do. Random forests belong to the class of techniques of decision tree ensembles, along with gradient boosting machines being the other key type, and some variants like extremely randomized trees. They have the benefit that they're highly interpretable, scalable, flexible, work well for most kinds of data. They have the downside that they don't extrapolate at all to like data that's outside the range that you've seen, as we looked at the end of last week's session. But they're a great starting point, and so I think there's a huge catalog of machine learning tools out there, and like a lot of courses and books don't attempt to kind of curate that down and say like, for these kinds of problems use this, for these kinds of problems use that, finished. But they're rather like, here's a description of 100 different algorithms, and you just don't need them, like I don't see why you would ever use a support vector machine today, for instance. Like no reason at all I could think of doing that. People loved studying them in the 90s because they are like very theoretically elegant, and like you can really write a lot of math about support vector machines, and people did. But in practice, I don't see them as having any place. So there's like a lot of techniques that you could include in an exhaustive list of every way that people have looked at machine learning problems. But I would rather tell you like how to actually solve machine learning problems in practice. I think we're about to finish today the first class, which is one type of decision tree ensembles. In part 2, Yannet will tell you about the other key type there being gradient boosting, and we're about to launch next lesson into neural nets, which includes all kinds of GLM, ridge regression, elastic net, lasso, logistic regression, etc., are all variants of neural nets. Interestingly, Leo Breiman, who created random forests, did so very late in his life and unfortunately passed away not many years later. So partly because of that, very little has been written about them in the academic literature. Partly because SVMs had taken over at that point. Other people didn't look at them. And also, like, just because they're like quite hard to grasp at a theoretical level, like analyze them theoretically, it's quite hard to write conference papers about them or academic papers about them. So there hasn't been that much written about them, but there's been a real resurgence, or not resurgence, a new wave in recent years of empirical machine learning, like what actually works. Kaggle's been part of that, but also just part of it has just been like companies using machine learning to make shitloads of money, like Amazon and Google. And so nowadays, a lot of people are writing about decision tree ensembles and creating better software for decision tree ensembles like GBM and XGBoost and Ranger for R and Scikit-learn and so forth. But a lot of this is being done in industry rather than academia. But you know, it's encouraging to see. There's certainly more work being done in deep learning than in decision tree ensembles, particularly in academia, but there's a lot of progress being made in both. You know, if you look at like of the packages being used today for decision tree ensembles, like all the best ones, the top 5 or 6, I don't know that any of them really existed 5 years ago, you know, maybe other than like sklearn or even 3 years ago. So yeah, so that's been good. But I think there's a lot of work still to be done. We talked about, for example, figuring out what interactions are the most important last week. And some of you pointed out in the forums that actually there is such a project already for gradient boosting machines, which is great, but it doesn't seem that there's anything like that yet for random forests. And, you know, random forests do have a nice benefit over GBMs, that they're kind of harder to screw up, you know, and easier to scale. So hopefully that's something that, you know, this community might help fix. Another question I had during the week was about the size of your validation set. How big should it be? So, like, to answer this question about how big does your validation set need to be, you first need to answer the question, how accurate do I need, how precisely do I need to know the accuracy of this algorithm, right? So, like, if the validation set that you have is saying, like, this is 70% accurate, and if somebody said, well, is it 75% or 65% or 70%? And the answer was, I don't know, anything in that range is close enough. Like, that would be one answer. Whereas if it's like, is it 70% or 70.01% or 69.99%? Like, then that's something else again, right? So you need to kind of start out by saying, like, how accurate do I need this? So, like, for example, in the deep learning course, we've been looking at dogs versus cats images. And the models that we're looking at had about a 99.4, 99.5% accuracy on the validation set. Okay. And our validation set size was 2,000. Okay. In fact, let's do this in Excel. That'll be a bit easier. So our validation set size was 2,000, and our accuracy was 99.4%, right? So the number of incorrect is something around 1 minus accuracy times n. So we were getting about 12 wrong, right? And the number of cats we had is half. And so the number of wrong cats is about 6. Okay. So then, like, we run a new model and we find instead that the accuracy has gone to 99.2%. Right? And then it's like, okay, is this less good at finding cats? And it's like, well, it got 2 more cats wrong. So it's like, probably not, right? So, but then it's like, well, does this matter? Does 99.4 versus 99.2 matter. And if this was like, it wasn't about cats and dogs, but it was about finding fraud, right? Then the difference between a 0.6% error rate and a 0.8% error rate is like 25% of your cost of fraud. So like that can be huge. Like it was really interesting, like when ImageNet came out earlier this year, the new competition results came out, and the accuracy had gone down from 3%, the error went down from 3% to 2%. And I saw a lot of people on the internet, like famous machine learning researchers being like, nah, some Chinese guys got it better from like 97% to 98%. It's like statistically not even significant, who cares, kind of a thing. But actually, I thought like, holy crap, this Chinese team just blew away the state-of-the-art in image recognition. Like the old one was 50% less accurate than the new one. Like that's actually the right way to think about it, isn't it? Because it's like, you know, we were trying to recognize, you know, like which tomatoes were ripe and which ones weren't. And like our new approach, you know, the old approach, like 50% of the time more was like letting in the unripe tomatoes. Or, you know, 50% more of the time we were like accepting fraudulent customers. Like that's a really big difference. So just because like this particular validation set we can't really see 6 versus 8 doesn't mean that 0.2% different isn't important. It could be. So my kind of rule of thumb is that this number of like how many observations you're actually looking at, I want that generally to be somewhere higher than 22. Why 22? Because 22 is the magic number where the t-distribution roughly turns into the normal distribution. Right? So as you may have learnt, the t-distribution is the normal distribution for small data sets. Right? And so in other words, once we have 22 of something or more, it kind of starts to behave kind of normally in both sense of the words. Like it's kind of more stable and you can kind of understand it better. So that's my magic number. When somebody says, do I have enough of something? I kind of start out by saying, like, do you have 22 observations of the thing of interest? So if you were looking at like lung cancer, you know, and you had a data set that had like 1,000 people without lung cancer and 20 people with lung cancer, I'd be like, I very much doubt we're going to make much progress, you know, because we haven't even got 20 of the thing you want. So ditto with the validation set. If you don't have 20 of the thing you want, then it's very unlikely to be useful. Or if like at the level of accuracy we need, it's not plus or minus 20. That's the point where I'm thinking like, be a bit careful.
So just to be clear, you want 22 to be the number of samples in each set, like in the validation, the test, and the train, or?
So what I'm saying is like, if there's less than 22 of a class in any of the sets, then it's getting pretty unstable at that point, right? And so like that's just like the first rule of thumb. But then what I would actually do is like start practicing what we learned about the binomial distribution, or actually the Bernoulli distribution. So what is the mean of the binomial distribution of n samples and probability p? N times p. Okay, thank you. N times p is our mean, right? So if you've got a 50% chance of getting a head and you toss it 100 times, on average you get 50 heads. Okay, and then what's the standard deviation? NP1 minus p. Okay, so these are like two numbers. Well, the first number you don't really have to remember, it's intuitively obvious. The second one is one that try to remember forevermore, because not only does it come up all the time, the people that you work with will all have forgotten it. So you'll be like the one person in the conversation who can immediately go, we don't have to run this 100 times, I can tell you straight away, it's binomial, it's going to be NPQ, NP1 minus P. Then there's the standard error. The standard error is if you run a bunch of trials, each time getting a mean, what is the standard deviation of the mean? I don't think you guys have covered this yet, is that right? No? So this is really important because this means like if you train 100 models, right, each time the validation set accuracy is like the mean of a distribution. And so therefore the standard deviation of that validation set accuracy, it can be calculated with the standard error. And this is equal to the standard deviation divided by square root n, right? So this tells you, so like one approach to figuring out like is my validation set big enough is train your model 5 times with exactly the same hyperparameters each time and look at the validation set accuracy each time, and it gives, there's like a mean and a standard deviation of 5 numbers you could use, or a maximum and a minimum you can choose. But to save yourself some time, you can figure out straight away that like, okay, well, I have a 0.99 accuracy as to whether I get the cat correct or not correct. So therefore, the standard deviation is equal to 0.99 times 0.01. Okay, and then I can get the standard error of that, right? So basically, the size of the validation set you need is like however big it has to be such that your insights about its accuracy are good enough for your particular business problem. And so like I say, like the simple way to do it is to pick a validation set of like a size 1,000, train 5 models, and see how much the validation set accuracy varies. And if it's like if they're all close enough for what you need, then you're fine. If it's not, maybe you should make it bigger, or maybe you should consider using cross-validation instead. Okay. So like, as you can see, it really depends on what it is you're trying to do. How common your less common class is and how accurate your model is. Could you pass that back to Melissa, please?
Thank you. I have a question about the less common classes. If you have less than 22, let's say you have one sample of something, let's say it's a face, and I only have one representation from that particular country, do I toss that into the training set and it adds variety? Do I pull it out completely out of the data set? Or do I put it in a test set instead of the validation set?
So you certainly couldn't put it in the test or the validation set because you're asking, in general, because you're asking, can I recognize something I've never seen before? But actually, this question of like, can I recognize something I've not seen before? There's actually a whole class of models specifically for that purpose. It's called either one-shot learning, which is you get to see something once and then you have to recognize it again, or zero-shot learning, which is where you have to recognize something you've never seen before. We're not going to cover them in this course, but they can be useful for things like face recognition. Like, is this the same person I've seen before? And so generally speaking, obviously for something like that to work, it's not that you've never seen a face before, it's that you've never seen Melissa's face before, and so you see Melissa's face once and you have to recognize it again. Yeah, so in general, your validation set and test set need to have the same mix or frequency of observations that you're going to see in production in the real world. And then your training set should have an equal number in each class. And if you don't, just replicate the less common one until it is equal. So this is, I think we've mentioned this paper before, very recent paper that came out. They tried lots of different approaches to training with unbalanced data sets and found consistently that oversampling the less common class until it is the same size as the more common class is always the right thing to do. So you could literally copy, so like I've only got 1,000, 10 examples of people with cancer and 100 without, so I could just copy those 10 another, 90 times. That's kind of a little memory inefficient. So a lot of things, including I think sklearn's random forests, have a class weights parameter that says each time you're bootstrapping or resampling, I want you to sample the less common class with a higher probability. Or ditto if you're doing deep learning, make sure in your mini batch it's not randomly sampled, but it's a stratified sample, so the less common class is picked more often. Okay. Okay. So let's get back to finishing off our random forests. And so what we're going to do today is we're going to finish off writing our random forest, and then after today your homework will be to take this class and to add to it all of the random forest interpretation algorithms that we've learned. Okay, so obviously to be able to do that, you're going to need to totally understand how this class works. So please, ask lots of questions as necessary as we go along. So just to remind you, we're doing the bulldozers Kaggle competition data set again. We split it as before into 12,000 validation, the last 12,000 records. And then just to make it easier for us to keep track of what we're doing, we're going to just pick 2 columns out to start with, year made and machine hours on the meter. Okay. And so what we did last time was we started out by creating a tree ensemble, and the tree ensemble had a bunch of trees, which was literally a list of n trees, where each time we just called create tree. Okay. And create tree contained a sample size number of random indexes. Okay. And this one was drawn without replacement. So remember, bootstrapping means sampling with replacement. So normally with scikit-learn, if you've got n rows, we grab n rows with replacement, which means many of them will appear more than once. So each time we get a different sample, but it's always the same size as the original data set. And then we have our setRF samples function that we can use, which does with replacement sampling of less than n rows. This is doing something again, which is it's sampling without replacement sample size rows, okay? Because we're permuting the numbers from 0 to self.y minus 1, and then grabbing the first self.sample size of them. Actually, there's a faster way to do this. You can just use np.random.choice, which is a slightly more direct way, but this way works as well. All right, so this is our random sample for this one of our n trees. And so then we're going to create a decision tree. And our decision tree, we don't pass it all of x, we pass it these specific indexes. And remember, x is a pandas data frame. So if we want to index into it with a bunch of integers, we have to use iloc, integer locations. Okay, and that makes it behave indexing-wise just like NumPy. Our y vector is NumPy, so we can just index into it directly. Right? And then we're going to keep track of our minimum leaf size. So then the only other thing we really need in Ensemble is some way to make a prediction. And so we were just going to do the mean of the tree prediction for each tree. All right, so that was that. And so then in order to be able to run that, we need a decision tree class because it's being called here. And so there we go. Okay, so that's the starting point. So the next thing we need to do is to flesh out our decision tree. So the important thing to remember is all of our randomness happened back here in the tree ensemble. The decision tree class we're going to create doesn't have randomness in it.
Okay, so right now we are building a random tree regressor, right? So that's why we are taking the mean of the tree, the outputs. If we were to work with classification, do we take the max? Like the classifier will give you either zeros or ones?
No, I would still take the mean. So each tree is going to tell you what percentage of that leaf node contains cats and what percentage contains dogs. So then I would average all those percentages and say across the trees, on average, there is 19% cats and 81% dogs. Good question. So, random tree classifiers are almost identical, or can be almost identical to random tree regressors. The technique we're going to use to build this today will basically exactly work for classification. It's certainly for binary classification, you can do with exactly the same code. For multi-class classification, you just need to change your data structure so that like you have like a one hot encoded matrix or a list of integers that you treat as a one hot encoded matrix. Okay, so our decision tree. So remember, our idea here is that we're going to like try to avoid thinking. So we're going to basically write it as if everything we need already exists. Okay, so we know from when we created the decision tree, we're going to pass in the x, the y, and the minimum leaf size. So here we need to make sure we've got the x and the y and the minimum leaf size. Okay, so then there's one other thing, which is as we split our tree into subtrees, we're going to need to keep track of which of the row indexes went into the left-hand side of the tree, which went into the right-hand side of the tree. Okay, so we're going to have this thing called indexes as well, right? So at first, we just didn't bother passing in indexes at all. So if indexes is not passed in, if it's none, then we're just going to set it to the entire length of y. Right, so np.arange is the same as just range in Python, but it returns a NumPy array. Right, so the root of a decision tree contains all the rows. That's the definition, really, of the root of a decision tree. So all the rows is row 0, row 1, row 2, etc., up to row y minus 1. Okay, and then we're just going to store away all that information that we were given. We're going to keep track of how many rows are there and how many columns are there. Okay. So then every leaf and every node in a tree has a value. It has a prediction. And that prediction is just equal to the average of the dependent variable. Okay. So every node in the tree, y indexed with the indexes is the values of the dependent variable that are in this branch of the tree. And so here is the mean. Okay? Some nodes in a tree also have a score, which is like how effective was the split here, right? But that's only going to be true if it's not a leaf node, right? A leaf node has no further splits. And at this point when we create a tree, we haven't done any splits yet. So its score starts out as being infinity. Okay? So having built the root of the tree, our next job is to find out which variable should we split on and what level of that variable should we split on. So let's pretend that there's something that does that. Find var split. So then we're done. Okay. So how do we find a variable to split on? So, well, we could just go through each potential variable. So C contains the number of columns we have. So go through each one and see if we can find a better split than we have so far on that column. Okay. Now notice this is like not the full random forest definition. This is assuming that max features is set to all, right? Remember, we could set max features to like 0.5, in which case we wouldn't check all the numbers from 0 to C. We would check half the numbers at random from 0 to C. So if you want to turn this into like a random forest that has the max features support, you could easily like add one line of code to do that. But we're not going to do it in our implementation today. So then we just need find better split. And since we're not interested in thinking at the moment, for now, we're just going to leave that empty. All right. So the one other thing I like to do with my kind of, when I start writing a class, is I like to have some way to print out what's in that class, right? And so if you type print followed by an object, or if at Jupyter Notebook you just type the name of the object, at the moment, it's just printing out underscore underscore main underscore underscore dot decision tree at blah blah blah, which is not very helpful, right? So if we want to replace this with something helpful, we have to define the special Python method name dunder repre to get a representation of this object. So when we basically just write the name like this, behind the scenes it calls that function, and the default implementation of that method is just to print out this unhelpful stuff. So we can replace it by instead saying, let's create a format string where we're going to print out n, and then show n, and then print val, and then show val. Okay, so how many rows are in this node, and what's the average of the dependent variable? Okay. Then, if it's not a leaf node, so if it has a split, then we should also be able to print out the score, the value we split out, and the variable that we split on. Now you'll notice here, self.isLeaf. IsLeaf is defined as a method, but I don't have any parentheses after it. This is a special kind of method called a property. And so a property is something that kind of looks like a regular variable, but it's actually calculated on the fly. So when I call isLeaf, it actually calls this function, right? But I've got this special decorator property, okay? And what this says is basically you don't have to include the parentheses when you call it, okay? And so it's going to say, all right, is this a leaf or not? So a leaf is something that we don't split on. If we haven't split on it, then its score is still set to infinity. So that's my logic. Does that make sense? So this at notation is called a decorator. It's basically a way of telling Python more information about your method. Does anybody here remember where you have seen decorators before? Can you pass it over here? Yeah, where have you seen decorators
Flask.
before? Tell us more about Flask and how it uses decorators.
It was the app route.
Yeah? What does that do?
That I forgot.
Okay. So,
I don't know how to describe it.
No worries. So Flask, so anybody who's done any web programming before with something like Flask or a similar framework would have had to have said, like, this method is going to respond to this bit of the URL and either to post or to get, and you put it in a special decorator. So behind the scenes, that's telling Python to treat this method in a special way. So here's another decorator, okay? And so, you know, if you get more advanced with Python, you can actually learn how to write your own decorators, which, as was mentioned, you know, basically insert some additional code. But for now, just know there's a bunch of predefined decorators we can use to change how our methods behave. And one of them is @property, which basically means you don't have to put parentheses anymore, which of course means you can't add any more parameters beyond self. Yep.
Why, if it's not a leaf, why is the score infinity? Because doesn't infinity mean you're at the root? Why? If
no, infinity means that you're not at the root. It means that you're at a leaf. So the root will have a split, assuming we find one.
Yeah.
Right? Everything will have a split till we get all the way to the bottom, the leaf. And so the leaves will have a score of infinity because they won't split. Great. All right. So that's our decision tree. It doesn't do very much, but at least we can like create an ensemble, right? 10 trees, sample size 1,000, right? And we can like print out. So now when I go mtrees 0, it doesn't say blah, 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 blah. It says what we asked it to say, n : 1,000, val : 10.8. Oh, wait. Okay? And this is a leaf because we haven't split on it yet. So we've got nothing more to say. Okay, so then the indexes are all the numbers from 0 to 1,000. Okay, because the base of the tree has everything. This is like everything in the random sample that was passed to it. Because remember, by the time we get to the point where it's a decision tree, we don't have to worry about any of the randomness in the random forest anymore. Okay. All right. So let's try to write the thing which finds a split. Okay, so we need to implement find better split. Okay, and so it's going to take the index of a variable number 1, variable number 3, whatever, and it's going to figure out what's the best split point. Is that better than any split we have so far? And for the first variable, the answer will always be yes, because the best one so far is none at all, which is infinity bad. Okay? So let's start by making sure we've got something to compare to. So the thing we're going to compare to will be scikit-learn's random forest. And so we need to make sure that scikit-learn's random forest gets exactly the same data that we have. So we start out by creating ensemble, grab a tree out of it, and then find out which particular random sample of X and Y did this tree use. Okay, and we're going to store them away so that we can pass them to scikit-learn. So we have exactly the same information. So let's go ahead and now create our random forest using scikit-learn. So one tree, one decision, no bootstrapping, so the whole data set. Right? So this should be exactly the same as the thing that we're going to create, this tree. Okay? So let's try. So we need to define find better split. Okay. So find better split takes a variable. Okay. So let's define our X independent variables and say, okay, well, it's everything inside our tree, but only those indexes that are in this node, right, which at the top of the tree is everything, right, and just this one variable. Okay? And then for our Y's, it's just whatever our dependent variable is at the indexes in this node. Okay, so there's our X and Y. So let's now go through every single value in our independent variable. And so I'll show you what's going to happen. So let's say our independent variable is year made. And not going to be in order. Right? And so we're going to go to the very first row, and we're going to say, okay, year made here is 3, right? And so what I'm going to do is I'm going to try and calculate the score if we decided to branch on the number 3, right? So I need to know which rows are greater than 3, which rows are less than or equal to 3, and they're going to become my left-hand side and my right-hand side, right? And then we need a score, right? So there's lots of scores we could use. So in random forests, we call this the information gain, right? The information gain is like how much better does our score get because we split it into these two groups of data. There's lots of ways we could calculate it: Gini, cross entropy, root mean squared error, whatever. If you think about it, there is an alternative formulation of root mean squared error which is mathematically the same to within a constant scale, but it's a little bit easier to deal with, which is we're going to try and find a split which causes the two groups to each have as low a standard deviation as possible. Right? So like I want to find a split that puts all the cats over here and all the dogs over here. Right? So if these are all cats and these are all dogs, then this has a standard deviation of 0 and this has a standard deviation of 0. Whereas this is like a totally random mix of cats and dogs, this is a totally random mix of cats and dogs, they're going to have a much higher standard deviation. That makes sense? And so it turns out if you find a split that minimizes those group standard deviations, or specifically the weighted average of the two standard deviations, it's mathematically the same as minimizing the root mean squared error. That's something you can prove to yourself after class if you want to. All right, so we're going to need to find, first of all, split this into two groups. So where's all the stuff that is greater than 3? So greater than 3 is this one, and this one. So we need the standard deviation of that. So let's go ahead and say standard deviation of greater than 3. That one, and that one. Okay? And then the next will be the standard deviation of less than or equal to 3. So that would be that one, that one, that one. And then we just take the weighted average of those two. And that's our score. That would be our score if we split on 3. Does that make sense? And so then the next step would be try to split on 4, try splitting on 1, try splitting on 6, redundantly try splitting on 4 again, redundantly try splitting on 1 again, and find out which one works best. So that's our code here, is we're going to go through every row, and so let's say, okay, left-hand side is any values in X that are less than or equal to this particular value. Our right-hand side is every value in X that are greater than this particular value. Okay, so what's the data type that's going to be in LHS and RHS? What are they actually going to contain? They're going to be arrays. Arrays of what? Arrays of Booleans. Yeah, which we can treat as 0 and 1. Okay, so LHS will be an array of false every time it's not less than or equal to and true otherwise, and RHS will be a Boolean array of the opposite. Okay, and now we can't take a standard deviation of an empty set, right? So if there's nothing that's greater than this number, then these will all be false, which means the sum will be 0. Okay, and in that case, let's not go any further with this step because there's nothing to take the standard deviation of, and it's obviously not a useful split. Okay, so assuming we've got this far, we can now calculate the standard deviation of the left-hand side and of the right-hand side, and take the weighted average, or the sum, it's the same thing, to a scalar, right? And so there's our score. And so we can then check, is this better than our best score so far? And our best score so far, we initialized it to infinity, right? So initially this is better. So if it's better, let's store away all of the information we need. Which variable has found this better split? What was the score we found? And what was the value that we split on? Okay, so there it is. So if we run that, and I'm using timeit, so what timeit does is it sees how long this command takes to run, and it tries to give you a kind of statistically valid measure of that. So you can see here it's run it 10 times to get an average, and then it's done that 7 times to get a mean and standard deviation across runs, and so it's taking me 75 milliseconds plus or minus 10. Okay. So let's check that this works. Find bladder split tree 0. So 0 is year made, 1 is machine hours current meter. So with 1, we got back machine hours current meter 3744 with this score, and then we ran it again with 0, that's year made, and we got a better score, 658, and split 1974. And so 1974, let's compare. Yep, that was what this tree did as well. Okay, so we've confirmed that this method is giving the same result that sklearn's random forest did. Okay, and you can also see here the value 10.08, and again matching here the value 10.08. Okay, so we've got something that can find one split. Could you pass that to Yannet, please?
So Jeremy, why don't we put a unique on the X there?
Because I'm not trying to optimize the performance yet.
But you see that, no? Like he's doing more.
Yeah, so it's like you can see in the Excel, I like checked this 1 twice, I checked this 4 twice unnecessarily. Yeah. Okay. So and so Yannet's already thinking about performance, which is good. So tell me, what is the computational complexity of this section of the code? And like have a think about it, but also like feel free to talk us through it if you want to kind of think and talk at the same time. So what's the computational complexity of this piece of code? Can I pass it over there? Yes. All right, Jade, take us through your thought process.
I think you have to take each different values through the column to calculate it once to see the splits.
Mm-hmm.
So and then compare all the possible combinations between these different values. So that can be expensive. Like, because you're...
Can you, or does somebody else want to tell us the actual computational complexity? So, like, yeah, quite high, Jade's thinking. How high?
I think it's n squared.
Okay, so tell me why is it n squared?
Because for the for loop it is n.
Yes.
And I think I guessed the standard deviation will take n, so it's n squared.
Okay, or this one maybe is even easier to know. Like, this is like, which ones are less than xi?
Yeah,
I'm going to have to check every value to see if it's less than xi. Okay, and so it's useful to know, like, how do I quickly calculate computational complexity? I can guarantee most of the interviews you do are going to ask you to calculate computational complexity on the fly. And it's also like when you're coding, you want it to be second nature. So the technique is basically, is there a loop? Okay, we're obviously doing this n times. Okay, so there's an n involved. Is there a loop inside the loop? If there is, then you need to multiply those two together. In this case, there's not. Is there anything inside the loop that's not a constant time thing? So you might see a sort in there, and you just need to know that sort is n log n, like that should be second nature. If you see a matrix multiply, you need to know what that is. In this case, there are some things that are doing element-wise array operations, right? So keep an eye out for anything where numpy is doing something to every value of an array. In this case, it's checking every value of x against a constant. So it's going to have to do that n times. So to flesh this out into a computational complexity, you just take the number of things in the loop and you multiply it by the highest computational complexity inside the loop. N times n is n squared. You pass that.
In this case, couldn't we just pre-sort the list and then do like one n log n computation?
There's lots of things we can do to speed this up. So at this stage, it's just like, what is the computational complexity we have? But absolutely, it's certainly not as good as it can be. Okay, so and that's where we're going to go next. It's like, all right, n squared is not great, so let's try and make it better. So here's my attempt at making it better. And the idea is this. Okay, who wants to first of all tell me what's the equation for standard deviation? Masha, can you grab the box?
So for the standard deviation, it's the difference between the value and its mean. We take a square root of that. We take the power of 2.
Yep.
Then we sum up all of these observations, and we take the square root out of all this sum.
Yeah, you have to divide by n. So, yep, great. Good, okay. Now, in practice, we don't normally use that formulation because it kind of requires us calculating, x minus the mean lots of times. Does anybody know the formulation that just requires x and x squared? Anybody happen to know that one? Yes, at the back. Do you want to pass that back there?
Square root of a mean of squares minus square of mean.
Yeah, great. Mean of squares minus the square of the means. All right. So that's a really good one, divided by n. That's a really good one to know because, like, you can now calculate variances or standard deviations of anything. You just have to, first of all, grab the column as it is, the column squared, right? And as long as you've got those stored away somewhere, you can immediately calculate the standard deviation. So the reason this is handy for us is that if we first of all sort our data, right? So let's go ahead and sort our data. Then if you think about it, as we kind of start going down one step at a time, right, then each group is exactly the same as the previous group on the left-hand side with one more thing in it, and on the right-hand side with one less thing in it. And so given that we just have to keep track of sum of x and sum of x squared, we can just add one more thing to x squared on the left, and remove one thing on the right. Okay, so we don't have to go through the whole lot each time, and so we can turn this into a order n algorithm. So that's all I do here, is I sort the data, right, and I'm going to keep track of the count of things on the right, the sum of things on the right, and the sum of squareds on the right, and initially everything's on the right-hand side. Okay, so initially n is the count, y sum is the sum on the right, and y squared sum is the sum of squares on the right. And then nothing is initially on the left, so it's zeros. Okay, and then we just have to loop through each observation, right, and add 1 to the left-hand count, subtract 1 from the right-hand count. Add the value to the left-hand count, subtract it from the right-hand count. Add the value squared to the left-hand, subtract it from the right-hand. Okay? Now, we do need to be careful, though, because if we're saying less than or equal to 1, say, we're not stopping here, we're stopping here. Like, we have to have everything in that group. So the other thing I'm going to do is I'm just going to make sure that the next value is not the same as this value. If it is, I'm going to skip over it, right? So I'm just going to double check that this value and the next one aren't the same. Okay? So as long as they're not the same, I can keep going ahead and calculate my standard deviation now, passing in the count, the sum, and the sum squared, right? And there's that formula. Okay? The sum of squared divided by the square of the sum. Sorry, minus the square of the sum. Do that for the right-hand side, and so now we can calculate the weighted average score, just like before, and all of these lines are now the same. Okay, so we've turned our order n squared algorithm into an order n algorithm, and in general, stuff like this is going to get you a lot more value than like pushing something onto a Spark cluster, or ordering faster RAM, or using more cores in your CPU, or whatever, right? This is the way you want to be, improving your code, and specifically write your code, right, without thinking too much about performance. Run it. Is it fast enough for what you need? Then you're done. If not, profile it, right? So in Jupyter, instead of saying %time it, you say %prun, and it will tell you exactly where the time was spent in your algorithm. And then you can go to the bit that's actually taking the time and think about, like, okay, is this algorithmically as efficient as it can be? Okay? So in this case, we run it, and we've gone down from 76 milliseconds to less than 2 milliseconds. And now some people that are new to programming think like, oh great, I've saved 60-something milliseconds. But the point is, this is going to get run like tens of millions of times. Okay, so the 76 millisecond version is so slow that it's going to be impractical for any random forest you use in practice, right? Whereas the 1 millisecond version I found is actually quite acceptable. And then check the numbers should be exactly the same as before. And they are. Okay. So now that we have a function, find better split, that does what we want, I want to insert it into my decision tree class. And this is a really cool Python trick. Python does everything dynamically, right? So we can actually say the method called find better split in decision tree is that function I just created. And that like sticks it inside that class. Right? Now, I'll tell you what's slightly confusing about this is that this word here and this word here, they actually have no relationship to each other. They just happen to have the same letters in the same order, right? So like I could call this find better split _ foo, right? And then I could like call that, right? And call that, right? So now my function is actually called find better split _ foo, but my method, I'm expecting to call something called decision tree.find better split, right? So here I could say decision tree.find better split equals find better split _ foo. Okay, you see that's the same thing, right? So like, it's important to understand how namespaces work. Like in every language that you use, one of the most important things is kind of understanding how it figures out what a name refers to. So this here means find better split as defined inside this class, right? And nowhere else. right? Well, I mean, a parent class, but never mind about that. This one here means find better split foo in the global namespace. A lot of languages don't have a global namespace, but Python does, okay? And so the two are, like, even if they happen to have the same letters in the same order, they're not referring in any way to the same thing. Does that make sense? It's like this family over here may have somebody called Jeremy, and my family has somebody called Jeremy, and our names happen to be the same, but we're not the same person. Okay? Great. So now that we've stuck the decision tree, the find better split method inside the decision tree with this new definition, when I now call the tree ensemble constructor, right, the tree ensemble constructor called create tree instantiated decision tree called find var split, which went through every column to see if it could find a better split, and we've now defined find better split, and therefore tree ensemble, when we create it, has gone ahead and done the split. Does that make sense? Does anybody have any questions or uncertainties about that? Like, we're only creating one single split so far. All right, so this is pretty neat, right? We kind of just do a little bit at a time, testing everything as we go. And so it's, as you all implement the random forest interpretation techniques, you may want to try programming this way to, like, every step check that, you know, what you're doing matches up with what scikit-learn does, or with a test that you've built, or whatever. So at this point, we should try to go deeper. Very inception, right? So let's go now, max depth is 2. And so here is what scikit-learn did. After breaking at year made 74, it then broke at machine hours meter 2956. So we had this thing called find var split, right? We just went through every column and tried to see if there was a better split there, right? But actually, we need to go a bit further than that. Not only do we have to go through every column and see if there's a better split in this node, but then we also have to see whether there's a better split in the left and the right sides that we just created, right? Or in other words, the left, right side and the right-hand side should become decision trees themselves, right? So there's no difference at all between what we do here to create this tree and what we do here to create this tree, other than this one contains 159 samples and this one contains 1,000. So this row of code is exactly the same as we had before, right? And then we check, actually we could do this a little bit easier. We could say if self dot is leaf, right? Would be the same thing. Okay, but I'll just leave it here for now. So is self dot score. So if the score is infinite still, in fact, let's write it properly. Is leaf. So let's go back up and just remind ourselves. Is leaf is self dot score equals inf. Okay. So since it's there, we might as well use it. So if it's a leaf node, then we have nothing further to do, right? So that means we're right at the bottom. There's no split that's been made. Okay, so we don't have to do anything further. On the other hand, if it's not a leaf node, so it's somewhere back earlier on, then we need to split it into the left-hand side and the right-hand side. Now, earlier on, we created a left-hand side and a right-hand side array of Booleans, right? Now, better would be to have an array of indexes, and that's because we don't want to have a full array of all the Booleans in every single node, right? Because remember, although it doesn't look like there are many nodes when you see a tree of this size, when it's fully expanded, the bottom level, if there's a minimum leaf size of 1, contains the same number of nodes as the entire data set. And so if every one of those contained a full Boolean array of size of the whole data set, you've got squared memory requirements, which would be bad, right? On the other hand, if we just store the indexes of the things in this node, then that's going to get smaller and smaller, okay? So np.non-zero is exactly the same as just this thing which gets the Boolean array, but it turns it into the indexes of the trues, Okay, so this is now a list of indexes for the left-hand side and indexes for the right-hand side. Right? So now that we have the indexes for the left-hand side and the right-hand side, we can now just go ahead and create a decision tree. Right? So there's a decision tree for the left, and there's our decision tree for the right. Okay, and we don't have to do anything else. We've already written these. We already have a function, a constructor that can create a decision tree. So, like, when you really think about what this is doing, it kind of hurts your head, right? Because the whole reason that find var split got called is because find var split is called by the decision tree constructor. But then the decision tree, but then find var split itself then calls the decision tree constructor. So we actually have circular recursion. And I'm not nearly smart enough to be able to think through recursion, so I just choose not to, right? Like, I just write what I mean, and then I don't think about it anymore, right? Like, what do I want? Well, to find a variable split, I've got to go through every column, see if there's something better. If it managed to do a split, figure out the left-hand side and the right-hand side, and make them into decision trees. Okay? Like, now trying to think through how these two methods call each other would just drive me crazy, but I don't need to, right? I know I have a decision tree constructor that works, right? I know I have a find var split that works, so that's it, right? That's how I do recursive programming, is by pretending I don't. Right? Just ignore it. That's my advice. Right? A lot of you are probably smart enough to be able to think through it better than I can, so that's fine if you can. All right. So now that I've written that, again, I can patch it into the decision tree class. And as soon as I do, the tree ensemble constructor will now use that, right? Because Python's dynamic, right? That just happens automatically. So now I can check my left-hand side should have 159 samples, right? And a value of 9.66. There it is, 159 samples, 9.66. The right-hand side, 841, 10.15. The left-hand side of the left-hand side, 150 samples, 9.62. 150 samples, 9.62. Okay, so you can see, like, because I'm not nearly clever enough to write machine learning algorithms, like, not only can I not write them correctly the first time, often, like, every single line I write will be wrong, right? So I always start from the assumption that the line of code I just typed is almost certainly wrong, and I just have to see why and how, right? And so, like, I just make sure. And so eventually I get to the point where, like, much to my surprise, it's not broken anymore, you know? So here I can feel like, okay, it would be surprising if all of these things accidentally happen to be exactly the same as scikit-learn. So this is looking pretty good. Okay? So now that we have something that can build a whole tree, we want to have something that can calculate predictions. Right? And so to remind you, we already have something that calculates predictions for a tree ensemble by calling tree.predict. But there is nothing called tree.predict. So we're going to have to write that. Okay. To make this more interesting, let's start bringing up the number of columns that we use. Let's create our tree ensemble again. And this time, let's go to a maximum depth of 3. Okay, so now our tree is getting more interesting. And let's now define how do we create a set of predictions for a tree. And so a set of predictions for a tree is simply the prediction for a row for every row. That's it, right? That's our predictions. So the predictions for a tree are every row's predictions in an array. Okay. So again, we're like skipping thinking. Thinking's hard, you know, so let's just like keep pushing it back. This is kind of handy, right? Notice that you can do for blah in array with a NumPy array, regardless of the rank of the array, regardless of the number of axes. in the array. And what it does is it will loop through the leading axis, right? And these concepts are going to be very, very important as we get into more and more neural networks, because we're going to be all doing tensor computations all the time. So the leading axis of a vector is the vector itself. The leading axis of a matrix are the rows. The leading axis of a three-dimensional tensor are the matrices that represent the slices, and so forth, right? So in this case, because X is a matrix, this is going to loop through the rows. And if you write your kind of tensor code this way, then it'll kind of tend to generalize nicely to higher dimensions. Like, it doesn't really matter how many dimensions are in X. This is going to loop through each of the leading axis, right? Okay, so we can now call that decision tree.predict. Right, so all I need to do is write predict row, right? And I've delayed thinking so much, which is great, that the actual point where I actually have to do the work, it's now basically trivial. So if we're at a leaf node, then the prediction is just equal to whatever that value was, which we calculated right back in the original tree constructor. It's just the average of the y's, right? If it's not a leaf node, then we have to figure out whether to go down the left-hand path or the right-hand path to get the prediction, right? So if this variable in this row is less than or equal to the amount we decided to split on, then we go down the left path. Otherwise, we go down the right path. Okay? And then having figured out what path we want, which tree we want, then we can just call predict row on that, right? And again, we've accidentally created something recursive. And again, I don't want to think about how that works control flow wise or whatever, but I don't need to, because like it just does, like I just told it what I wanted, so I'll trust it to work, right? If it's a leaf, return the value, otherwise return the prediction for the left-hand side or the right-hand side as appropriate. Okay. Notice this here. This if has nothing to do with this if. Right, this if is a control flow statement that tells Python to go down that path or that path to do some calculation. This if is an operator that returns a value. So those of you that have done C or C++ will recognize it as being identical to that. It's called the ternary operator, right? If you haven't, that's fine. Basically, what we're doing is we're going to get a value where we're going to say it's this value if this thing is true, and that value otherwise. And so you could write it this way, right? But that would require writing 4 lines of code to do one thing. It would also require you to have code that if you read it to yourself or to somebody else is not at all naturally the way you would express it, right? I want to say the tree I'm going to go down is the left-hand side if the variable's less than the split, or the right-hand side otherwise, right? So I want to write my code the way I would think about or the way I would say my code, okay? So this kind of ternary operator can be quite helpful for that. All right. So now that I've got a prediction for a row, I can dump that into my class. And now I can calculate predictions. And I can now plot my actuals against my predictions. When you do a scatter plot, you'll often have a lot of dots sitting on top of each other. So a good trick is to use alpha. Alpha means how transparent the things, not just in Matplotlib, but like in every graphics package in the world pretty much. And so if you set alpha to less than 1, then this is saying you would need 20 dots on top of each other for it to be fully blue. And so this is a good way to kind of see how much things are sitting on top of each other. So it's a good trick for scatter plots. There's my R squared, not bad. And so let's now go ahead and do a random forest with no max amount of splitting. And our tree ensemble had no max amount of splitting. We can compare our R squared to their R squared. And so they're not the same, but actually ours is a little better. So I don't know what we did differently, but we'll take it. Okay, so we have now something which for a forest with a single tree in is giving as good accuracy on a validation set using an actual real-world data set, bulldogs for bulldozers, compared to scikit-learn. So let's go ahead and round this out. So what I would want to do now is to create a package that has this code in. And I created it by creating a method here, a method here, a method here, and patching them together. So what I did now is I went back through my notebook and collected up all the cells that implemented methods and pasted them all together, right? And I've just pasted them down here. So this is my original tree ensemble. And here is all the cells from the decision tree. I just dumped them all into one place without any change. So that was it. That was the code we wrote together. So now I can go ahead and I can create a tree ensemble. I can calculate my predictions. I can do my scatter plot. I can get my R squared, right? And this is now with 5 trees, right? And here we are. We have a model of Blue Duck for bulldozers with a 71% R squared. With a random forest we wrote entirely from scratch. So that's pretty cool. Any questions about that? And I know there's quite a lot to get through, so during the week, feel free to ask on the forum about any bits of code you come across. Can somebody pass the box to Masha? Oh, there it is.
Can we get back to the, probably to the top, or maybe at the decision tree when we set the score equal to infinity, right?
Yes.
Do we calculate this score further? I mean, I lost track of that. And specifically, I wonder, when we implement find var split, we check for self-score equal to whether it's equal to infinity or not. It seems to me, it seems unclear whether we fall out of this. I mean, if we ever implement the method, if our initial value is infinity.
Okay, let's talk through the logic. So the decision tree starts out with a score of infinity. So in other words, at this point, when we've created the node, there is no split, so it's infinitely bad. Okay? So that's why the score is infinity. And then we try to find a variable and a split that is better. And to do that, we loop through each column and say, hey, column, do you have a split which is better than the best one we have so far? And so then we implement that. Let's do the slow way, since it's a bit simpler. Find better split. We do that by looping through each row and finding out, this is the current score, if we split here. Is it better than the current score? The current score is infinitely bad, so yes it is. And so now we set the new score equal to what we just calculated, and we keep track of which variable we chose and the split we split on. Okay, no worries. Okay, great. Let's take a 5-minute break, and I'll see you back here at 22. So when I tried comparing the performance of this against scikit-learn, this is quite a lot slower. And the reason why is that although a lot of the work's been done by NumPy, which is nicely optimized C code, think about the very bottom level of a tree. If we've got 1 million data points, then the bottom level of the tree has something like 500,000 decision points with 1 million leaves underneath, right? And so that's 500,000 split methods being called, each one which contains multiple calls to NumPy, which only have like one item that's actually being calculated on. And so it's like, that's like very inefficient. And it's the kind of thing that Python is particularly not good at performance-wise, right? Like calling lots of functions lots of times. I mean, we can see it's not bad, right? You know, for a kind of a random forest which 15 years ago would have been considered pretty big, this would be considered pretty good performance, right? But nowadays this is some hundreds of times at least slower than it should be. So what the scikit-learn folks did to avoid this problem was that they wrote their implementation in something called Cython. And Cython is a superset of Python. So any Python you've written, pretty much, you can use as Cython, right? But then what happens is Cython runs it in a very different way. Rather than passing it to the kind of the Python interpreter, it instead converts it to C, compiles that, and then runs that C code, right? Which means the first time you run it, it takes a little longer because it has to go through the kind of translation and compilation. But then after that, it can be quite a bit faster. And so I wanted just to quickly show you what that looks like, because you are absolutely going to be in a position where Cython's going to help you with your work, and most of the people you're working with will have never used it, may not even know it exists, and so this is like a great superpower to have. So to use Cython in a notebook, you say load extension Cython, right? And so here's a Python function, fib1. Here is the same as a Cython function. It's exactly the same thing with %% at the top. This actually runs about twice as fast as this, right? Just because it does the compilation. Here is the same version again, where I've used a special Cython extension called cdef, which defines the C data type of the return value and of each variable, right? And so basically that's the trick that you can use to start making things run quickly, right? And at that point, now it knows it's not just some Python object called T. In fact, I probably should put one here as well. Let's try that. So we've got fib2, we'll call that fib3. So for fib3, yeah, so it's exactly the same as before, but we say what the data type of the thing we passed to it is, and then define the data types of each of the variables. And so then if we call that, okay, we've now got something that's 10 times faster, right? So yeah, it doesn't really take that much extra, and it's just Python with a few little bits of markup. So that's like, it's good to know that that exists, because if there's something custom you're trying to do, it's actually, I find it kind of painful having to go out and, you know, go into C and compile it and link it back and all that, whereas doing it here is pretty easy. Can you pass that just to your right, please, Masha?
So when you're doing, like, for the Cython version of it, so in the case of an array, for an MP array, is there a specific C type of...
Yeah, so there's like a lot of specific stuff for integrating Cython with NumPy, and there's a whole page about it. Yeah, so we won't worry about going over it, but you can read that and you can basically see the basic ideas. There's this C import, which basically imports certain types of Python library into the kind of the C bit of the code, and you can then use it in your Cython. So, yeah, it's pretty straightforward. Oh, good question. Thank you. All right, so your mission now is to implement confidence based on tree variance, feature importance, partial dependence, and tree interpreter for that random forest. Removing redundant features doesn't use a random forest at all, so you don't have to worry about that. Extrapolation is not an interpretation technique, so you don't have to worry about that. So it's just the other ones. So confidence based on tree variance, we've already written that code, so I suspect that the exact same code we have in the notebook should continue to work. So you can try and make sure get that working. Feature importance is with the variable shuffling technique. And once you have that working, partial dependence will just be a couple of lines of code away, because rather than shuffling a column, you're just replacing it with a constant value. Right? But it's nearly the same code. And then tree interpreter is going to require you writing some code and thinking about that. But once you've written tree interpreter, you're very close, if you want to creating the second approach to feature importance, the one where you add up the importance across all of the rows, which means you would then be very close to doing interaction importance. So it turns out that there's actually a very good library for interaction importance for XGBoost, but there doesn't seem to be one for random forest. So you could start by getting it working on our version, and if you want to do interaction importance, and then you could get it working on the original sklearn version, and that would be a cool contribution. Right? Sometimes writing it against your own implementation is kind of nicer because you can see exactly what's going on. All right. So that's your job. You don't have to rewrite the random forest. Feel free to if you want to, practice. So if you get stuck at any point, ask on the forum, right? There is a whole page here on wiki.fast.ai about how to ask for help. So when you ask your co-workers on Slack for help, when you ask people in a technical community on GitHub or Discourse for help or whatever, asking for help the right way will go a long way towards, having people want to help you and be able to help you, right? So search for your answer, search for the error you're getting, see if somebody's already asked about it. How have you tried to fix it already? What do you think's going wrong? What kind of computer are you on? How is it set up? What are the software versions? Exactly what did you type and exactly what happened, right? Now, you could do that by taking a screenshot. So, make sure you've got some screenshot software that's really easy to use. So if I were to take a screenshot, I just hit a button, select the area, copy to clipboard, go to my forum, paste it in, and there we go, right? That looks a little bit too big, so let's make it a little smaller, right? And so now I've got a screenshot, people can see exactly what happened. Better still, if there's a few lines of code and error messages to look at, create a gist. A gist is a handy little GitHub thing which basically lets you share code. So if I wanted to create a gist of this, I actually have a extension. There we are, that little extension. So if I click on here, give it a name, say make public, right? And that takes my Jupyter notebook, shares it publicly. I can then grab that URL, copy link location, right? And paste it into my forum post, right? And then when people click on it, then they'll immediately see my notebook when it renders. Okay, so that's a really good way. Now, that particular button is an extension. So on Jupyter, you need to click NV extensions and click on Gist it, right? While you're there, you should also click on collapsible headings. That's this really handy thing I use that lets me collapse things and open them up. If you go to your Jupyter and don't see this NV extensions button, then just Google for Jupyter NV extensions. It'll show you how to pip install it and and get it set up, right? But those two extensions are super duper handy. All right. So other than that assignment, we're done with random forests, and until the next course, when you look at GBMs, we're done with decision tree ensembles. And so we're going to move on to neural networks broadly defined. And so neural networks are going to allow us to go beyond just, the kind of nearest neighbors approach of random forests. All a random forest can do is to average data that it's already seen. It can't extrapolate. It can't calculate, right? Linear regression can calculate and can extrapolate, but only in very limited ways. Neural nets give us the best of both worlds. We're going to start by applying them to unstructured data, right? So unstructured data means like pixels or the amplitudes of sound waves or words, data where everything in all the columns are all of the same type, as opposed to like a database table where you've got like a revenue and a cost and a zip code and a state. It should be structured data. Okay. We're going to use it for structured data as well, but we're going to do that a little bit later. So unstructured data is a little easier, and it's also the area which more people have been applying deep learning to for longer. If you're doing the deep learning course as well, you'll see that we're going to be approaching kind of the same conclusion from two different directions. So the deep learning course is starting out with big, complicated convolutional neural networks being solved with, sophisticated optimization schemes, and we're going to kind of gradually drill down into like exactly how they work. Whereas with the machine learning course, we're going to be starting out more with like, how does stochastic gradient descent actually work? What do we do? What can we do with like one single layer, which would allow us to create things like logistic regression? When we add regularization to that, how does that give us things like ridge regression, elastic net, lasso? And then as we add additional layers to that, how does that let us handle more complex problems? And so we're only going to be looking at fully connected layers in this machine learning course. And then I think next semester with your net, you're probably going to be looking at some more sophisticated approaches. And so, so in this machine learning, we're going to be looking much more at like what's actually happening with the matrices and how are they actually calculated. And the deep learning, it's much more like what are the best practices for actually solving, at a world-class level, real-world deep learning problems, right? So next week, we're going to be looking at like the classic MNIST problem, which is like, how do we recognize digits? Now, if you're interested, you can like skip ahead and like try and do this with a random forest, and you'll find it's not bad. Right? Given that a random forest is basically a type of nearest neighbors, right? It's finding like what are the nearest neighbors in tree space. Then a random forest could absolutely recognize that this 9, those pixels, are similar to pixels we've seen in these other ones, and on average they were 9s as well, right? And so like we can absolutely solve these kinds of problems to an extent using random forests. But we end up being rather data limited because every time we put in another decision point, we're halving our data roughly. And so there's just this limitation in the amount of calculation that we can do. Whereas with neural nets, we're going to be able to use lots and lots and lots of parameters using these tricks we're going to learn about with regularization. So we're going to be able to do lots of computation, and there's going to be very little limitation on really what we can actually end up calculating as a result. Great. Good luck with your random forest interpretation, and I will see you next time. So I I don't want to embarrass Rachel, but I'm very excited that Rachel's here. So this is Rachel, for those of you that don't know. She's not quite back on her feet after her illness, but well enough to at least come to at least part of this lesson. So don't worry if she can't stay for the whole thing. And I'm really glad she's here because Rachel actually wrote the vast majority of the lesson we're going to see. I think it's a really, really cool work. So I'm glad she's going to at least see it being taught, even if unfortunately she's not teaching it herself. So it's coming. Good Thanksgiving present. Best Thanksgiving present. So we're, as we discussed at the end of last lesson, we're kind of moving from the decision tree ensembles to neural nets, broadly defined. And as we discussed, random forests and decision trees are limited by the fact, in the end, that they're basically doing nearest neighbors, right? That all they can do is to return the average of a bunch of other points. And so they can't extrapolate out to, if you're thinking, what happens if I increase my prices by 20%, and you've never priced at that level before, or what's going to happen to sales next year? And obviously we've never seen next year before. It's very hard to extrapolate. It's also hard if it needs to, it can only do around log base 2n decisions, and so if there's like a time series it needs to fit to that takes like 4 steps to kind of get to the right time area, then suddenly there's not many decisions left for it to make. So there's kind of this limited amount of computation that it can do. So there's a limited complexity of relationship that it can model, right? Yes, Prince.
Can I ask about one more drawback of random forest that I feel? So if we have data as categorical variable which are not in sequential order, so for random forest we encode them and treat them as numbers. Let's say we have 20 cardinality and 1 to 20. So the result that random forest gives is like the split that random forest gives is something like less than 5, less than 6. But if the categories are not sequential, not in any order, what does that mean?
Yeah, so if you've got like, I don't know, let's go back to bulldozers. EROPS with a C, OROPS, and I don't know, whatever, right? And we arbitrarily label them like this, right? And so actually we know that all that really mattered was if it had air conditioning. So what's going to happen? Well, it's basically going to say like, okay, if I group it into those together and those together, that like, that's an interesting break, just because it so happens that the air conditioning ones all are going to end up in the right-hand side. And then having done that, right, it's then going to say, okay, well, within the group with the 2 and 3, it's going to notice that it's furthermore going to have to split it into 2 more groups. So eventually it's going to get there. It's going to pull out that category. It's going to take more splits than we would ideally like. So it's kind of similar to the fact that for it to model a line, it can only do it with lots of splits and only approximately.
So random forest is fine with categories that are not sequential also.
Yeah, so it can do it. It's just like in some way it's suboptimal because we just need to do more breakpoints than we would have liked. But it gets there. It does a pretty good job. And so even although random forests, do have some deficiencies, they're incredibly powerful, particularly because they have so few assumptions, they're really hard to screw up. And, it's kind of hard to actually win a Kaggle competition with a random forest, but it's very easy to get like top 10%. So in real life, where often that third decimal place doesn't matter, random forests are often like what you end up doing. But for some things like this Ecuadorian groceries competition, it's very, very hard to get a good result with a random forest, because there's a huge time series component, and nearly everything is these 2 massively high cardinality categorical variables, which is the store and the item, and so there's very little there to even throw at a random forest, and the the difference between every pair of stores is kind of different in different ways. And so, there are some things that are just hard to get even relatively good results with a random forest. Another example is recognizing numbers. You can get okay results with a random forest, but in the end, the relationship between, the spatial structure turns out to be important, right? And you kind of want to be able to do computations, like finding edges or whatever, that kind of carry forward through the computation. So, just doing a clever nearest neighbors, like a random forest, turns out not to be ideal. So for stuff like this, neural networks turn out that they are ideal. Neural networks turn out to be something that works particularly well for both things like the Ecuadorian groceries competition, so forecasting sales over time by store and by item, and for things like recognizing digits, and for things like turning voice into speech. And so it's kind of nice between these two things, neural nets and random forests, we kind of cover the territory, right? I haven't needed to use anything other than these two things for a very long time. And we'll actually learn, I don't know in what course exactly, but at some point we'll learn also how to combine the two, because you can combine the two in really cool ways. So here's a picture from Adam Geitke of an image. So an image is just a bunch of numbers, right? And each of those numbers is 0 to 255, and the dark ones are close to 255, the light ones are close to 0. All right. So here is an example of a digit from this MNIST dataset. MNIST is a really old, it's like the hello world of neural networks. And so here's an example. And so there are 28 by 28 pixels. If it was color, there would be 3 of these, one for red, one for green, one for blue. Okay. So our job is to look at, the array of numbers and figure out that this is the number 8, which is tricky, right? How do we do that? So we're going to use a small number of FastAI pieces, and we're gradually going to remove more and more and more until by the end we'll have implemented our own neural network from scratch, our own training loop from scratch, and our own matrix multiplication from scratch. So we're gradually going to dig in further and further. All right, so the data for MNIST, which is the name of this very famous data set, is available from here. And we have a thing in fastai.io called getData, which will grab it from a URL and store it on your computer, unless it's already there, in which case it'll just go ahead and use it. Okay, and then we've got a little function here called loadMNIST, which simply loads it up. You'll see that it's zipped, so we can just use Python's gzip to open it up. And then it's also pickled. So if you have any kind of Python object at all, you can use this built-in Python library called pickle to dump it out onto your disk, share it around, load it up later, and you get back the same Python object you started with. So you've already seen this, something like this with pandas feather format, right? Pickle is not just for pandas, it's not just for anything, it works for basically nearly every Python object. So, which might lead to the question, well, why didn't we use pickle for a pandas data frame, right? And the answer is, pickle works for nearly every Python object, but it's probably not optimal for nearly any Python object, right? So because we were looking at pandas data frames with over 100 million rows, we really want to save that quickly, and so feather is a format that's specifically designed for that purpose, and so it's going to do that really fast. If we tried to pickle it, it would have taken a lot longer, right? Also note that pickle files are only for Python, so you can't give them to somebody else, whereas a feather file you can hand around. Okay, so it's worth knowing that pickle exists, because if you've got some dictionary or some kind of object floating around that you want to save for later or send to somebody else, you can always just pickle it. Okay. So in this particular case, the folks at deeplearning.net were kind enough to provide a pickled version. Pickle has changed slightly over time. And so old pickle files like this one, you actually have to, this was a Python 2 one. So you have to tell it that it was encoded using this particular Python 2 character set. But other than that, Python 2 and 3 can normally open each other's pickle files. All right, so once we've loaded that in, we load it in like so. And so this thing which we're doing here, this is called destructuring. And so destructuring means that load_mnist is giving us back a tuple of tuples. And so if we have on the left-hand side of the equal sign a tuple of tuples, we can fill all these things in. So we're given back a tuple of training data, a tuple of validation data, and a tuple of test data. In this case, I don't care about the test data, so I just put it into a variable called underscore, which kind of by like Python people tend to think of underscore as being a special variable which we put things we're going to throw away into. It's actually not special, but it's really common. If you see something assigned to underscore, it probably means you're just throwing it away, right? By the way, in a Jupyter notebook, it does have a special meaning, which is the last cell that you calculate is always available in underscore, by the way. But that's kind of a separate issue. So then the first thing in that tuple is itself a tuple. And so we're going to stick that into X and Y for our training data. And then the second one goes into X and Y for our validation data. Okay, so that's called destructuring. And it's pretty common in lots of languages. Some languages don't support it, but those that do, life becomes a lot easier. So as soon as I look at some new data set, I just check out what have I got, right? So what's its type? Okay, it's a NumPy array. What's its shape? It's 50,000 by 784. And then what about the dependent variables? That's an array. Its shape is 50,000. So this image is not of length 784. It's of size 28 by 28. So what happened here? Well, we could guess, and we can check on the website, it turns out we would be right, that all they did was they took the second row and concatenated it to the first row, and the third row and concatenated to that, and the fourth row and concatenated to that. So in other words, they took this whole 28 by 28 and flattened it out into a single 1D array. Does that make sense? So it's going to be of size 28 squared. This is not like normal by any means, so don't think like everything you see is going to be like this. Most of the time when people share images, they share them as JPEGs or PNGs. You load them up, you get back a nice 2D array. But in this particular case, for whatever reason, the thing that they pickled was flattened out to be 784. Okay. And this word flatten is very common with, kind of working with tensors. So when you flatten a tensor, it just means that you're turning it into a lower rank tensor than you started with. In this case, we started with a rank 2 tensor, a matrix, for each image, and we turned each one into a rank 1 tensor, i.e. a vector. So overall, the whole thing, is a rank 2 matrix, a rank 2 tensor rather than a rank 3 tensor. So just to remind us of, the jargon here, this in math we would call a vector, right? In computer science we would call it a 1D array. But because deep learning people have to come across as smarter than everybody else, we have to call this a rank 1 tensor. Okay. They all mean the same thing, more or less. Unless you're a physicist, in which case this means something else, and you get very angry at the deep learning people because you say it's not a tensor. So there you go. Don't blame me. This is just what people say. So this is either a matrix or a 2D array or a rank 2 tensor. And so once we start to get into 3 dimensions, we start to run out of mathematical names, right? Which is why we start to be nice just to say rank 3 tensor. And so there's actually nothing special about vectors and matrices that make them in any way more important than rank 3 tensors or rank 4 tensors or whatever. So I try not to use the terms vector and matrix where possible, because I don't really think they're any more special than any other rank of tensor. Okay, so kind of it's good to get used to thinking of this as a rank 2 tensor. Okay, and then the rows and columns, if we're computer science people, we would call this dimension 0 and dimension 1. But if we're deep learning people, we would call this axis 0 or axis 1. Okay? And then just to be really confusing, if you're an image person, this is the first axis and this is the second axis. Right? So if you think about like TVs, 1920 by 1080, columns by rows. Everybody else, including deep learning and mathematicians, rows by columns. So this is pretty confusing if you use like the Python imaging library. You get back columns by rows, pretty much everything else, rows by columns. So be careful.
Why did they do that?
Because they hate us. Because they're bad people. I guess. I mean, there's a lot of just, particularly in deep learning, like a whole lot of different areas have come together, like information theory, computer vision, statistics, signal processing, and you've ended up with this hodgepodge of nomenclature in deep learning. Often, like, every version of things will be used. So today we're going to hear about something that's called either negative log likelihood or binomial or categorical cross entropy, depending on where you come from. We've already seen something that's called either one-hot encoding or dummy variables, depending on where you come from. And really it's just like the same concept gets kind of somewhat independently invented in different fields, and eventually they find their way to machine learning, and then we don't know what to call them, so we call them all of the above, something like that. So I think that's what's happened with computer vision rows and columns. So there's this idea of normalizing data, which is subtracting out the mean and dividing by the standard deviation. So a question for you. Do you, often it's important to normalize the data so that we can more easily train a model. Do you think it would be important to normalize the independent variables for a random forest, if we're training a random forest?
To be honest, I don't know why we don't need to normalize. I just know that we don't.
We don't. Okay. Does anybody want to think about why? Kara?
It wouldn't matter because each scaling and transformation we can have will be applied to each row, and we will be computing means as we were doing, like local averages, and at the end we will of course want to denormalize it back to give, so it wouldn't change the result.
I'm talking about the independent variables, not the dependent variable.
I thought you asked about dependent variables.
Okay, who wants to have a go? Matthew.
It might be because we just care about the relationship between the independent variables and the dependent variable, so scale doesn't really matter.
Okay, go on. Why? Why do we only
Because at each split point, we can just divide to see which, regardless of what scale you're on, what minimizes variance, and that would.
Right. So really, the key is that when we're deciding where to split, all that matters is the order. All that matters is how they're sorted. So if we divide by subtract the mean and divide by the standard deviation, they're still sorted in the same order. So remember when we implemented the random forest, we said sort them, and then we completely ignored the values. We just said now add on one thing from the dependent at a time. So random forests only care about the sort order of the independent variables. They don't care at all about their size. And so that's why they're wonderfully immune to outliers, because they totally ignore the fact that it's an outlier. They only care about which one's higher then what other thing, right? So this is an important concept. It doesn't just appear in random forests. It occurs in some metrics as well. For example, area under the ROC curve, you come across a lot. Right? Area under the ROC curve completely ignores scale and only cares about sort. We saw something else when we did the dendrogram. Spearman's correlation is a rank correlation, only cares about order, not about scale. So random forests, one of the many wonderful things about them are that we can completely ignore a lot of these statistical distribution issues. But we can't for deep learning, because for deep learning, we're trying to train a parameterized model. So we do need to normalize our data. If we don't, then it's going to be much harder to create a network that trains effectively. So we grab the mean and the standard deviation of our training data and subtract out the mean, divide by the standard deviation, and that gives us a mean of 0 and a standard deviation of 1. Now, for our validation data, we need to use the standard deviation and mean from the training data, right? We have to normalize it the same way. Just like categorical variables, we had to make sure they had the same indexes mapped to the same levels for a random forest. Or missing values, we had to make sure we had the same median used when we were replacing the missing values. You need to make sure anything you do in the training set, you do exactly the same thing in the test and validation set. So here I'm subtracting out the training set mean, the training set standard deviation. So this is not exactly 0, and this is not exactly 1, but it's pretty close. And so in general, if you find you try something on a validation set or a test set and it's like much, much, much worse than your training set, it's probably because you normalized in an inconsistent way or encoded categories in an inconsistent way or something like that. All right, so let's take a look at some of this data. So we've got 10,000 images in the validation set, and each one is a rank 1 tensor of length 784. In order to display it, I want to turn it into a rank 2 tensor of 28 by 28. So there's NumPy has a reshape function that takes a tensor in and reshapes it to whatever size tensor you request. Now, if you think about it, you only need to tell it about, if there are d axes, you only need to tell it about d minus 1 of the axes you want, because the last one it can figure out for itself, right? So in total, there are 10,000 by 784 numbers here altogether, right? So if you say, well, I want my last axes to be 28 by 28, then you can figure out that this must be 10,000. Otherwise, it's not going to fit. That makes sense? So if you put minus 1, it says, like, make it as big or as small as you have to make it fit. And so you can see here it figured out it has to be 10,000. So you'll see this used in neural net software, pre-processing and stuff like that all the time. Like, I could have written 10,000 here, but I try to get into a habit of, like, any time I'm referring to, like, how many items are in my input, I tend to use minus 1, because, like, it just means later on I could, like, use a subsample, this code wouldn't break. I could, do some kind of stratified sampling. If it was unbalanced, this code wouldn't break. So by using this kind of approach of saying, like, minus 1 here for the size, it just makes it more resilient to changes later. It's a good habit to get into. So this kind of idea of, like, being able to take tensors and reshape them and change axes around and stuff like that is something you need to be, like, totally do without thinking, because it's going to happen all the time. So, for example, here's one. I tried to read in some images. They were flattened. I need to unflatten them into a bunch of matrices. Okay, reshape, bang. I read some images in with OpenCV, and it turns out OpenCV orders the channels blue, green, red. Everything else expects them to be red, green, blue. I need to reverse the last axis. How do you do that? I read in some images with Python imaging library. It reads them as, rows by columns by channels. PyTorch expects channels by rows by columns. How do I transform that? So these are all things you need to be able to do without thinking, like straight away, because it happens all the time. and you never want to be sitting there thinking about it for ages. So make sure you spend a lot of time over the week just practicing with things like all the stuff we're going to see today: reshaping, slicing, reordering dimensions, stuff like that. And so the best way is to create some small tensors yourself and start thinking like, okay, what shall I experiment with? So here, can we pass that over there?
Do you mind if I backtrack a little bit?
Of course, I love it.
So back in normalize, you say, like, you might have gone over this, but I'm still like wrestling with it a little bit.
Yeah.
You say many machine learning algorithms behave better when the data is normalized,
Yeah.
but you also just said that scale doesn't really matter. So like,
I said it doesn't matter for random forests.
okay.
Yeah. So random forests are just going to split things based on order. And so we love them. We love random forests for the way they're so immune to worrying about distributional assumptions. But we're not doing random forests. We're doing deep learning, and deep learning does care.
Can we generalize this?
Can you pass it over there?
If we have a parametric, then we should scale. If we have a non-parametric, then we should know how to scale. Can we generalize?
No, not quite, right? Because like k nearest neighbors is non-parametric, and scale matters a hell of a lot.
Yeah.
So I would say things involving trees generally are just going to split at a point, and so probably you don't care about scale. But you probably just need to think like, is this an algorithm that uses order, or does it use specific numbers?
Can you please give us an intuition of why it needs scale? Just because that may clarify some of the issues.
Not until we get to doing SGD. So we're going to get to that. Yeah. So for now, we're just going to say, take my word for it. Can you pass it to Daniel?
So this is probably a dumb question, but can you explain a little bit more what you mean by scale? Because I guess when I think of scale, I'm like, oh, all the numbers should be generally the same size.
That's exactly what we mean.
But is that the case with the cats and dogs that we went over with the deep learning? You could have a small cat and a larger cat, but it would still know that those were both cats.
Oh, I guess, this is one of these problems where language gets overloaded. Yeah. So in computer vision, when we scale an image, we're actually increasing the size of the cat. In this case, we're scaling the actual pixel values. So in both cases, scaling means to make something bigger and smaller. In this case, we're taking the numbers from 0 to 255 and making them so that they have an average of 0 and a standard deviation of 1.
Jeremy, could you please explain us, is it by column, by row?
By pixel. By pixel.
When
there's a single...
In general, when you're scaling, just not thinking about even a picture, but a kind of an input to a machine learning.
So, okay,
method.
yeah, sure. So, I mean, it's a little bit subtle, but in this case, I've just got a single mean and a single standard deviation, right? So it's basically, on average, how much black is there, right? And so, on average, we have a mean and a standard deviation across all the pixels. In computer vision, we would normally do it by channel. So we would normally have one number for red, one number for green, one number for blue. In general, you need a different set of normalization coefficients for each thing you would expect to behave differently. So if we were doing a structured data set where we've got income, distance in kilometers, and number of children, you need 3 separate normalization coefficients for those. They're very different kinds of things. So yeah, it's kind of a bit domain specific here. It's in this case, all of the pixels are, levels of gray. So we just got a single scaling number. Where else you could imagine if they were red versus green versus blue, you could need to scale those channels in different ways. Can you pass that back, please?
So I'm having a bit of trouble imagining what would happen if we don't normalize in this case.
So we'll get there. So so this is kind of what Yannet was saying. Is why do we normalize? And for now, we're normalizing because I say we have to. When we get to looking at stochastic gradient descent, we'll basically discover that if you basically, to skip ahead a little bit, we're going to be doing a matrix multiply by a bunch of weights. We're going to pick those weights in such a way that when we do the matrix multiply, we're going to try to keep the numbers at the same scale that they started out as. And that's going to basically require the initial numbers. We're going to have to know what their scale is. So basically, it's much easier to create a single kind of neural network architecture that works for lots of different kinds of inputs if we know that they're consistently going to be mean 0, standard deviation 1. That would be the short answer. But we'll learn a lot more about it. And if in a couple of lessons you're still not quite sure why, let's come back to it, because it's a really interesting thing to talk about.
Yes, I'm just trying to visualize the axes we're working with here. So under plots, when you write, so x valid shape, we get 10,000 by 7, 8, 4. Does that mean that we brought in 10,000 pictures of that dimension?
Exactly.
Okay. And then in the next line, when you choose to reshape it, is there a reason why you put 28, 28 on as y or z coordinates, or is there a reason why they're in that order?
Yeah, there is. Pretty much all neural network libraries assume that the first axis is like, it's kind of the equivalent of a row. It's like a separate thing. It's a sentence or an image or a, example of sales or whatever. So I want each image, to be a separate item of the first axis. And then so that leaves 2 more axes for the rows and columns of the images.
And that's pretty standard.
That's totally standard. Yeah, I don't think I've ever seen a library that doesn't work that way. Can you pass it to Abira?
So while normalizing the validation data, I saw you have used mean of x and standard deviation of x data, training data only.
Yes.
So shouldn't we use mean and standard deviation of validation data?
You mean like join them together, or?
No, separately calculating mean?
No, because you see, then you would be normalizing the validation set using different numbers. And so now the meaning of like this pixel has a value of 3 in the validation set has a different meaning to the meaning of 3 in the training set. It would be like if we had like days of the week encoded such that Monday was a 1 in the training set and was a 0 in the validation set. We've got now 2 different sets where the same number has a different meaning. So we want to make sure that so let me give you an example. Let's say we were doing like full color images, and our tests, their training set contained like green frogs, green snakes, and gray elephants, right? We're trying to figure out which was which. And we normalized using, each channel mean. And then we have a validation set and a test set which are just green frogs and green snakes. So if we were to normalize by the validation set's statistics, we would end up saying things on average are green, and so we would like remove all the greenness out. And so we would now fail to recognize the green frogs and the green snakes effectively, right? So we actually want to use the same normalization coefficients that we were training on. And for those of you doing the deep learning class, we actually go further than that. When we use a pre-trained network, we have to use the same normalization coefficients that the original authors trained on. So the idea is that, a number needs to have this consistent meaning across every data set where you use it. Can you pass it to Asmita?
That means when you're looking at the test set, you normalize the test set based on this mean.
That's right.
Okay.
That's right. Okay. So here's so the validation y values are just rank 1 tensor of 10,000. Remember, there's this kind of weird Python thing where a tuple with just one thing in it needs a trailing comma. Okay, so this is a rank 1 tensor of length 10,000, and so here's an example of something from that. It's just the number 3. Right. So that's our labels. So here's another thing you need to be able to do in your sleep, slicing into a tensor. So in this case, we're slicing into the first axis with 0, so that means we're grabbing the first slice. So because this is a single number, this is going to reduce the rank of the tensor by 1. It's going to turn it from a 3-dimensional tensor into a 2-dimensional tensor, right? So you can see here, this is now just a matrix, and then we're going to grab 10 through 14 inclusive rows, 10 through 14 inclusive columns, and here it is, right? So this is the kind of thing you need to be super comfortable, like grabbing pieces out, looking at the numbers, and looking at the picture, right? So here's an example of a little piece of that first image. And so you kind of want to get used to this idea that if you're working with something like pictures or audio, this is something your brain's really good at interpreting, right? So like keep showing pictures of what you're doing whenever you can. But also remember behind the scenes they're numbers. So like if something's going weird, print out a few of the actual numbers. You might find somehow some of them have become infinity, or they're all zero, or whatever, right? So like use this interactive environment and to explore the data as you go. Did you have a question? Where's the box? Oh.
Just a quick, I guess, semantic question. Why, when it's a tensor of rank 3, is it stored as like XYZ instead of, like, to me it would make more sense to store it as like a list of like 2D tensors.
It's not stored as either, right? So
but, like for the formatting, because
let's look at this as a 3D. Okay, so here's a 3D, right? So a 3D tensor is formatted as showing a list of 2D tensors, basically.
But when you're extracting it, why isn't it, like, if you're extracting the first one, why isn't it X images, square bracket 0, close square brackets, and then a second set of square brackets?
Because that has a different meaning, right? So it's kind of the difference between tensors and jagged arrays, right? So basically, if you do like something like that, that says take the second list item and from it grab the third list item. And so we tend to use that when we have something called a jagged array, which is where each subarray may be of a different length, right? Whereas we have like a single object of 3 dimensions. And so we're trying to say like which little piece of it do we want. And so the idea is that that is a single slice object to go in and grab that piece out. Okay. So here's an example of a few of those images along with their labels. And this kind of stuff you want to be able to do pretty quickly with Matplotlib. It's going to help you a lot in life, in your exam. So you can have a look at what Rachel wrote here when she wrote plots. We can use add subplot to basically create those little separate plots. And you need to know that IMShow is how we basically take a NumPy array and draw it as a picture. Okay, and then we've also added the title on top. So there it is. All right. So let's now take that data and try to build a neural network with it. And so a neural network, and sorry, this is going to be a lot of review for those of you already doing deep learning. A neural network is just a particular mathematical function or a class of mathematical functions, but it's a really important class because it has the property, it supports what's called the universal approximation theorem, which means that a neural network can approximate any other function arbitrarily closely, right? So in other words, it can do, in theory, it can do anything as long as we make it big enough. So this is very different to a function like 3x plus 5, right, which can only do one thing. It's a specific function, or the class of functions ax plus b, which can only represent lines of different slopes moving it up and down different amounts, or even the function ax squared plus bx plus c plus sine d, again, only can represent a very specific subset of relationships. The neural network, however, is a function that can represent any other function to arbitrarily close accuracy. Right. So what we're going to do is we're going to learn how to take a function, and so let's take like ax plus b, and we're going to learn how to find its parameters, in this case a and b, which allow it to fit as closely as possible to a set of data. And so this here is showing an example from a notebook that we'll be looking at in the deep learning course, which basically shows what happens when we use something called stochastic gradient descent to try and set A and B. And basically what happens is we're going to pick a random A to start with, a random B to start with, and then we're going to basically figure out, do I need to increase or decrease A to make it closer, the line closer to the dots? Do I need to increase or decrease B to make the line closer to the dots? And then just keep increasing and decreasing A and B lots and lots of times. Okay, so that's what we're going to do. And to answer the question, do I need to increase or decrease A and B, we're going to take the derivative. Right? So the derivative of the function with respect to A and B tells us how will that function change as we change A and B. Right? So that's basically what we're going to do. But we're not going to start with just a line. The idea is we're going to build up to actually having a neural net. And so it's going to be exactly the same idea, but because it's an infinitely flexible function, we're going to be able to use this exact same technique to fit arbitrarily complex relationships. Now, that's basically the idea. So then what you need to know is that a neural net is actually a very simple thing. A neural net actually is something which takes as input, let's say we've got a vector, does a matrix product by that vector, right? So if this is like, this is of size, let's draw this properly. So like if this is size R, this is like R by C, a matrix product will spit out something of size C, right? And then we do something called a nonlinearity, which is basically we're going to throw away all the negative values. So it's basically max 0, x. And then we're going to put that through another matrix multiply. And then we're going to put that through another max 0, x. And we're going to put that through another matrix multiply, and so on, right? Until eventually we end up with the single vector that we want. In other words, each stage of our neural network is the key thing going on is a matrix multiply. So in other words, a linear function. So basically deep learning, most of the calculation is lots and lots of linear functions, but between each one, we're going to replace the negative numbers with zeros. Can you pass it to me? Yes.
So why are we throwing away the negative numbers as we go through this process?
We'll see, right? The short answer is if you apply a linear function to a linear function to a linear function, it's still just a linear function. Okay. So it's totally useless. But if you throw away the negatives, that's actually a non-linear transformation. And so it turns out that if you apply a linear function to the thing where you threw away the negatives and apply that to a linear function, that creates a neural network. And it turns out that's a thing that can approximate any other function arbitrarily closely. So this tiny little difference actually makes all the difference. And if you're interested in it, check out the deep learning video where we cover this, because I actually show a nice visual intuitive proof, not something that I created, but something that Michael Nielsen created. Or if you want to skip straight to his website, you could go to Michael Nielsen, Universal, I think I spelled his name wrong, never mind, Hessian theorem. There we go. Neural Networks and Deep Learning, Chapter 4, and he's got a really nice walkthrough, basically, with lots of animations where you can see why this works. I feel like the hardest thing. I feel like the hardest thing with getting started, like technical writing on the internet, is just like posting your first thing. If you do a search for Rachel Thomas Medium blog, you'll find this. We'll put it on the lesson wiki, where she talks about, she actually says the top advice she would give to her younger self would be to start blogging sooner. And she has like both reasons why you should do it, some examples of things that, examples of places she's blogged and it's turned out to be great for her and her career, but then some tips about how to get started. I remember when I first suggested to Rachel she might think about blogging because she had so much interesting to say. And, at first she was kind of surprised at the idea that, like, she could blog, and now people come up to us at conferences and they're like, oh, you're Rachel Thomas. I love your writing, so like I've kind of seen that transition from like, wow, could I blog to being known as a strong technical author. So check out this article if you still need convincing or if you're wondering how to get started. And since the first one is the hardest, maybe your first one should be like something really easy for you to write, So it could be like, here's a summary of the first 15 minutes of lesson 3 of our machine learning course. Here's why it's interesting, here's what we learned. Or it could be like, here's a summary of how I used a random forest to solve a particular problem in my practicum. I often get questions like, my practicum, my organization, we've got like sensitive commercial data. That's fine. Like, just find another data set and do it on that instead to show the example, or, anonymize all of the values and change the names of the variables or whatever. Like, you can talk to your employer or your practicum partner to make sure that they're comfortable with whatever it is you're writing. In general, though, people love it when their interns and staff blog about what they're working on because it makes them look super cool. It's like, hey, I'm an, intern working at this company and I wrote this post about this cool analysis I did, and then other people will be like, wow, that looks like a great company to work for. So generally speaking, you should find people are pretty supportive. Besides which, there's lots and lots of data sets out there available. So even if you can't base it on the work you're doing, you can find something similar for sure. All right. So we're going to start building our neural network. We're going to build it using something called PyTorch. PyTorch is a library that basically looks a lot like NumPy. But when you create some code with PyTorch, you can run it on the GPU rather than the CPU. So the GPU is something which is basically going to be probably at least an order of magnitude, possibly hundreds of times faster than the code that you might write for the CPU for particularly stuff involving lots of linear algebra. Right? So with deep learning, neural nets, you can, if you don't have a GPU, you can do it on the CPU, right? But it's going to be frustratingly slow. Your Mac does not have a GPU that we can use for this because I'm actually advertising today. We need an NVIDIA GPU. I would actually much prefer that we could use your Macs because competition's great, right? But NVIDIA were really the first ones to create a GPU which did a good job of supporting general purpose graphics programming units, GPU. So in other words, that means using a GPU for things other than playing computer games. They created a framework called CUDA, C-U-D-A. It's a very good framework. It's pretty much universally used in deep learning. If you don't have an NVIDIA GPU, you can't use it. No current Macs have an NVIDIA GPU. Most laptops of any kind don't have an NVIDIA GPU. If you're interested in doing deep learning on your laptop, the good news is that you need to buy one which is really good for playing computer games on. There's a place called Exotic PC gaming laptops where you can go and buy yourself a great laptop for doing deep learning. You can tell your parents that you need the money to do deep learning. So could you please have... Yeah, so you'll generally find a whole bunch of laptops with names like Predator and Viper with pictures of robots and stuff. So Stealth Pro, Raider, Leopard. Anyway, Having said that, like I don't know that many people that do much deep learning on their laptop. Most people will log into a cloud environment. By far the easiest I know of to use is called Crestle. With Crestle, you can basically sign up, and straight away the first thing you get is thrown straight into a Jupyter notebook, backed by a GPU, costs 60 cents an hour, with all of the fast AI libraries and data already available. So that makes life really easy. It's less flexible and in some ways less fast than using AWS, which is the Amazon Web Services option. It costs a little bit more, 90 cents an hour rather than 60 cents an hour. But it's very likely that your employer is already using that. It's good to get to know anyway. They've got more different choices around GPUs, and it's a good choice. If you Google for GitHub Student Pack, if you're a student, you can get $150 of credits straight away, pretty much. And so that's a really good way to get started. Daniel, did you have a question? Yeah, can you pass that to me?
I just wanted to know your opinion on, I know that Intel recently published like an open source way of boosting regular packages that they claim is equivalent, if you use the bottom tier GPU on your CPU, if you use their boost packages, you can get the same performance. Do you know anything about that?
Yeah, I do. Okay. It's a good question. So, and actually Intel makes some great numerical programming libraries, particularly this one called MKL, the matrix kernel library. They definitely make things faster than not using those libraries. But if you look at a graph of performance over time, GPUs have consistently throughout the last 10 years, including now, are about 10 times more floating point operations per second than the equivalent CPU, and they're generally about a fifth of the price for that performance. So, yeah, and then because of that, everybody doing anything with deep learning basically does it on NVIDIA GPUs, and therefore using anything other than NVIDIA GPUs is currently very annoying. So slower, more expensive, more annoying. I really hope there will be more activity around AMD GPUs in particular in this area, but AMD's got literally years of catching up to do, so it might take a while.
Yeah, so I just wanted to point out that you can also buy things such as a GPU extender to a laptop.
Yeah.
That's also kind of maybe a first step solution before you really want to put something on.
Yeah, I think for $300 or so, you can buy something that plugs into your Thunderbolt port if you have a Mac, and then for another $500 or $600, you can buy a GPU to plug into that. Having said that, for about $1,000, you can actually create a pretty good, GPU-based desktop. And so if you're considering that, the Fast AI forums have lots of threads where people help each other spec out something at a particular price point. Anyway, so to start with, I'd say use Crestle, and then, when you're ready to invest a few extra minutes getting going, use AWS. To use AWS, you basically... Huh? Yeah. Yeah. Yeah, I'm just talking to the folks online as well. So, okay. So AWS. When you get there, go to EC2. EC2, there's lots of stuff on AWS. EC2 is the bit where we get to rent computers by the hour, right? Now we're going to need a GPU-based instance. Unfortunately, when you first sign up for AWS, they don't give you access to them, so you have to request that access. So go to Limits up on the top left, right? And the main GPU instance we'll be using is called the P2. So scroll down to P2, and here P2.xlarge, you need to make sure that that number's not 0. If you've just got a new account, it probably is 0, which means you won't be allowed to create one. So you have to go Request Limit Increase. And the trick there is when it asks you, why do you want the limit increase, type fast.ai, because AWS knows to look out, and they know that fast.ai people are good people, so they'll do it quite quickly. That takes a day or two, generally speaking, to go through. So once you get the email saying you've been approved for P2 instances, you can then go back here and say launch instance. And so we've basically set up one that has everything you need. So if you click on Community AMI, and AMI is an Amazon machine image, it's basically a completely set up computer, right? And so if you type FastAI, all one word, you'll find here FastAI DL Part 1 version 2 for the P2, right? So that's all set up, ready to go. So if you click on select, and then it'll say, okay, what kind of computer do you want, right? And so we have to say, all right, I want a GPU compute type, and specifically I want a P2 extra large, right? And then you can say review and launch. I'm assuming you already know how to deal with SSH keys and all that kind of stuff. If you don't, check out the introductory tutorials and workshop videos that we have online. Or Google around for SSH keys. Very important skill to know anyway. All right, so hopefully you get through all that. You have something running on a GPU with the FastAI repo. If you use Crestle, just cd FastAI2, the repo's already there, git pull. AWS, cd FastAI, the repo is already there, git pull. If it's your own computer, you'll just have to git clone, and then away you go. All right, so part of all of those is PyTorch is pre-installed, and so PyTorch basically means we can write code that looks a lot like NumPy, but it's going to run really quickly on the GPU. Secondly, since we need to know like which direction and how much to move our parameters to improve our loss, we need to know the derivative of functions. PyTorch has this amazing thing where any code you write using the PyTorch library, it can automatically take the derivative of that for you. So we're not going to look at any calculus in this course, and I don't look at any calculus in any of my courses or in any of my work, basically ever, in terms of like actually calculating derivatives myself, because I've never had to. It's done for me by the library. So as long as you write the Python code, the derivative is done. So the only calculus you really need to know to be an effective practitioner is like, what does it mean to be a derivative? And you also need to know the chain rule, which we'll come to. All right. So we're going to start out kind of top down, create a neural net, and we're going to assume a whole bunch of stuff. And gradually we're going to dig into each piece, right? So to create neural nets, we need to import the PyTorch neural net library. PyTorch, funnily enough, is not called PyTorch, it's called Torch. Okay, so torch.nn is the PyTorch subsection that's responsible for neural nets. Okay, so we'll call that NN. And then we're going to import a few bits out of FastAI just to make life a bit easier for us. So here's how you create a neural network in PyTorch. The simplest possible neural network. You say sequential, and sequential means I am now going to give you a list of the layers that I want in my neural network. Right? So in this case, my list has two things in it. The first thing says I want a linear layer. So a linear layer is something that's basically going to do y equals ax plus b, right? But matrix multiply, not univariate, obviously. So it's going to do a matrix product, basically. So the input to the matrix product is going to be a vector of length 28 times 28, because that's how many pixels we have. And the output needs to be of size 10. We'll talk about why in a moment. But for now, this is how we define a linear layer. And then again, we're going to dig into this in detail, but every linear layer, just about in neural nets, has to have a nonlinearity after it. And we're going to learn about this particular nonlinearity in a moment. It's called the softmax. And if you've done the DL course, you've already seen this. So that's how we define a neural net. This is a two-layer neural net. There's also kind of an implicit additional first layer, which is the input. But with PyTorch, you don't have to explicitly mention the input. But normally we think conceptually like the input image is kind of also a layer. Because we're kind of doing things pretty manually, with PyTorch, we're not taking advantage of any of the conveniences in FastAI for building this stuff. We have to then write .CUDA, which tells PyTorch to copy this neural network across to the GPU. So now, from now on, that network is going to be actually running on the GPU. If we didn't say that, it would run on the CPU. Okay. So that gives us back a neural net, a very simple neural net. So we're then going to try and fit the neural net to some data. So we need some data. FastAI has this concept of a model data object, which is basically something that wraps up training data, validation data, and optionally test data. And so to create a model data object, you can just say, I want to create some image classifier data. I'm going to grab it from some arrays, right? And you just say, okay, this is the path that I'm going to save any temporary files. This is my training data, arrays, and this is my validation data, arrays. Okay? And so that just returns an object that's going to wrap that all up, and so we're going to be able to fit to that data. So now that we have a neural net, and we have some data, we're going to come back to this in a moment, but we basically say what loss function do we want to use, what optimizer do we want to use, and then we say fit. We say fit this network to this data, going over every image once, using this loss function and this optimizer, and print out these metrics. Bang. Okay, and this says here, this is 91.8% accurate. Okay, so that's like the simplest possible neural net. So what that's doing is it's creating a matrix multiplication followed by a nonlinearity, and then it's trying to find the values for this matrix which basically that fit the data as well as possible, that end up predicting this is a 1, this is a 9, this is a 3. And so we need some definition for as well as possible. And so the general term for that thing is called the loss function. So the loss function is the function that's going to be lower if this is better, right? Just like with random forests, we had this concept of information gain, and we got to like pick what function do you want to use to define information gain, and we were mainly looking at root mean squared error, right? Most machine learning algorithms we call something very similar to that loss, right? So the loss is how do we score how good we are? And so in the end, we're going to calculate the derivative of the loss with respect to the weight matrix that we're multiplying by to figure out how to update it, right? So we're going to use something called negative log likelihood loss. So negative log likelihood loss is also known as cross entropy. They're literally the same thing. There's two versions, one called binary cross entropy or binary negative log likelihood, and another called categorical cross entropy. They're the same thing. One is for when you've only got a 0 or 1 dependent. The other is if you've got like cat, dog, airplane or horse, or 0, 1 through 9, or so forth. So what we've got here is the binary version of cross entropy. And so here is the definition. I think maybe the easiest way to understand this definition is to look at an example. So let's say we're trying to predict cat versus dog. 1 is cat, 0 is dog. So here we've got cat, dog, dog, cat. And here are our predictions. We said 90% sure it's a cat, 90% sure it's a dog, 80% sure it's a dog, 80% sure it's a cat, right? So we can then calculate the binary cross entropy by calling our function. So it's going to say, okay, for the first one, we've got y equals 1. So it's going to be 1 times log of 0.9 plus 1 minus y, 1 minus 1 is 0, so that's going to be skipped. Okay, and then the second one is going to be a 0, so it's going to be 0 times something, so that's going to be skipped. And then the second part will be 1 minus 0. So this is 1 times log of 1 minus p, 1 minus 0.1 is 0.9. So in other words, the first piece and the second piece of this are going to give exactly the same number, which makes sense because the first one we said we were 90% confident it was a cat, and it was. And the second we said we were 90% confident it was a dog, and it was. So in each case, the loss is coming from the fact that, we could have been more confident. So if we said we were 100% confident, the loss would have been 0. Right? So let's look at that in Excel. So here's our .9, .1, .2, .8, right? And here's our predictions, 1001. So here's 1 minus the prediction, right? Here is log of our prediction. Here is log of 1 minus our prediction. And so then here is our sum. Okay? So if you think about it, and I want you to think about this during the week, you could replace this with an if statement rather than y, because y is always 1 or 0, right? Then it's only ever going to use either this or this. So you could replace this with an if statement. So I'd like you during the week to try to rewrite this with an if statement, okay? And then see if you can then scale it out to be a categorical cross-entropy. So categorical cross-entropy works this way. Let's say we were trying to predict 3 and then 6 and then 7 and then 2. So if we were trying to predict 3 and the actual thing that was predicted was like 4.7, right, versus like, well, actually think of it this way. We're trying to predict 3 and we actually predicted 5, or we're trying to predict 3 and we accidentally predicted 9. Like being 5 instead of 3 is no better than being 9 instead of 3. So we're not actually going to say like how far away is the actual number. We're going to express it differently. Or to put it another way, what if we're trying to predict cats, dogs, horses, and airplanes? You can't, like how far away is cat from horse? So we're going to express these a little bit differently. Rather than thinking of it as a 3, let's think of it as a vector with a 1 in the third location. And rather than thinking of it as a 6, let's think of it as a vector of zeros with a 1 in the 6th location. So in other words, one hot encoding. Right? So let's one hot encode our dependent variable. And so that way now, rather than trying to predict a single number, let's predict 10 numbers. Let's predict what's the probability that it's a 0, what's the probability it's a 1, what's the probability it's a 2, and so forth. Right? And so let's say we're trying to predict the 2, right? Then here is our binary cross-entropy. Sorry, categorical cross-entropy. So it's just saying, okay, did this one predict correctly or not? How far off was it? And so forth for each one, right? And so add them all up. So categorical cross-entropy is identical to binary cross-entropy. We just have to add it up across all of the categories. Right? So try and turn the binary cross-entropy function in Python into a categorical cross-entropy Python, and maybe create both the version with the if statement and the version with the sum and the product. Right? All right. So that's why in our PyTorch we had 10 as the output dimensionality for this matrix, because when we multiply by a matrix with 10 columns, we're going to end up with something of length 10, which is what we want. We want to have 10 predictions. Okay? So that's the loss function that we're using. All right, so then we can fit the model. And what it does is it goes through every image this many times. So in this case, it's just looking at every image once and going to slightly update the values in that weight matrix based on those gradients. And so once we've trained it, we can then say predict using this model on the validation set. Right? And now that spits out something of 10,000 by 10. Can somebody tell me why is this of shape, these predictions, why are they of shape 10,000 by 10? Go for it, Chris, it's right next to you.
Well, it's because we have 10,000 images we're training on.
10,000 images training on, so that's what, well, we're validating on in this case, but same thing. So 10,000 we're validating on, so that's the first axis.
Yeah, that's the first axis. And then the second axis is because we actually make 10 predictions per image.
Good, exactly. So each one of these rows is the probabilities that it's a 0, that it's a 1, that it's a 2, that's a 3, and so forth. Okay, very good. So in math, there's a really common operation we do called argmax. And when I say it's common, it's funny, like, at high school, I never saw argmax. First year undergrad, I never saw argmax. But somehow after university, everything's about argmax. So it's one of these things that's for some reason not really taught at school, but it actually turns out to be super critical. And so argmax is both something that you'll see in math, and it's just written out in full, argmax. It's in NumPy, it's in PyTorch, it's super important. And what it does is it says, let's take this array of preds, right? And let's figure out on this axis, remember axis 1 is columns, right? So across, as Chris said, the 10 predictions for each one, for each row. Let's find which prediction has the highest value and return not that. If it just said max, it would return the value. Argmax returns the index of the value, right? So by saying argmax axis equals 1, it's going to return the index, which is actually the number itself, right? So let's grab the first 5. Okay, so for the first one, it thinks it's a 3, then it thinks the next one's an 8, next one's a 6, the next one's a 9, next one's a 6 again. Okay, so that's how we can convert our probabilities back into predictions. All right, so if we save that away, call it preds, we can then say, okay, when does preds equal the ground truth? Right? So that's going to return an array of bools, which we can treat as 1s and 0s. And the mean of a bunch of 1s and 0s is just the average. So that gives us the accuracy. So there's our 91.8%. And so you want to be able to like replicate the numbers you see, and here it is. There's our 91.8%. Right? So when we train this, it tells us, the last thing it tells us is whatever metric we asked for, and we asked for accuracy. Okay, so the last thing it tells us is our metric, which is accuracy, and then before that we get the training set loss, and the loss is again whatever else we asked for, negative log likelihood, and the second thing is the validation set loss. PyTorch doesn't use the word loss, they use the word criterion, so you'll see here crit. Okay, so that's criterion equals loss. This is what loss function do we want to use, they call that the criterion. Same thing, okay? So here's how we can recreate that accuracy. So now we can go ahead and plot 8 of the images along with their predictions. And we've got 3, 8, 6, 9, oh, wrong, 5, wrong. Okay, and you can see like why they're wrong. Like this is pretty close to a 9. It's just missing a little cross at the top. This is pretty close to a 5. It's got a little bit of the extra here, right? So we've made a start. And all we've done so far is we haven't actually created a deep neural net. We've actually got only one layer. So what we've actually done is we've created a logistic regression. Okay, so a logistic regression is literally what we just built. And you could try and replicate this with sklearn's logistic regression package. When I did it, I got similar accuracy, but this version ran much faster because this is running on the GPU, where else sklearn runs on the CPU. Okay, so even for something like logistic regression, we can, implement it very quickly with PyTorch. Can you pass that to Ian?
So when we're creating our net, we have to do .CUDA. What would be the consequence of not doing that? Would it just not run?
It wouldn't run quickly. Yeah, it'll run on the CPU. Can you pass it to Jade?
So when we build the neural network, why is that we have to do linear and followed by a nonlinear?
So the short answer is because that's what the universal approximation theorem says is the structure which can give you arbitrarily accurate functions for any functional form. So the long answer is the details of why the universal approximation theorem works. Another version of the short answer is that's the definition of a neural network. So the definition of a neural network is a linear layer followed by a activation function, followed by a linear layer, followed by an activation function, etc. We go into a lot more detail of this in the deep learning course. But for this purpose, it's enough to know that it works. So far, of course, we haven't actually built a deep neural net at all. We've just built a logistic regression. And so at this point, if you think about it, all we're doing is we're taking every input pixel and multiplying it by a weight for each possible outcome, right? So we're basically saying, on average, the number 1, has these pixels turned on, the number 2 has these pixels turned on, and that's why it's not terribly accurate, right? That's not how digit recognition works in real life, but that's all we've built so far. Okay, can you pass that to Devin?
So you keep saying this universal approximation theorem.
Yeah.
Did you define that?
But let's cover it again because it's worth talking about. So, all right. So Michael Nielsen has this great website called Neural Networks and Deep Learning, and his chapter 4 is actually kind of famous now. And in it, he does this walkthrough of basically showing that a neural network can approximate any other function to arbitrarily close accuracy as long as it's big enough. And we walk through this in a lot of detail in the deep learning course. But the basic trick is that he shows that with a few different numbers, you can basically kind of cause these things to kind of create little boxes. You can move the boxes up and down. You can move them around. You can join them together to eventually basically create connections of towers, which you can use to approximate any kind of surface, right? So that's basically the trick. And so all we need to do, given that, is to kind of find the parameters for each of the linear functions in that neural network. So to find the weights in each of the matrices. And so far we've got just one matrix, and so we've just built a simple logistic regression so far. Kunal, did you have a question? No.
Just a small doubt. I just want to confirm that when you showed images of the examples of the images which were misclassified,
yeah,
they look rectangular. So it's just that while rendering, the pixels are being scaled differently. So are they still 28 by 28 square?
They're 28 by 28. I think they're square. I think they just look rectangular because they've got titles on the top. I'm not sure. Good question. I don't know. Anyway, they are square. And Matplotlib, does often fiddle around with what it considers black versus white, and having different size axes and stuff. So you do have to be a bit careful there sometimes. Okay, so hopefully this will now make more sense, because what we're going to do is dig in a layer deeper and define logistic regression without using nn.sequential, without using nn.linear, without using nn.log softmax. So we're going to do nearly all of the layer definition from scratch. Okay, so to do that, we're going to have to define a PyTorch module. A PyTorch module is basically either a neural net or a layer in a neural net, which is actually kind of a powerful concept of itself. Basically, anything that can kind of behave like a neural net can itself be part of another neural net. And so this is how we can construct particularly powerful architectures combining lots of other pieces. So to create a PyTorch module, just create a Python class, but it has to inherit from nn.module. So we haven't done inheritance before. Other than that, this is all the same concepts we've seen in OO already. Basically, if you put something in parentheses here, what it means is that our class gets all of the functionality of this class for free. It's called subclassing it. So we're going to get all of the capabilities of a neural network module that the PyTorch authors have provided, and then we're going to add additional functionality to it. When you create a subclass, there is one key thing you need to remember to do, which is when you initialize your class, you have to first of all initialize the superclass. Right? So the superclass is the nn.module. So the nn.module has to be built before you can start adding your pieces to it. And so this is just like something you can copy and paste into every one of your modules. You just say super.init. This just means construct the superclass first. Okay? So, having done that, we can now go ahead and define our weights and our bias. So our weights is the weight matrix. It's the actual matrix that we're going to multiply our data by. And as we discussed, it's going to have 28 times 28 rows and 10 columns. And that's because if we take an image which we flattened out into a 28 by 28 length vector, right, then we can multiply it by this weight matrix to get back out a length 10 vector, which we can then use to consider as a set of predictions. So that's our weight matrix. Now, the problem is that we don't just want y equals ax, we want y equals ax plus b. So the plus b in neural nets is called bias. And so as well as defining weights, we're also going to find bias. And so since this thing is going to spit out for every image something of length 10, that means that we need to create a vector of length 10 to be our biases. In other words, for everything 0, 1, 2, 3 up to 9, we're going to have a different plus b that would be adding, right? So we've got our data matrix here, which is of length 10,000 by 28 times 28, right? And then we've got our weight matrix, which is 28 by 28 rows by 10. So if we multiply those together, we get something of size 10,000 by 10. Right? And then we want to add on our bias. Oh, sorry, wrong way around. Add on our bias. Okay, like so. And so when we add on, and we're going to learn a lot more about this later, but when we add on a vector like this, it basically is going to get added to every row. Okay, so the bias is going to get added to every row. So we first of all define those. And so to define them, we've created a tiny little function called getWeights, which is over here, right? Which basically just creates some normally distributed random numbers. So torch.randn returns a tensor filled with random numbers from a normal distribution. We have to be a bit careful though. When we do deep learning, like when we add more linear layers later, imagine if we have a matrix which on average tends to increase the size of the inputs we give to it. If we then multiply by lots of matrices of that size, it's going to make the numbers bigger and bigger and bigger, like exponentially bigger. Or what if it made them a bit smaller? It's going to make them smaller and smaller and smaller, exponentially smaller. So like, because a deep network applies lots of linear layers, if on average they result in things a bit bigger than they started with, or a bit smaller than they started with, it's going to like exponentially multiply that difference. So we need to make sure that the weight matrix is of an appropriate size, that the inputs to it, the kind of the mean of the inputs basically is not going to change. So it turns out that if you use normally distributed random numbers and divide it by the number of rows in the weight matrix, it turns out that particular random initialization keeps your numbers at about the right scale, right? So this idea that like, if you've done linear algebra, basically if the eigenvalue, the first eigenvalue is like bigger than 1 or smaller than 1, it's going to cause the gradients to like get bigger and bigger or smaller and smaller. That's called gradient explosion, right? So we'll talk more about this in the deep learning course, but if you're interested, you can look up Kaiming-He initialization and read all about this concept, right? But for now, it's probably just enough to know that if you use this type of random number generation, you're going to get random numbers that are nicely behaved. You're going to start out with an input, which is mean 0, standard deviation 1. Once you put it through this set of random numbers, you'll still have something that's about mean 0, standard deviation 1. That's basically the goal, okay? One nice thing about PyTorch is that you can play with this stuff, right? So torch.randn, like try it out. Like every time you see a function being used, run it, right? And take a look. And so you'll see it looks a lot like NumPy, right? But it doesn't return a NumPy array, it returns a tensor. And in fact, now I'm GPU programming. Okay, like put .CUDA and now it's doing it on the GPU. So like, I just multiplied that matrix by 3 very quickly on the GPU, right? So that's how we do GPU programming with PyTorch, right? So this is our weight matrix. So we create, as I said, we create one 28 by 28 by 10. One is just rank 1 of 10 for the biases. We have to make them a parameter. This is basically telling PyTorch which things to update when it does SGD. That's very minor technical detail. So having created the weight matrices, we then define a special method with the name forward. This is a special method. The name forward has a special meaning in PyTorch. A method called forward in PyTorch is the name of the method that will get called when your layer is calculated. Okay, so if you create a neural net or a layer, you have to define forward. And it's going to get passed the data from the previous layer. So our definition is to do a matrix multiplication of our input data times our weights and add on the biases. So that's it. That's what happened earlier on when we said nn.linear. It created this thing for us. Okay. Now, unfortunately, though, we're not getting a 28 by 28 long vector. We're getting a 28 row by 28 column matrix, so we have to flatten it. Unfortunately, in PyTorch, they tend to rename things. They spell reshape, they spell it view. Okay, so view means reshape. So you can see here we end up with something where the number of images we're going to leave the same, and then we're going to replace row by column with a single axis, again, -1 meaning as long as required. Okay, so this is how we flatten something using PyTorch. So we flatten it, do a matrix multiply, and then finally we do a softmax. So softmax is the activation function we use. If you look in the deep learning repo, you'll find something called entropy example, where you'll see an example of softmax. But a softmax simply takes the outputs from our final layer. So we get our outputs from our linear layer. And what we do is we go e to the power of for each output. And then we take that number and we divide by the sum of the e to the power ofs. That's called softmax. Why do we do that? Well, because we're dividing this by the sum, that means that the sum of those itself must add to 1, right? And that's what we want. We want the probabilities of all the possible outcomes to add to 1. Furthermore, because we're using e to the power of, that means we know that every one of these is between 0 and 1, and probabilities we know should be between 0 and 1. And then finally, because we're using e to the power of, it tends to mean that slightly bigger values in the input turn into much bigger values in the output. So you'll see, generally speaking, in my softmax, there's going to be one big number and lots of small numbers. And that's what we want, right? Because we know that the output is one hot encoded. So in other words, the softmax activation function, the softmax nonlinearity, is something that returns things that behave like probabilities, and where one of those probabilities is more likely to be kind of high, and the other ones are more likely to be low. And we know that's what we want for to map to our one hot encoding. So a softmax is a great activation function to use to kind of help the neural net, make it easier for the neural net to map to the output that you wanted. And this is what we generally want. When we're kind of designing neural networks, we try to come up with little architectural tweaks that make it as easy for it as possible to match the output that we know we want. So that's basically it, right? Like, rather than doing sequential, and using nn.linear, nn.softmax, we've defined it from scratch. We can now say, just like before, our net is equal to that class.CUDA, and we can say .fit, and we get to within a slight random deviation, exactly the same output. Okay? So what I'd like you to do during the week is to play around with like torch.randn to generate some random tensors, torch.matmul to start multiplying them together, adding them up. Try to make sure that you can rewrite softmax yourself from scratch. Like try to fiddle around a bit with, reshaping view, all that kind of stuff, so that by the time you come back next week, you feel like pretty comfortable with PyTorch. And if you Google for PyTorch tutorial, you'll see there's a lot of great material actually on the PyTorch website to help you along, basically showing you how to create tensors and modify them and do operations on them. All right, great. Yes, you had a question. Can you pass it over?
So I see that the forward is the layer that gets applied after each of the linear layers. So,
well, not quite. The forward is just the definition of the module. So this is like how we're implementing linear.
So does that mean after each linear layer we have to apply the same function? Let's say we can't do a log softmax after layer 1 and then apply some other function after layer 2 if we have like a multi-layer neural network.
So normally we define neural networks like so. We just say, here is a list of the layers we want. Right? You don't have to write your own forward, right? All we did just now was to say like, okay, instead of doing this, let's not use any of this at all, but write it all by hand ourselves. Right? So you can write as many layers as you like in any order you like here. The point was that here we're not using any of that. We've written our own matmul plus bias, our own softmax. So this is just Python code. You can write whatever Python code inside forward that you like to define your own neural net. So like you won't normally do this yourself. Normally you'll just use the layers that PyTorch provides and you'll use .sequential to put them together. Or even more likely, you'll download a predefined architecture and use that. We're just doing this to learn how it works behind the scenes. All right, great. Thanks everybody.